Hello, and welcome to Tech with Shaping Pixel. This time we are bringing you free certification crash course. The AWS Certified CloudOps Engineer Associate Certification Exam, also known as SOA-C03, is designed for cloud operations engineers with at least 1 year of experience in deployment management, troubleshooting, networking, and security on Amazon Web Services. If you're not already subscribed, please subscribe to our YouTube channel. Thorough preparation will help you succeed and earn your AWS Certified CloudOps Engineer Associate credential. Review the official AWS exam guide for detailed task statements and domain weightings. This exam lasts 130 minutes and features 65 multiple choice or multiple response questions. Only 50 questions count toward your score, while 15 are unscored and used for evaluation. There is no penalty for guessing, so always answer every question. The passing score is 720 out of 1,000. The exam covers 5 domains: monitoring, logging, analysis, remediation, and performance optimization, reliability and business continuity, deployment, provisioning, and automation, security and compliance, and networking and content delivery. Each domain tests your skills in areas like configuring metrics with Amazon CloudWatch, implementing backup strategies with AWS Backup, automating deployments using CloudFormation and the AWS Cloud Development Kit, managing security with AWS Identity and Access Management, and optimizing networking with Amazon CloudFront and Route 53. Compute. When we talk about compute in Amazon Web Services, or AWS, we are referring to the processing power and resources that applications and systems need to perform tasks. Compute resources are essentially the brains behind the operations, handling instructions and calculations. Traditionally, compute resources are found in physical servers within data centers. These servers are equipped with components like central processing units, or CPUs, and random access memory, or RAM. Together, they process instructions from operating systems and applications, powering everything from websites to databases. AWS offers a wide range of compute services and features to meet different needs. For example, Amazon Elastic Compute Cloud, or EC2, provides virtual servers that can run continuously for months or even years, handling billions of instructions. On the other hand, AWS Lambda allows you to run code for just a few milliseconds in response to events, without managing any servers. This flexibility means you can choose the right compute resources for your specific requirements, whether you need long-running servers or quick event-driven functions. Ultimately, the compute services you use in AWS will depend on your business goals and technical needs. Amazon Elastic Compute Cloud, or EC2, is a core service in Amazon Web Services that lets you deploy virtual servers in the cloud. EC2 is often the first compute service you'll use when working with AWS, powering a wide range of applications. To launch an EC2 instance, you start by choosing an Amazon Machine Image, or AMI. AMIs are templates that include an operating system and pre-installed applications, making it easy to spin up new servers quickly. You can use AWS-provided AMIs, create your own, or select from the AWS Marketplace or Community AMIs. This flexibility helps you scale and automate deployments efficiently. Next, select an instance type, which defines the virtual hardware such as CPU, memory, and storage. EC2 offers various instance families, including general purpose, compute optimized, and memory optimized, so you can match resources to your workload. For cost control, choose from on-demand, spot, or reserved instances, each with different pricing and commitment levels. EC2 supports persistent storage with Amazon Elastic Block Storage, or EBS, and temporary storage with Instance Store Volumes. Security is managed through security groups, which act as firewalls and key pairs for secure login. Remember, keeping your operating system and security patches updated is your responsibility. EC2 Image Builder is a powerful tool from Amazon Web Services that automates the creation of secure, up-to-date virtual machine images for your EC2 instances and Docker containers. With EC2 Image Builder, you can set up a pipeline that handles everything from operating system updates and software installation to security patching and compliance checks. The pipeline can automatically test your images, ensuring they boot correctly, run sample applications, and meet your security policies. Once validated, your images can be distributed to selected AWS regions and rotated into your EC2 fleets, streamlining your deployment process. Getting started is simple. Define a pipeline with a name, description, tags, and a build schedule. Next, specify a recipe, which is a set of instructions for building your Amazon Machine Image, or AMI. You can use pre-built recipes or create your own, choosing from 6 supported operating systems. Add components to customize your image. Build components install software, while test components validate functionality. Each component uses a YAML-formatted document with build, validate, and test phases, allowing deep customization and automation. EC2 autoscaling is a feature in Amazon Web Services, or AWS, that automatically adjusts your EC2 resources to match demand. By using custom metrics and thresholds, it helps ensure your infrastructure is always right-sized for your needs. With EC2 autoscaling, you can set rules based on metrics like CPU utilization. For example, if your web server's CPU usage reaches 75%, autoscaling can automatically launch another EC2 instance to share the load. When demand drops and CPU usage falls to 20%, it can terminate unnecessary instances, keeping your environment efficient. This automation means your team does not have to manually add or remove servers. It leads to greater customer satisfaction since your applications remain responsive even during traffic spikes. Plus, you save money by only paying for resources when they are actually running, optimizing your costs. Pairing autoscaling with an elastic load balancer creates a flexible, scalable architecture. This ensures your applications can handle changing demand smoothly, providing a reliable experience for your users while keeping costs under control. EC2 autoscaling in Amazon Web Services, or AWS, helps you automatically adjust the number of EC2 instances in your environment. This ensures your applications always have the right resources, no matter the demand. To use EC2 autoscaling, you first need to define how new instances should be launched. You can do this with either a launch configuration or a launch template. Both options let you specify details like the Amazon Machine Image, or AMI, instance type, storage, security groups, and user data for automation. Launch templates are the newer, more advanced option. They allow you to set up all configuration options on a single page, including network settings, tags, and advanced features like spot instances or instance profiles. Templates can also be versioned for easy updates. Launch configurations are similar, but offer fewer advanced features and are created through a step-by-step process. While still supported, launch templates are now the preferred method. Once your template or configuration is ready, you create an auto-scaling group. This group manages how many instances run, scaling up or down based on policies like CPU utilization. Launch templates provide more flexibility and features, making them the recommended choice. Remember, without a launch configuration or template, autoscaling cannot launch or manage your EC2 instances. Autoscaling is a fundamental part of building elastic and fault-tolerant architectures in Amazon Web Services, or AWS. It acts as the glue that keeps your infrastructure running smoothly, automatically adjusting resources to meet demand. Yet, many people take autoscaling for granted, assuming it will just work out of the box. There are four main ways to control the number of instances in an autoscaling group. First, you can manually adjust variables, setting the upper and lower limits or the desired number of instances. Second, you can schedule scaling events to occur at specific times, adding or removing servers as needed. Third, dynamic scaling automatically responds to real-time demand, increasing or decreasing capacity as required. Finally, predictive scaling uses machine learning to analyze historical data and forecast future needs, provisioning resources in advance. Each autoscaling method has its strengths and weaknesses. Manual adjustments offer control, but require constant attention. Scheduled scaling is predictable, but may not react to unexpected changes. Dynamic scaling is responsive, but can be complex to configure. Predictive scaling is proactive, but relies on accurate data. Understanding these options is crucial. Next, let's explore why you might choose to manually scale your autoscaling groups. Autoscaling groups are designed to automatically adjust your resources based on demand. But sometimes relying solely on automation is not enough. There are moments when manual intervention is not just helpful, but essential. Imagine you know a huge spike in traffic is coming. Maybe your company is about to launch a major marketing campaign, or you are running an ad during a major sporting event with millions of viewers. In these cases, waiting for autoscaling to react could mean slow load times for users, or even downtime. That is why manually scaling your autoscaling group ahead of time can make all the difference. If you have just spent millions of dollars to attract users, you do not want them leaving because your website is slow. By increasing your desired number of instances before the surge, you ensure a smooth experience. As soon as the event is over and traffic returns to normal, you can scale back down. Adjust not only your desired number of instances, but also the minimum and maximum limits in your autoscaling group. This gives you full control during critical periods. Manual scaling lets you get ahead of big events and reduce downtime. However, it's not a daily solution. Reserve it for special, planned scenarios where automation alone is not enough. Dynamic scaling is a core feature of autoscaling in Amazon Web Services, or AWS. It automatically adds or removes instances based on demand, so you do not have to manage them manually. This keeps your resources efficient and responsive. Step scaling is the original method for dynamic scaling in AWS. It works by monitoring a metric like CPU usage and adjusting the number of instances in your autoscaling group. For example, if CPU usage goes above 80%, step scaling can add an instance. If it drops below 20%, it can remove one, helping you balance performance and cost. To prevent rapid scaling, cooldown policies pause scaling actions for a set time, letting new instances come online before more are added. CloudWatch alarms trigger scaling at different thresholds, like 60, 80, or 95% CPU usage, each adding a specific number of instances. Target tracking simplifies scaling. You set a target metric, such as 40% CPU utilization, and AWS automatically manages scaling to keep that target. It is especially useful for those who want less manual setup. Remember, scaling up is aggressive, but scaling down is slower to avoid instability. For small groups, each instance change has a big impact. Never delete CloudWatch alarms created by target tracking policies. When managing cloud resources, scaling is key to keeping your systems running smoothly. There are two main approaches: dynamic scaling, which reacts to changes, and predictive scaling, which anticipates them. Dynamic scaling is reactionary. Imagine a surge in users during lunch breaks. The system notices the increased load and automatically adds more instances to keep performance steady. It responds to real-time demand, optimizing metrics as they fluctuate. Predictive scaling, on the other hand, aims to stay ahead of the curve. Instead of waiting for a spike, it uses machine learning to forecast when traffic will rise or fall. This is especially useful for cyclical or recurring workloads, like business hours or scheduled analytics. The system learns from your historical data using at least 24 hours of CloudWatch metrics and can look back up to 14 days. It updates its forecasts daily, provisioning resources just before they are needed and scaling down as demand drops. You can test predictive scaling in forecast-only mode, letting you compare predictions to reality without affecting your users. If satisfied, enable full scaling control. Using both predictive and dynamic scaling together offers high availability, though it may increase costs. The right balance keeps your users happy and your systems efficient. Scheduled scaling is a powerful technique that lets you add or remove instances from your auto-scaling groups based on specific time parameters. Instead of relying solely on demand, you can schedule your resources to match predictable patterns, making your infrastructure more efficient. For instance, imagine you have a fleet of batch processing instances. You might want these to run only during the middle of the night, when spot instance prices are typically lower. By scheduling these instances to start and stop at set times, you can complete your work during those cost-effective hours. Another common use is in development environments. There is no need to keep test and development workloads running after business hours. With scheduled scaling, you can automatically turn off these environments at night and bring them back online in the morning. Scheduled scaling can also work alongside other scaling mechanisms. For example, your development and test environments might be scheduled to turn off at night, but during the day, dynamic scaling can adjust the number of instances as needed, ensuring resources are always optimized. Integrating scheduled scaling into your architecture can lead to significant cost savings, especially when paired with spot instances. This approach is most effective when your solutions can handle stopping and starting resources as needed. The AWS Elastic Load Balancer, or ELB, is a managed service that distributes incoming requests across multiple targets, such as EC2 instances, Lambda functions, or containers. This helps ensure your applications remain available and responsive. Relying on a single instance can lead to downtime if it fails or struggles with traffic spikes. By introducing an ELB and multiple instances, you gain high availability and automatic traffic distribution. ELB is elastic, scaling up or down as your traffic changes, all managed by AWS. There are three main types of ELB. The application load balancer is ideal for web applications using HTTP or HTTPS. The network load balancer offers ultra-high performance and low latency. The classic load balancer supports older EC2 classic environments. Each ELB uses listeners to define how requests are routed, target groups to organize resources, and rules to control traffic flow. Health checks automatically detect unhealthy targets and stop sending them traffic, ensuring only healthy resources serve your users. ELBs can be internal, serving only within your virtual private cloud, or internet-facing, accessible from the internet with a public DNS name. With cross-zone load balancing enabled, traffic is evenly distributed across all targets and all availability zones, maximizing efficiency and reliability. Server certificates play a crucial role in securing your elastic load balancers. When you use an application load balancer, or ALB, for your web applications, you have the option to handle both HTTP and HTTPS protocols, depending on your security needs. Configuring an HTTP listener on port 80 is straightforward, but using HTTPS on port 443 requires extra steps. HTTPS is the encrypted version of HTTP, creating a secure channel between clients and your ALB. To enable this, your ALB must have a server certificate and a security policy. The server certificate used by the ALB is an X509 certificate issued by a certificate authority. When setting up HTTPS, you can select a certificate from 4 options. Choose or upload a certificate to AWS Certificate Manager, or ACM, or choose or upload a certificate to Identity and Access Management, or IAM. ACM simplifies creating and managing SSL or TLS certificates within AWS, making it the preferred choice. IAM is used for third-party certificates or in regions where ACM is not supported, offering flexibility for different deployment scenarios. Summary: understanding server certificates ensures your load balancers securely handle encrypted traffic, protecting your web applications and users. The Application Load Balancer, or ALB, is a key service in Amazon Web Services for distributing incoming application traffic. Operating at Layer 7 of the Open Systems Interconnection Model, or OSI model, the ALB is designed for advanced routing and visibility, making it ideal for modern application architectures like microservices and containers. Before configuring your ALB, it is best practice to set up target groups. A target group is simply a collection of resources, such as web servers, that the ALB will route requests to. For example, you might create one target group for HTTP traffic on port 80 and another for secure HTTPS traffic on port 443. Each group can be customized with health checks, ensuring only healthy targets receive traffic. To create an ALB, navigate to the Load Balancing section in the Amazon Web Services Management Console. Assign a name, select Internet-Facing or Internal, and configure listeners for your desired protocols and ports. Choose your availability zones and security groups. Then associate your previously created target group. Review your settings and launch the ALB. Listeners define how the ALB handles incoming requests. You can add rules based on conditions like source IP address, forwarding specific requests to different target groups. A network load balancer, or NLB, is designed to distribute incoming traffic across multiple targets, ensuring high availability and performance. Unlike the application load balancer, which operates at the application layer, the NLB works at Layer 4 of the OSI model, focusing on TCP and UDP protocols. The NLB supports listeners for TCP, Transport Layer Security or TLS, and UDP. It can handle millions of requests per second, making it ideal for ultra-high performance needs. If your application requires a static IP address, the NLB is the recommended choice. Cross-zone load balancing can be enabled or disabled, offering flexibility depending on your deployment requirements. To configure an NLB in the Amazon Web Services Management Console, navigate to EC2 under Compute, then select Load Balancers. Choose to create a network load balancer, give it a name, and select Internal or Internet-Facing. Set your listener protocol and port, such as UDP on port 53 for DNS. Choose your availability zones, configure security settings, and create or select a target group. Register your targets, review your settings, and create the load balancer. The process is straightforward and similar to configuring an application load balancer, but with different protocol and port options. Your NLB is now ready to handle traffic efficiently. The classic load balancer is one of the original load balancing options in Amazon Web Services, or AWS. It supports TCP, SSL or TLS, HTTP, and HTTPS protocols, but it is not as feature-rich as newer options. Classic load balancers are unique because they support the EC2 Classic platform, which allowed instances to run in a single flat network shared with other customers. However, EC2 Classic is no longer available for accounts created after April 12, 2013. The Classic Load Balancer also supports TCP and SSL listeners, sticky sessions using application-generated cookies, and allows cross-zone load balancing to be enabled or disabled. To create a Classic Load Balancer, navigate to the EC2 dashboard, select Load Balancers, and choose to create a Classic Load Balancer. Assign a name, select your Virtual Private Cloud or VPC, and configure listeners such as port 80. Choose your availability zones and subnets, assign a security group, and configure health checks. Finally, select the EC2 instances to associate, add tags, review, and create. While the Classic Load Balancer is simple to set up, it is best practice to use the Application Load Balancer unless you have legacy needs. The ALB offers more features and flexibility for modern applications. AWS, or Amazon Web Services, is known for building services based on customer needs. One such innovation is the AWS Gateway Load Balancer, designed to simplify and enhance traffic management for virtual appliances in the cloud. Previously, deploying and scaling virtual appliances from AWS partners or the AWS Marketplace was challenging. To address this, AWS Gateway Load Balancer allows you to direct all inbound and outbound traffic from an internet gateway or virtual private gateway to a specific elastic network interface within your virtual private cloud or VPC. This is achieved using VPC ingress routing, which forwards traffic to the Gateway Load Balancer by updating route tables. The Gateway Load Balancer acts as a single point of access for all traffic, ensuring transparency and seamless flow. It automatically routes traffic through healthy virtual appliances and stops sending traffic to any that become unhealthy. This service also supports IP tunneling, preventing address conflicts, and enables you to add custom logic for inspecting and acting on network packets, all while maintaining sticky, transparent, and symmetric traffic flows. With AWS Gateway Load Balancer, managing and scaling virtual appliances becomes easier, more reliable, and more secure, empowering you to optimize your cloud network traffic with confidence. Elastic Load Balancers, or ELBs, and EC2 Autoscaling are two powerful Amazon Web Services tools that work best together. Let us quickly explore how they complement each other to boost both performance and cost efficiency. On their own, each service solves specific challenges. ELBs distribute incoming traffic across your resources using target groups and rules. EC2 Autoscaling automatically adjusts the number of instances in response to demand. However, using only one can create extra manual work. Without autoscaling, you must manually add or remove targets from your ELB. Without an ELB, distributing traffic evenly to your EC2 fleet becomes difficult. When you attach an ELB to an autoscaling group, the ELB automatically detects new instances and distributes traffic to them. For application load balancers or network load balancers, you associate your autoscaling group with a target group. For classic load balancers, your EC2 instances register directly with the load balancer. This seamless integration ensures your infrastructure scales efficiently as demand changes. To connect an existing load balancer, simply edit your autoscaling group. Select your classic load balancer or the appropriate target group for application or network load balancers, then save your changes. To understand serverless compute, imagine all the work involved in managing a server, installing software, patching, scaling, and configuring storage. With serverless, that maintenance disappears from your to-do list, letting you focus entirely on your code and business logic. AWS Lambda is Amazon Web Services' serverless compute service. Instead of managing servers, you write functions, small pieces of code that handle specific tasks. Lambda takes care of the infrastructure, so you only need to worry about your application's logic and configuration. A Lambda function has three main parts: input, the function itself, and output. You upload your code, choose the runtime, like Python, Java, or Node.js, and set how much memory and power your function needs. Lambda then allocates proportional CPU, network, and disk resources. Your Lambda function can be triggered in several ways: directly through the AWS console, software development kits or command line tools, via an HTTP endpoint, or automatically by AWS services like Amazon S3 or API Gateway, responding to events or schedules. Lambda automatically monitors your functions with logs and metrics, sending data to Amazon CloudWatch. You only pay for what you use, the number of requests, the duration your code runs, and the compute power you provision. Serverless means efficiency and simplicity. Amazon EC2 Container Service, or Amazon ECS, is a managed service that lets you run Docker-enabled applications as containers across a cluster of EC2 instances. With ECS, you do not need to handle complex cluster management yourself. Amazon Web Services, or AWS, manages it for you. Docker is software that automates installing and distributing applications inside Linux containers. A container holds everything an application needs to run except for the operating system, making it lightweight and portable. AWS Fargate is an engine that allows ECS to run containers without you managing servers or clusters. ECS offers two deployment models: Fargate Launch, which is simple and requires minimal configuration, and EC2 Launch, which gives you more control over instance types and scaling. Monitoring is handled by AWS CloudWatch, which tracks metrics and can send notifications when events like scaling occur. ECS clusters aggregate resources like CPU and memory, scaling dynamically from a single instance to thousands. Clusters are region-specific but can span multiple availability zones. Features like security groups, elastic load balancing, and auto-scaling are supported, making ECS flexible and powerful for containerized applications. Kubernetes is an open-source container orchestration tool that automates the deployment, scaling, and operation of containerized applications. It is designed to handle everything from a handful to millions of containers and works with different container runtimes like Docker. Elastic Container Service for Kubernetes, or EKS, is a managed service from Amazon Web Services that lets you run Kubernetes clusters on AWS infrastructure. With EKS, AWS manages the Kubernetes control plane, so you only need to focus on your worker nodes. The control plane is the brain of Kubernetes, scheduling containers onto nodes and tracking the state of your clusters. AWS provisions and manages this across multiple availability zones for resiliency. Worker nodes are the machines that actually run your containers, and you are responsible for managing these within EKS. To start, create an IAM service role with the Amazon EKS service policy and Amazon EKS cluster policy permissions. Next, set up a virtual private cloud using AWS CloudFormation. Install kubectl, the Kubernetes command line tool, and the AWS IAM Authenticator for secure access. Create your EKS cluster, configure kubectl, and provision worker nodes. Once connected, your EKS environment is ready for deploying applications with Kubernetes, combining AWS reliability with Kubernetes flexibility. Elastic Container Registry, or ECR, is a fully managed service from Amazon Web Services that lets developers securely store, manage, and distribute Docker images. With ECR, there is no need to provision infrastructure. AWS handles it all. ECR consists of several key components: the registry, authorization tokens, repositories, repository policies, and images. The registry is where your Docker images are hosted. Each AWS account gets a default registry, accessible via a unique URL. Within this registry, you can create multiple repositories to organize your images. Before your Docker client can interact with ECR, it must authenticate as an AWS user. This is done using an authorization token generated by running the AWS command line interface get-login command. The resulting Docker login command authenticates your client for 12 hours. Access to your registry and repositories is managed through AWS Identity and Access Management, or IAM, policies and repository policies. These policies allow you to control who can push or pull images, ensuring your Docker images remain secure. Once authenticated, use the Docker push command to upload images and the Docker pull command to retrieve them, making ECR a central hub for your container images. Storage. As organizations move to the cloud, they seek benefits like flexibility, scalability, cost efficiency, and security. Amazon Web Services, or AWS, offers a wide range of storage services to help businesses take full advantage of these cloud benefits. You might wonder why AWS provides so many different storage options. The answer is simple. Just like in traditional data centers, not all data is the same. Some data needs to be accessed quickly, some needs to be archived, and some requires extra security or durability. AWS storage solutions fall into three main categories: block storage, file storage, and object storage. Block storage divides data into blocks, offering low latency and is similar to directly attached disks. File storage organizes data as files within directories, allowing shared access, much like network-attached storage, or NAS. Object storage uses a flat address space, referencing each object with a unique key and supporting metadata for easy identification. AWS recognizes that every workload is unique. By offering a variety of storage services, AWS lets you choose the best fit for your specific requirements, ensuring your data is stored efficiently, securely, and cost-effectively. Kubernetes is an open-source container orchestration tool that automates the deployment, scaling, and operation of containerized applications. It is designed to handle everything from a handful to millions of containers and works with different container runtimes like Docker. Elastic Container Service for Kubernetes, or EKS, is a managed service from Amazon Web Services that lets you run Kubernetes clusters on AWS infrastructure. With EKS, AWS manages the Kubernetes control plane, so you only need to focus on your worker nodes. The control plane is the brain of Kubernetes, scheduling containers onto nodes and tracking the state of your clusters. AWS provisions and manages this across multiple availability zones for resiliency. Worker nodes are the machines that actually run your containers, and you are responsible for managing these within EKS. To start, create an IAM service role with the Amazon EKS service policy and Amazon EKS cluster policy permissions. Next, set up a virtual private cloud using AWS CloudFormation. Install kubectl, the Kubernetes command line tool, and the AWS IAM Authenticator for secure access. Create your EKS cluster, configure kubectl, and provision worker nodes. Once connected, your EKS environment is ready for deploying applications with Kubernetes, combining AWS reliability with Kubernetes flexibility. Amazon S3 offers a range of storage classes, each designed for different data access needs and cost considerations. Let's break down the key options so you can choose the best fit for your data. S3 Standard is the go-to for frequently accessed data, offering high throughput, low latency, and 11 nines or 99.9999999% durability across multiple availability zones. S3 Intelligent Tiering automatically moves your data between frequent, infrequent, and archive tiers based on usage, optimizing costs when access patterns are unpredictable. Both support Secure Sockets Layer, or SSL, encryption, and lifecycle rules for automated management. Amazon Simple Storage Service, or S3, offers a powerful feature called bucket versioning. This allows you to keep multiple versions of the same file, protecting your data from accidental or malicious deletion. When versioning is enabled, every time you overwrite or delete an object, S3 automatically creates a new version. Only the latest version appears by default, but all previous versions are still accessible. Versioning is not enabled by default, and once turned on, it cannot be disabled, only suspended. You can enable versioning during bucket creation or on an existing bucket through the AWS Management Console. Once enabled, each new or modified object receives a unique version ID. Existing objects get a null version ID until they are changed or deleted. To see all versions, simply select Show in the bucket's versioning view. This lets you recover older files or review changes. But remember, storing multiple versions can increase your storage costs. Deleting an object adds a delete marker, hiding it from view but not erasing previous versions. To permanently remove a version, you must specify its version ID when deleting. Hosting a static website on Amazon's Simple Storage Service, or S3, is straightforward if you follow the right steps. Let's walk through how to configure your S3 bucket for static website hosting. First, open your S3 bucket's properties page. Find the static website hosting tile and select it. By default, this feature is disabled. Choose Use this bucket to host a website. You'll need to provide an index document which acts as your home page and optionally an error document for handling errors. For your website to be accessible, you must make your bucket publicly readable. Go to the Permissions tab. Edit the Block Public Access settings and uncheck Block All Public Access. Save and confirm these changes. Next, add a bucket policy that allows everyone to perform the Get Object action, making your website files readable by the public. Upload your index.html file and any other necessary files to your bucket. When uploading, ensure you grant public read access to each object so visitors can view your website content. Once everything is set, use the provided S3 website endpoint to test your site. Your static website should now be live and accessible to anyone with the endpoint URL. Object-level logging with S3 buckets is a powerful feature that lets you track exactly what happens to your data. But did you know this capability is actually managed by AWS CloudTrail, not S3 itself. AWS CloudTrail is a service designed to record and track all API requests made within your AWS environment. Whether you use the AWS command line interface, software development kits, the management console, or even another AWS service, CloudTrail captures each API call as an event and stores it in a log file on S3. When you enable object-level logging, CloudTrail records specific S3 data events, such as getObject, putObject, and deleteObject. Each event includes important metadata like the identity of the caller, the timestamp, and the source IP address. This detailed tracking helps you monitor access and changes to your S3 objects for security and compliance. You can set up S3 data event logging in two ways: through the CloudTrail console by adding S3 buckets to a trail, or directly in the S3 Buckets Properties tab. Simply choose your trail, select which events to capture, and enable object-level logging. Object-level logging with S3 buckets is a powerful feature that lets you track exactly what happens to your data. But did you know this capability is actually managed by AWS CloudTrail, not S3 itself? AWS CloudTrail is a service designed to record and track all API requests made within your AWS environment. Whether you use the AWS command line interface, software development kits, the management console, or even another AWS service, CloudTrail captures each API call as an event and stores it in a log file on S3. When you enable object-level logging, CloudTrail records specific S3 data events, such as getObject, putObject, and deleteObject. Each event includes important metadata like the identity of the caller, the timestamp, and the source IP address. This detailed tracking helps you monitor access and changes to your S3 objects for security and compliance. You can set up S3 data event logging in two ways: through the CloudTrail console by adding S3 buckets to a trail, or directly in the S3 Buckets Properties tab. Simply choose your trail, select which events to capture, and enable object-level logging. Amazon S3 Object Lock is an advanced feature that helps you protect your data using the write once, read many, or warm compliance model. This prevents objects from being deleted for a set period or indefinitely. To enable Object Lock, you must turn it on when creating a new S3 bucket. It cannot be enabled on existing buckets. Versioning must also be activated first. Once Object Lock is enabled, it is permanent and cannot be disabled. Object Lock offers two retention modes: governance mode and compliance mode. Governance mode blocks most users from deleting or overriding objects during the retention period, but users with special permissions can override it. Compliance mode is stricter. No user, not even the AWS root account, can delete or alter objects until the retention period ends. Both modes require you to set a retention period in days. You can also set Object Lock on individual objects. Legal holds can be applied to object versions, preventing deletion without an expiration date. Only users with specific permissions can remove a legal hold. Object Lock in S3 buckets ensures your data stays protected, helping you meet strict compliance requirements like those from the Financial Industry Regulatory Authority. Speeding up your long-distance Amazon S3 data transfers is easier than you might think. With transfer acceleration, you can move data into or out of S3 buckets much faster, especially over large distances. Transfer acceleration leverages Amazon CloudFront, which is a content delivery network, or CDN. CloudFront uses edge locations in major cities around the world to route your data. When you upload or download data with transfer acceleration enabled, your request first goes to the nearest CloudFront edge location. From there, it travels through Amazon's high-speed, optimized network directly to your S3 bucket, reducing latency and improving transfer speeds. It is important to note that transfer acceleration comes with additional costs. While standard data transfers into S3 from the internet are free, using transfer acceleration incurs a per gigabyte fee based on the edge location. The same applies to data transferred out of S3, whether to the internet or another AWS region. To enable transfer acceleration, simply select your S3 bucket in the console, go to Properties, and choose the Transfer Acceleration option. Remember, your bucket name must be DNS compliant and cannot contain periods. Transfer acceleration does not support certain operations, such as listing buckets, creating or deleting buckets, or cross-region copies using put object copy. Configuring bucket event notifications in Amazon Web Services, or AWS, lets you monitor specific actions in your storage buckets. You can send alerts to an Amazon Simple Notification Service topic, or an Amazon Simple Queue Service queue, or a Lambda function. To get started, create a new topic in Amazon Simple Notification Service, or SNS. Give your topic a name like S3 Put Event and accept the default settings. Next, create a subscription to this topic using your email address. Confirm the subscription from your inbox to start receiving notifications. Now, head to your S3 bucket's properties and select the Events section. Add a new notification, name it, and choose the event type you want to monitor, such as Put Events for new uploads. You can filter events by prefix or suffix, but for now, leave those blank. Set the destination to your SNS topic. Upload a file to your bucket. When the event occurs, Amazon S3 sends a notification to your SNS topic, which then emails you details about the event, including the source, region, and file name. That's how you configure S3 bucket event notifications and receive real-time alerts using Amazon SNS in AWS. Let's explore an advanced Amazon Simple Storage Service, or S3, bucket property called Requester Pays. This feature changes who is responsible for certain cost when accessing data stored in an S3 bucket, making it especially useful for buckets with high public access or shared datasets. When Requester Pays is enabled, the requester, not the bucket owner, pays for the costs associated with requests and data transfer. However, the bucket owner still covers the storage costs for the objects in the bucket. This setup is ideal for scenarios where multiple users or organizations need access to the same data, ensuring fair distribution of data transfer expenses. To enable Requester Pays, simply select the Requester Pays option in the bucket's properties. You can choose to enable or disable this feature, then save your changes. From that point on, any post, GET, or head requests must include the XAMZ request payer header, confirming the requester accepts the associated costs. A crucial requirement is that all access must be authenticated. Anonymous requests are not supported, as Amazon Web Services, or AWS, needs to identify which account to charge. This ensures transparency and accurate billing for every data access. Amazon S3 Server Access Logging lets you track requests made to your S3 bucket and its objects. Each log entry can include the request type, resource accessed, IP address, or AWS identity and access management user, timestamp, response status, error code, and object size. Enabling logging is useful for root cause analysis after incidents and may be required for audit or governance compliance. However, Amazon S3 only provides these logs on a best effort basis, so they are not guaranteed to capture every request. Logs are delivered every few hours, and there's no guarantee that every request will be logged or that logs will arrive within a specific time frame. Sometimes a log might not be sent at all, so use them to understand traffic patterns rather than for complete auditing. To enable logging, select your bucket in the Amazon S3 console, go to the Properties tab, and find the Server Access Logging section. Click Edit, Enable Logging, and choose a destination bucket in the same region. Optionally, add a target prefix and select your preferred log object key format. The destination bucket cannot have logging enabled, S3 object lock, or requester pays. Default encryption is supported but not SSE KMS. Storage costs apply for log files. When setting up logging for your Amazon Web Services Simple Storage Service, or AWS S3, you need to ensure that your source bucket can write logs to a destination bucket. This process involves configuring specific permissions. The S3 logging service requires access to write log files into your destination bucket. If you are using the AWS Management Console, these permissions are set automatically. However, if you are configuring logging programmatically, you must set these permissions yourself to ensure logs are delivered correctly. While you might consider adding the log delivery group to the bucket access control lists, or ACLs, AWS no longer recommends this method. Instead, the preferred approach is to use a bucket policy. This policy should grant write access for logging. If you configure server access logging outside the console, remember to add this policy yourself to keep your logs flowing securely and reliably. Let us break down what you will find in an Amazon Simple Storage Service, or S3, server access log record. Each log entry is a single line with fields separated by spaces. The first field is the bucket owner, which is the canonical user ID of the bucket's owner. Next is the bucket name, followed by the time of the request in Coordinated Universal Time, or UTC. The remote IP address shows who made the request. The requester field displays the AWS Identity and Access Management, or IAM, identity for authenticated users, or a hyphen for unauthenticated ones. Request ID is a unique string for each request. Operation tells you what action was performed, and key is the object name. Request URI shows the HTTP request's Uniform Resource Identifier. HTTP status is the numeric status code, and error code appears if something went wrong. If a field's data is unknown or not applicable, you will see a hyphen. For example, unauthenticated requests or 0 bytes sent will display a hyphen in those fields. Other fields include bytes sent, object size, total time, turnaround time, referrer, user agent, version ID, host ID, signature version, cipher suite, authentication type, host header, TLS version, access point Amazon resource name, or ARN, and ACL required. Identity-based policies are attached to an AWS Identity and Access Management, or IAM, user, group, or role. These policies define which S3 resources, like buckets or objects, a user can access. For example, a policy might allow a user to perform all S3 actions on a specific bucket, such as S3 Deep Dive. You can also add conditions like restricting access based on the user's IP address. Resource-based policies are attached directly to S3 resources, such as buckets. The most common are bucket policies, written in JSON, which specify who can access the bucket and what actions they can perform. Unlike identity-based policies, bucket policies require a principal element to define who is allowed or denied access. S3 Access Control Lists, or ACLs, provide another way to manage access. ACLs can grant permissions to specific AWS accounts or predefined groups like the bucket owner or everyone. However, ACLs are less granular than policies and do not support conditions or explicit denies. When multiple policies apply, AWS evaluates them together. By default, access is denied unless explicitly allowed. If any policy includes a deny, it overrides any allow. For example, if a bucket policy denies delete actions, that deny takes precedence. In summary, you can use IAM policies, bucket policies, and ACLs together to control S3 access. Remember, deny always overrides allow, ensuring the principle of least privilege is maintained for your S3 resources. Amazon's Simple Storage Service, or S3, is often used to store massive data sets that need to be shared across different teams, services, or applications. But managing access at scale can quickly become complicated and overwhelming. Traditionally, administrators relied on identity and access management policies, bucket policies, and access control lists. These methods can create large, confusing policies, especially when each requester needs different permissions. To address this, Amazon Web Services introduced S3 access points. An S3 access point is created and attached to a single bucket. You can have multiple access points for one bucket, each with its own permissions tailored for specific teams or applications. However, access points cannot be shared across multiple buckets. Access points only allow object operations, like getObject and putObject, not bucket-level actions. Each access point can be configured to accept requests from a specific virtual private cloud, or VPC, or from anywhere. By default, public access is blocked for new access points. Access point policies work alongside bucket policies, but can only be as permissive as the bucket allows. Each access point has a unique Amazon resource name, or ARN, and can be managed through the AWS console, SDKs, or REST APIs. Data leaks from unprotected Amazon S3 buckets have caused major security breaches and financial penalties for organizations. To help prevent these incidents, Amazon Web Services, or AWS, has improved security features for S3 buckets. When you create a new S3 bucket, AWS automatically blocks all public access by default. This means you must actively change the setting if you want to allow public access. The default setting is designed to keep your data safe from accidental exposure. If you need some public access, you can turn off the block and choose from 4 specific options. These let you control access through access controllers, bucket policies, and cross-account permissions. You can mix and match these settings to fit your security needs. Even if you try to grant public access through access control lists or ACLs, the block all public access setting overrides your changes. You will see warnings and access denied errors, ensuring your bucket stays protected unless you intentionally change the settings. If you remove the block, AWS warns you about the risks. Granting public access is possible, but AWS highlights the security implications. Re-enabling the block instantly removes public access, making it a powerful tool for securing your data. Amazon S3's Access Analyzer is a powerful tool designed to help you keep your data secure. It alerts you whenever your S3 buckets are configured to allow public access or access from other Amazon Web Services or AWS accounts, including third-party accounts. Access Analyzer scans your buckets and identifies which ones are exposed, what level of access has been granted, and how that access is provided. For example, if a bucket is public or accessible by another account, Access Analyzer will show you the details, such as whether access is given by an access control list, or ACL, a bucket policy, or an access point policy. If you discover a bucket is public by mistake, you can block public access with a single click. Access Analyzer updates its findings every 30 minutes and lets you download a report as a CSV file so you can review all bucket permissions in your region. To use Access Analyzer, you must first create an accounts-level analyzer in Identity and Access Management, or IAM, for each region you want to monitor. Setup is simple and ensures your S3 buckets stay protected from unintended exposure. Cross-origin resource sharing, or CORS, is a key feature in Amazon Simple Storage Service, also known as Amazon S3. CORS lets web applications request resources from a different domain than their own, making it possible to build flexible, client-side web apps that interact with S3 buckets. To enable CORS in Amazon S3, you need to configure specific policies within your bucket's settings. These policies are found under the Permissions tab of your S3 bucket. By setting up CORS, you control which domains can access your resources, what HTTP methods they can use, and which headers are permitted in requests. A CORS policy in S3 can include multiple rules. Each rule specifies allowed origins, methods, and headers. For example, you might allow put, post, and delete requests from www.cloudacademy.com and permit all headers in pre-flight requests. The allowed headers element defines which headers are accepted, while expose header determines which response headers are accessible to applications. When a browser sends a pre-flight request, S3 checks the CORS policy for a matching rule. The request's origin, method, and headers must match the policy's allowed origins, allowed methods, and allowed headers. Multiple rules can be set for different origins and methods, offering flexible access control. Protecting your data in Amazon Simple Storage Service, or Amazon S3, is essential. Failing to secure your data can lead to serious consequences. Let us quickly break down the 3 main server-side encryption options Amazon S3 offers to keep your information safe. Server-side encryption with S3 managed keys, or SSE S3, is the default for all new uploads as of January 2023. With SSE S3, Amazon Web Services, or AWS, handles all key management, including rotation. You simply upload your data, and S3 takes care of the rest. Server-side encryption with Key Management Service Managed Keys, or SSE KMS, uses AWS Key Management Service to generate encryption keys. You can choose between AWS managed keys or customer managed keys for more control. SSE KMS also allows you to track and audit key usage with AWS CloudTrail, adding an extra layer of security. Server-side encryption with customer-provided keys, or SSEC, lets you supply your own encryption keys. S3 uses your key to encrypt and decrypt data, but you must use a secure HTTPS connection for every request. Amazon S3's default encryption is SSE S3, but you can switch to SSE KMS for greater flexibility. Choose the method that best fits your security needs and always prioritize data protection. Client-side encryption with Amazon Simple Storage Service, or S3, lets you encrypt your data before it ever leaves your premises. This adds an extra layer of security during transit and means you do not need server-side encryption once your data reaches S3. The Amazon S3 encryption client is your tool for this process. It generates a unique, symmetric, plain-text data encryption key to encrypt your object data. Then it encrypts that data key using a wrapping key, a process called envelope encryption. S3 itself simply stores the encrypted data and key, unaware of their encrypted state. You have flexibility with your wrapping key. Use symmetric or asymmetric keys, leverage the Amazon Web Services Key Management Service, or AWS KMS, or provide your own key. Using KMS is called client-side encryption with KMS-provided keys, or CSE KMS. Using your own key is called CSE-C. The S3 encryption client handles key creation, data encryption, and key wrapping. After encrypting, both the encrypted object and encrypted key are uploaded to S3. For decryption, the client retrieves and unwraps the key, decrypts the data, and deletes the plain text key from memory. Let us explore EC2 instance-level storage, also known as Instant Store Volumes. These are local disk drives that physically reside on the same host as your Amazon EC2 instance, providing fast, temporary storage. Unlike persistent storage options, Instant Store Volumes offer ephemeral storage. This means any data stored is temporary and not persistent. If your instance is stopped or terminated, all data on the Instant Store Volume is lost and cannot be recovered. It is not recommended to store critical or valuable data on Instant Store Volumes. If the underlying host fails, or if the instance is stopped or terminated, your data will be wiped. However, rebooting the instance does not affect the data. Instant Store Volumes are included in the price of your EC2 instance and offer extremely high input and output speeds. For example, i3 family instances can reach up to 3.3 million random read input-output operations per second. These volumes are ideal for caching, buffering, or workloads with frequently changing data. Instant Store Volumes inherit security from EC2, such as identity and access management policies. Not all instance types support them, so check AWS documentation. For persistent or shared data, use Elastic Block Store instead. Amazon Elastic Block Store, or EBS, is a service that provides persistent, durable block-level storage for your Amazon EC2 instances. Unlike Instant Store Volumes, EBS volumes are independent resources, offering flexibility and resilience for your data. EBS volumes can be attached to EC2 instances and are ideal for rapidly changing data or workloads needing specific input-output operations per second, known as IOPS. EBS volumes persist data even if your instance is stopped or terminated, as long as you configure it to do so. You can also resize EBS volumes elastically, making it easy to scale storage as your needs grow. There are two main types of EBS volumes: solid-state drive, or SSD-backed, and hard disk drive, or HDD-backed. SSD volumes are great for transactional workloads and boot volumes, while HDD volumes are designed for high-throughput tasks like big data processing and log storage. EBS allows you to create point-in-time backups called snapshots, which are stored in Amazon Simple Storage Service, or S3. Snapshots are incremental and can be used to restore data or create new volumes. EBS offers simple encryption using the Advanced Encryption Standard 256 algorithm, managed by the Key Management Service, or KMS. This ensures your data is secure both at rest and in transit. Amazon Web Services, or AWS, offers a range of storage solutions, each designed for different needs. Let us focus on Amazon Elastic File System, or EFS, and see how it fits into the AWS storage ecosystem. Amazon's Simple Storage Service, or S3, is object storage, best for storing large files that are written once and read many times, like videos or backups. Amazon Elastic Block Store, or EBS, is block-level storage, ideal for fast, low-latency access and persistent storage for a single EC2 instance, much like a computer's hard drive. Amazon Elastic File System, or EFS, is file-level storage optimized for low latency and supports access by multiple EC2 instances at once. It appears like a traditional file manager, using familiar file system features, such as locking, renaming, and hierarchical folders. EFS allows EC2 instances to access shared file systems through mount points across multiple availability zones. This setup is similar to traditional network-attached storage, but fully managed in the cloud. EFS is highly available, durable, and scalable to petabytes. It supports standard operating system APIs, NFS versions 4.1 and 4.0, and enables parallel access for applications across multiple instances and zones. Amazon Elastic File System, or EFS, offers flexible cloud storage for your data. Understanding its storage classes and performance modes helps you optimize both cost and performance for your workloads. EFS provides two storage classes, Standard and Infrequent Access, or IA. Standard is the default, ideal for frequently accessed data. IA is designed for data you rarely need, like audit logs, and offers lower storage costs. However, with IA, you pay for each read and write, and there is higher latency for the first byte compared to Standard. EFS Lifecycle Management can automatically move files between Standard and IA based on how often they are accessed. You can set this period to 14, 30, 60, or 90 days. Files under 128 kilobytes and metadata always stay in Standard. EFS offers two performance modes: General Purpose, which supports up to 7,000 operations per second with low latency, and Max I/O, which provides virtually unlimited throughput in IOPS, but with higher latency. Choose based on your workload's needs. There are also two throughput modes: Bursting Throughput, which scales with your storage size, and Provisioned Throughput, for consistently high performance regardless of file system size. Provisioned mode incurs extra charges. Let's walk through how to create and mount an Amazon Elastic File System, or EFS, using the AWS Management Console and the EFS Mount Helper for Linux-based EC2 instances. Before you begin, make sure you have a virtual private cloud, or VPC, with public subnets and at least one running EC2 instance. You'll also need security groups, one allowing SSH access to your EC2 instances and another for EFS that permits Network File System, or NFS, traffic on port 2049 from your EC2 security group. In the AWS console, navigate to EFS and create a new file system. Select your VPC, configure mount targets in your subnets, and assign the EFS security group. Choose Lifecycle Management, Throughput, Performance Mode, and enable encryption if needed. Review your settings and create the file system. Install the EFS Mount Helper utility on your EC2 instances. Create a directory, then use the provided mount command to connect your instance to EFS. The Mount Helper simplifies setup and includes built-in logging at var/log/amazon/EFS. Create a file in the EFS directory on one instance. Instantly, it appears on the other, confirming both EC2 instances share the same EFS storage. That's how easy it is. Let us explore the essentials of securing your Elastic File System, or EFS, focusing on access control, permissions, and encryption. These are critical for protecting sensitive data stored in the cloud. Before creating or managing an EFS file system, you need specific permissions. For EFS, you must allow Elastic File System create file system and Elastic File System create mount target. For Amazon Elastic Compute Cloud, or EC2 permissions, like describe subnet, create network interface, and describe network interfaces, are required. These permissions enable you to create the file system and its mount targets. When using the AWS Management Console, additional permissions allow you to view EFS resources, query EC2 for network details, and use the Key Management Service, or KMS, if encryption is enabled. EFS supports encryption at rest using AWS Key Management Service. You can select a customer master key, or CMK, managed either by you or by AWS. These keys encrypt your data encryption keys, ensuring your files remain protected while stored. To secure data moving between EFS and your client, enable encryption in transit using the Transport Layer Security, or TLS protocol. The EFS Mount Helper simplifies this process, creating a secure tunnel for your data. With the right permissions and encryption, EFS keeps your cloud data secure both at rest and in transit. If you need to move your on-premise data into Amazon Elastic File System, or EFS, there is a straightforward solution. Many organizations want to migrate existing datasets, like employee home directories, from local files servers to EFS to take advantage of its scalability and flexibility. The recommended approach is to use AWS DataSync. AWS DataSync is a service designed to securely migrate, move, and synchronize data from your on-premise environment to AWS storage services such as EFS or Amazon Simple Storage Service, also known as S3. Data transfer can happen over a direct connect link or the internet. To get started, you download the DataSync agent as a VMware ESXi host, configure it with your source and destination, and associate it with your AWS account. The agent acts as a bridge between your on-premise file system and EFS. AWS DataSync is also useful for transferring files between EFS file systems, even across AWS accounts. You can migrate NFS file systems, enable lifecycle management for cost savings, or replicate EFS file systems across regions for disaster recovery. While setup details are beyond this overview, AWS provides documentation and quick start guides to help you get started with DataSync and streamline your data migration to EFS. When storing data in Amazon Web Services, or AWS, you have several options. Amazon FSx stands out by offering fully managed file systems tailored for specific workloads, making it easier to choose the right storage for your needs. Amazon FSx for Windows File Server delivers a scalable, fully managed Microsoft Windows file system. It is perfect for Windows-based applications needing shared storage, supporting thousands of concurrent connections worldwide. Features include user quotas, end-user file restore, and integration with Microsoft Active Directory, which can be managed by AWS or on-premises. Data is encrypted at rest and in transit, and you can enable data deduplication to save space. Amazon FSx for Lustre is designed for high-performance computing. It provides a POSIX-compliant file system with up to 100 gigabits per second throughput and sub-millisecond latency. FSx for Lustre integrates deeply with Amazon's Simple Storage Service, or S3, allowing you to link S3 buckets and access objects as files, making it ideal for machine learning and data analytics. Choose FSx for Windows File Server for Windows workloads needing shared access and administrative controls. Select FSx for Lustre when speed and performance are critical, especially for high-performance computing or machine learning tasks. Meet Company A. They rely on on-premises servers and traditional storage arrays, but as their data grows, they face challenges with scaling, costs, and managing infrastructure across multiple locations. Company A wants to scale efficiently, reduce hardware investments, and centralize data access. Traditional storage arrays are expensive and hard to manage, especially with multiple sites. They need a flexible, hybrid solution. Enter AWS Storage Gateway. This service bridges on-premises infrastructure with the AWS cloud, allowing seamless data movement and access. It uses a local cache for staging uploads and providing low-latency access to frequently used data. You can deploy Storage Gateway as a virtual machine on VMware ESXi, Microsoft Hyper-V, or Linux KVM, as a pre-configured hardware appliance, or as an Amazon EC2 instance in the AWS cloud. There are 4 gateway types: S3 File Gateway for Amazon S3, FSX File Gateway for FSX for Windows File Server, Tape Gateway for virtual tape libraries, and Volume Gateway for block storage using ISCI. Costs include storage, requests, and data transfer fees. Storage and request pricing depend on the gateway type, while data transfer into AWS is free. Amazon Storage Gateway offers 4 types: S3 File Gateway, FSX File Gateway, Volume Gateway, and Tape Gateway. Each is designed for specific storage needs, from backup and archiving to seamless cloud migration. S3 File Gateway is ideal for backing up data like SQL databases and Hadoop clusters to Amazon Simple Storage Service, or S3. It lets you create file shares using Network File System or Server Message Block protocols, mapping files directly to S3 buckets. With features like S3 Object Lock, versioning, and lifecycle configurations, you can optimize costs by moving data to lower-cost storage tiers such as S3 Glacier Flexible Retrieval. FSX File Gateway is perfect for organizations needing a Microsoft Windows file system experience. It integrates with Microsoft Active Directory and supports features like shadow copies and data deduplication. FSX excels at multi-user file sharing, supporting up to 500 active users per gateway. Volume Gateway provides iSCSI block-level storage for on-premises applications. It is great for disaster recovery and cloud migration, allowing you to back up volumes as Amazon Elastic Block Store snapshots and restore them as needed. Tape Gateway replaces physical tape libraries with virtual tapes stored in AWS. It integrates with existing backup software, compresses and encrypts data, and archives tapes to Amazon Glacier. Choose your gateway based on your data type, sharing needs, and backup strategy. Let's walk through configuring an Amazon S3 file storage gateway on an EC2 instance. Start by opening the AWS console, searching for Storage Gateway, and clicking to create a new gateway. Name your gateway, select your time zone, and choose the S3 File Gateway option. Next, select Amazon EC2 as your hosting platform. Follow the provided setup instructions, then launch a new EC2 instance. Name it, keep the default Amazon machine image, and select at least an M5.X large instance type, as recommended. Choose a key pair for secure access, and configure your network settings, ensuring public IP is enabled. Create a new security group, leaving port 22 open for SSH, and open ports 80, 2049, 111, and 20048 for NFS access. Add a storage volume of at least 150 gigabytes. Then launch your instance and wait for it to initialize. Once your gateway is active, create an NFS file share linked to your S3 bucket. Select your gateway, specify your bucket, and leave protocol and storage class settings as defaults. Review and create the file share. Mount the file share on another EC2 instance using the provided Linux command. Create a directory, mount the share, and verify with the df command. Create a file, then check your S3 bucket to confirm seamless integration. Before diving into the AWS console to create backups, it is important to understand some key AWS backup terms. These concepts will help you manage and protect your data more effectively. A backup rule in AWS Backup specifies when and where your data should be backed up, as well as what actions to take over time. With backup rules, you can set schedules, define retention policies, and even manage cross-account backups. A backup plan is simply a collection of one or more backup rules. You assign resources to a backup plan, ensuring your data is protected according to your chosen policies. In AWS Backup, a resource is any item you want to back up. This could be an EC2 instance, an on-premises virtual machine, or an RDS database. All backups are stored in a vault, which is an AWS-managed encrypted storage location designed to keep your data safe. Enabling Vault Lock helps you meet compliance requirements by preventing your data from being re-encrypted, which can protect against ransomware attacks. Vault Lock uses the Write Once, Read Many, or WORM model to secure your backups. A job is the process of creating or restoring a backup according to your backup plan. Jobs allow you to track all backup and restore activities performed by AWS Backup. AWS Data Sync is a managed service designed to simplify and secure data transfers. Whether you need to move data from your on-premises data center to the cloud or between AWS storage services, Data Sync streamlines the process, making migrations and ongoing transfers efficient and reliable. Data Sync supports both migrations and ongoing data management. It can transfer data between on-premises storage and AWS or between different AWS storage services. The service is compatible with network file system shares, server message block shares, and self-managed object storage, providing flexibility for various environments. Data Sync automates and manages transfers, reducing manual effort and complexity. At the time of this recording, Data Sync works with Amazon's Simple Storage Service, or Amazon S3, Amazon Elastic File System, Amazon FSx for Windows Server, and AWS Snowcone. This broad compatibility makes it a versatile tool for many storage scenarios. Data Sync leverages AWS virtual private cloud endpoints for high bandwidth and low latency. Its parallel multi-threaded architecture enables transfer speeds up to 10 gigabits per second. Security is ensured through transport layer security encryption in transit and data validation for integrity. AWS Data Sync uses a straightforward per gigabyte pricing model, making costs predictable and avoiding surprises. Migrating data to Amazon Web Services, or AWS, can transform how organizations manage, store, and process information. Let's explore 3 key strategies for moving your data to AWS, each tailored to different business needs. If you have large amounts of rarely accessed data on your own servers, archiving to cold storage in the cloud is a smart move. Amazon S3 Glacier, especially Glacier Deep Archive, offers a cost-effective solution for long-term storage. Using AWS Data Sync, you can automate the migration of this data from your data center to Glacier, ensuring durability and reducing the burden of maintaining legacy storage systems. For businesses needing frequent or ongoing data transfers, AWS provides options like Amazon S3, Amazon FSx for Windows File Server, or Elastic File System, known as EFS. These services support regular migrations for backup or disaster recovery. For example, you might use EFS as a standby file system in the cloud, ready to take over if your primary on-site system fails. Hybrid cloud setups combine on-premises and AWS resources. When you need extra computing power, such as for machine learning or rapid data analysis, you can migrate data to AWS, process it, and then return results to your data center. AWS Data Sync is a managed service designed to simplify and automate data transfers. To understand its architecture, let's break down how it works in two common scenarios: moving data from on-premises storage to AWS and transferring data between AWS storage services. When migrating data from your own storage environment to AWS, three main components are involved: the agent, locations, and tasks. The agent is a virtual machine installed on your infrastructure, compatible with VMware ESXi, KVM, or Microsoft Hyper-V. It reads and writes data to your storage. Locations define the source and destination endpoints, such as network file systems or Amazon S3. Tasks specify what data to move, how to move it, and any filters or verification checks. Transferring data between AWS services like Amazon S3 to Amazon Elastic File System, or EFS, does not require the agent. You still define source and destination locations and configure a task, but the process is fully managed within AWS. Data sync only copies storage data, not permissions or settings. You can enable logging with Amazon CloudWatch logs to monitor transfers and troubleshoot errors, ensuring secure, encrypted data movement every time. Networking. Let's break down what a virtual private cloud, or VPC, really is. Imagine the Amazon Web Services, or AWS cloud, as a massive digital space. Inside this space, your VPC is your own private, isolated section. When you create a VPC, only your AWS account can access it. No one else, not even other AWS customers, can see or interact with your VPC. There are millions of VPCs worldwide, but each one is completely separate. This isolation is key to keeping your resources secure. So, what do you actually do with the VPC? It's where you deploy resources like compute power, storage, databases, and networking tools. This setup lets you build and run your own solutions in the cloud, all within your secure environment. Setting up a VPC is straightforward. You give it a name and define an IP address range using something called a classless interdomain routing block, or CIDR block. By default, you can create up to 5 VPCs per region in your AWS account. In summary, a VPC is your secure, private slice of the AWS cloud, perfect for deploying resources safely. Next, we'll explore how to segment your VPC for even more flexibility. Let's break down virtual private clouds, or VPCs, and subnets in Amazon Web Services. Understanding these concepts is key to building secure, scalable, and resilient cloud infrastructure. A VPC is your own isolated network within AWS. When you create a VPC, you assign it a CIDR block, which defines its range of IP addresses. Subnets are segments within your VPC, each with their own CIDR block that fits inside the VPC's range. Subnets help organize resources and improve management. Subnets can be public or private. Public subnets connect to the internet through an internet gateway and a special route in their route table. Private subnets, like those for databases, have no route to the internet gateway and are isolated by default. Every subnet starts private until you add internet access. For high availability, spread your subnets across multiple AWS availability zones. This way, if one zone fails, your resources in other zones keep running ensuring your services stay online and resilient. Each subnet reserves 5 IP addresses for networking and AWS functions. For example, in a subnet with 256 addresses, only 251 are usable for your resources. This ensures smooth network operations within your VPC. Security is crucial in Amazon Web Services, or AWS, especially when managing your virtual private cloud. One key component is the Network Access Control List, or NACL. NACLs act as virtual firewalls at the subnet level, controlling both incoming and outgoing traffic. Each subnet in your virtual private cloud automatically gets an NACL. By default, these lists allow all traffic, but for better security, you should configure them to only permit the traffic you want. NACLs use rules based on protocol, port range, source or destination, and an action to allow or deny. For example, a public subnet hosting web servers might have inbound rules allowing HTTP on port 80 and HTTPS on port 443 from any source. Any other traffic is denied by a default rule, ensuring only web traffic reaches your servers. It is important to remember that NACLs are stateless. This means you must explicitly allow both request and response traffic in your rules, as NACLs do not automatically track connections. In contrast, security groups in AWS control traffic at the instance level, not the subnet level. They provide another layer of security working alongside NACLs to protect your resources. Let us break down the difference between security groups and Network Access Control Lists, or NACLs, in cloud security. Both filter traffic, but they operate at different layers and serve unique purposes. NACLs, or Network Access Control Lists, work at the subnet level. Imagine 3 private subnets, each with its own IP address range. A single NACL can be associated with all 3, controlling which types of traffic are allowed in or out of the subnet. Security groups, on the other hand, operate at the instance level. For example, you might have a security group attached to your database instances. These groups specify which sources can access specific ports, like allowing only MySQL or Aurora traffic from a certain subnet. When a request is made, it first passes through the NACL at the subnet boundary. If allowed, it then reaches the security group attached to the instance. Only if both layers permit the traffic does it reach its destination. Otherwise, it is blocked. NACLs are stateless, meaning you must set rules for both inbound and outbound traffic. Security groups are stateful, so return traffic is automatically allowed. This layered approach enhances your cloud security. Let us break down the role of a NAT gateway in a virtual private cloud, or VPC. Imagine your VPC has 2 subnets, one public and one private. The private subnet is where your application servers, like EC2 instances, live. These servers need updates, but they cannot access the internet directly. To solve this, you place a NAT gateway in the public subnet. NAT stands for Network Address Translation. The NAT gateway gets a public IP address, called an elastic IP address, and connects to the internet through the Internet Gateway. You then update the private subnet's route table to send outbound internet requests to the NAT gateway. This way, your private EC2 instances can download updates or patches from the internet, but they remain hidden from direct inbound internet traffic. The NAT gateway only allows outbound connections from within your VPC. It blocks any inbound connections initiated from the internet, keeping your private subnet secure. AWS manages the NAT gateway for you, making setup simple and ensuring high availability. In short, a NAT gateway lets private subnets access the internet securely, while blocking unsolicited inbound traffic, helping you keep your EC2 instances updated and protected. Let us explore how to create private subnets with IPv6 using an egress-only internet gateway to maintain privacy while allowing outbound connectivity. Traditionally, with Internet Protocol version 4, or IPv4, private subnets are isolated from direct internet access. Resources in these subnets use a network address translation, or NAT, gateway to reach the internet. This setup ensures that connections can only be initiated from within the private subnet, and responses from the internet are allowed back in. However, unsolicited inbound connections from the internet are blocked, keeping the subnet private. With Internet Protocol version 6, or IPv6, every address is globally unique and publicly addressable. This presents a challenge. How do you keep an IPv6 instance private if all addresses are reachable from the internet? Simply placing an instance in a private subnet is not enough, since IPv6 does not use NAT in the same way as IPv4. To solve this, you use an egress-only internet gateway. This gateway allows outbound IPv6 traffic from your private subnet to the internet, but blocks any inbound connections initiated from the internet, preserving privacy for your resources. Remember to update your route tables, security groups, and network access control lists to ensure your IPv6 private subnet remains secure and functions as intended. A virtual private network, or VPN, is a secure way to connect two remote networks over the internet. In Amazon Web Services, or AWS, VPNs help link your virtual private cloud, or VPC, to your on-premise data center. Imagine your VPC in AWS and your data center, each with its own private network. You want resources in both locations to communicate securely. A VPN connection lets you do this, even if your VPC subnet is isolated from the internet. On the AWS side, you create a virtual private gateway and attach it to your VPC. In your data center, you set up a customer gateway, which can be hardware or software. These gateways form the endpoints of your VPN tunnel. You update your route tables so AWS resources know how to reach your data center. Security groups must allow the right protocols, like SSH or remote desktop, from your data center's network to your AWS instances. Direct Connect is another way to link your data center to AWS, but it does not use the internet. Instead, it uses dedicated private infrastructure for a more secure and reliable connection. Your data center connects to a Direct Connect location, which bridges to AWS. This setup allows access to both private VPC resources and public AWS services, all without traversing the public internet. Direct Connect offers speeds up to 10 gigabits per second. Virtual Private Cloud Peering, or VPC peering, is a way to connect two VPCs so their resources can communicate securely. Unlike VPN connectivity or Direct Connect, which link your on-premises network to a VPC, VPC peering connects VPCs directly. Each VPC might contain resources like EC2 instances or databases. With VPC peering, these resources can talk to each other, even if the VPCs are in different regions. The peering connection itself is hosted on Amazon Web Services infrastructure, making it highly resilient with no single point of failure or bandwidth bottleneck. VPC peering is always a one-to-one connection. If you have 3 VPCs, each pair that needs to communicate must have its own peering connection. Also, VPCs cannot have overlapping IP address ranges. For example, if both VPCs use 10.0.0.0/16, pairing is not possible. To set up peering, the owner of one VPC sends a request to another. If accepted, both VPCs update their route tables to allow traffic between them, ensuring their CIDR blocks do not overlap. Finally, update your security groups to permit the right resources, ports, and protocols. That's VPC pairing, a simple, resilient way to connect VPCs for secure communication. Navigating networking in Amazon Web Services, or AWS, can be complex. From route tables to CIDR blocks, connecting virtual private clouds, or VPCs, is essential for building secure cloud environments. While VPC peering and VPN connections are common, managing dozens or hundreds of connections quickly becomes overwhelming. Each new VPC or on-premises network adds complexity, making traditional methods hard to scale and maintain. Enter AWS Transit Gateway, Amazon's managed network transit hub. It acts as a regional router, allowing you to interconnect hundreds of VPCs and on-premises networks without the hassle of maintaining countless peering or VPN connections. Transit Gateway uses attachments to connect VPCs, VPNs, and direct connect gateways. Each attachment serves as a source and destination for traffic. Route tables within the Transit Gateway direct packets based on destination IP addresses, enabling flexible and secure network topologies. Transit Gateway scales automatically, supports multiple route tables, and simplifies adding new networks. However, there are limits: 5 transit gateways per region, 5 attachments per VPC, and bandwidth caps. Still, it's a powerful solution for complex AWS networking needs. Elastic IP addresses, or EIPs, are a key part of managing network infrastructure in Amazon Web Services, or AWS. While public IP addresses can be assigned to instances, they are not persistent and will change if the instance is stopped or terminated. An elastic IP address is a persistent public IPv4 address that you can allocate to your AWS account. Unlike standard public IP addresses, an EIP remains associated with your account until you choose to release it. This means you can attach it to any instance or Elastic Network Interface, or ENI, as needed. If you associate an EIP with an instance, it replaces any existing public IP address. The EIP will remain with the instance even if you stop and start it, ensuring continuity. However, if an EIP is not attached to a running instance, AWS will charge you for it. Always release unused EIPs to avoid unnecessary costs. In practice, associating an EIP is simple. Allocate the address, attach it to your instance, and it instantly replaces the previous public IP. Disassociating and releasing the EIP is just as straightforward. Elastic IP addresses provide persistence and flexibility, but remember to manage them wisely to avoid extra charges. Elastic Network Interfaces, or ENIs, are virtual network cards you can create and manage within your virtual private cloud, or VPC. ENIs let you add flexible networking options to your Amazon EC2 instances, making your cloud environment more adaptable. Every EC2 instance starts with a primary network interface called ETH0, which cannot be removed. However, sometimes you need more than one interface. For example, you might want to separate management traffic from production traffic by adding a secondary ENI. To do this, you can create a new ENI in the AWS Management Console. Assign it to a different subnet, like a management subnet, and attach it to your instance. The ENI's configuration, such as its IP address and security group, keeps its configuration even if you detach and reattach it to another instance. Detaching or deleting an ENI is simple. Just select the interface, choose Detach, confirm, and then delete if it is no longer needed. The ENI's configuration always stays with it. ENIs provide flexibility for your networking needs. Remember, the number of ENIs you can attach depends on your EC2 instance type. Check AWS documentation for details. If you want to boost your Amazon EC2 instance's network performance, enabling enhanced networking with the Elastic Network Adapter, or ENA, is the way to go. Let's explore how ENA can help your workloads. The Elastic Network Adapter is a custom network interface designed to optimize network speeds for EC2 instances. With ENA, you can achieve network speeds of up to 100 gigabits per second for supported Linux compute instances. Enhanced networking also delivers higher bandwidth, increased packets per second performance, and best of all, it comes at no extra cost. To use ENA, your instance must be one of the supported types and run a compatible Linux kernel version, such as 2.6.32 or 3.2 and above. If you launch an instance using Amazon Linux 2 or the latest Amazon Linux AMI on a supported instance type, enhanced networking is enabled by default. For the most current list of supported EC2 types, check the AWS documentation. To confirm ENA is active, ensure the ENA module is installed and the ENA support attribute is set. Run modinfo ENA in your terminal and use the AWS command line interface to check ENA support. With ENA, your EC2 instances can reach new levels of network performance simply and efficiently. VPC endpoints let you privately access Amazon Web Services or AWS services using the AWS internal network instead of the public internet. This means you do not need to set up an internet gateway, NAT gateway, virtual private network, or direct connect. There are two types of VPC endpoints: interface endpoints and gateway endpoints. Each type connects your virtual private cloud, or VPC, to AWS services in a different way, providing flexibility and security for your cloud resources. Interface endpoints are elastic network interfaces, or ENIs, placed within your subnet. They use private link to create secure private connections between your VPC, AWS services, and even on-premises applications. Communication must start from your VPC, not the service. Gateway endpoints are targets in your route tables, allowing access to supported services like Amazon S3 and DynamoDB. When you create a gateway endpoint, selected route tables are automatically updated to route traffic through the endpoint. Gateway endpoints only support IPv4. When you create an interface endpoint, AWS automatically creates a private DNS hostname in your VPC. Applications using the default DNS name will seamlessly connect through the internal AWS network with no need for reconfiguration. Everything stays private and secure. Let's spotlight a powerful tool in your Amazon Web Services toolbox, the VPC Reachability Analyzer. Whether you are new to cloud computing or an experienced user, this feature can save you time and frustration. In the past, diagnosing connectivity issues in Amazon Web Services could be overwhelming. Forgetting a security group rule or missing an internet gateway often left users stuck searching for answers. The VPC Reachability Analyzer changes that by making network troubleshooting much simpler. The VPC Reachability Analyzer tests connectivity between 2 points in your architecture. It checks each network component along the path, from security groups and elastic network interfaces to network access control lists. At the end, it provides a detailed report highlighting any issues it finds. For example, if you want to check connectivity between two instances, just select them, Choose your protocol like TCP or UDP and run the analysis. If there's a problem, the tool points out exactly where the connection fails, such as missing inbound rules. This tool supports many endpoints, including VPN gateways and VPC peering connections. For just 10 cents per run, it's a smart way to keep your cloud network running smoothly. Troubleshooting connectivity between Amazon EC2 instances can get complicated as your network grows. Today, let's see how to quickly diagnose connection issues between two instances in the same virtual private cloud, or VPC, using the VPC Reachability Analyzer. First, identify your source and destination instances. For this example, we'll test connectivity from Instance 1 to Instance 3, both inside VPC 1. Open the VPC Reachability Analyzer, create a new analysis, and select Instance 1 as the source and Instance 3 as the destination. Since we want to test Secure Shell or SSH connectivity, set the port to 22 for both source and destination. Start the analysis. In just a few seconds, the tool will show whether the connection is possible. If the result says not reachable, click the Analysis ID to view details. The tool displays a network path diagram. In this case, it highlights that none of the security group ingress rules allow the traffic, blocking the connection. Edit the security group for Instance 3 to add an inbound rule for SSH. Save the changes, then rerun the analysis. This time, the result shows reachable, confirming the issue is resolved. That's how you troubleshoot EC2 connectivity with VPC Reachability Analyzer. Let us explore how the VPC Reachability Analyzer can help troubleshoot connectivity issues between two virtual private clouds, or VPCs, in Amazon Web Services. This tool is essential for diagnosing routing problems, especially when using VPC peering connections. Imagine you have two VPCs, VPC1 and VPC2, connected by an active peering connection. You want to test if an instance in VPC2 can reach a web server running on port 80 in VPC1. Using the Reachability Analyzer, you set the source as VPC2 Instance 1 and the destination as VPC1 Instance 2. After running the analysis, you receive a not reachable error. Investigating further, you discover the route table in VPC2 does not have a route to the peering connection. The analyzer highlights this issue, showing the traffic path and pinpointing the missing route as the problem. To resolve this, you add the correct routes in both VPC's route tables, ensuring traffic can flow in both directions through the peering connection. Rerunning the analysis and conclusion. Rerunning the analyzer now shows the connection is reachable. The VPC Reachability Analyzer quickly identifies and helps fix network issues, saving valuable troubleshooting time. AWS Resource Access Manager, or RAM, is a powerful tool that lets you share a wide range of AWS resources from centralized accounts. With RAM, you can share resources like Aurora database clusters, dedicated hosts, resource groups, and especially virtual private cloud subnets. To get started with RAM, the first step is to enable sharing. You can do this through the Resource Access Manager console or by using the AWS command line interface. Once sharing is enabled, you create a resource share. This involves naming your share and selecting the resources you want to share. For example, you might create a share called DevTeam1 and include 3 subnets from the same virtual private cloud. Next, you assign permissions to your resource share. These permissions control what actions other users, called principals, can perform on the shared resources. If you choose to share with an organizational unit, or OU, All AWS accounts in that unit, including any added in the future, will have access. Finally, complete the wizard. The shared resources, such as the 3 subnets, will quickly appear in the virtual private cloud console of the selected AWS accounts, making collaboration seamless and efficient. AWS Global Accelerator is a global service designed to speed up and secure your application traffic. By leveraging the AWS global infrastructure, it routes user requests more reliably than the public internet, reducing latency and improving security for both UDP and TCP traffic. When you set up AWS Global Accelerator, you receive 2 static Internet Protocol version 4 or IPv4 addresses linked to a domain name system or DNS name. These addresses act as fixed entry points for your users, directing traffic to your application endpoints, which can be load balancers, EC2 instances, or elastic IP addresses. The accelerator intelligently routes requests through the optimal AWS edge locations, ensuring low latency and high availability. To configure AWS Global Accelerator, start by creating an accelerator and choosing your IP addresses. Next, add listeners to specify protocols and ports. Then create endpoint groups for each region. You can set traffic dials to control distribution and configure health checks to monitor endpoint health. Finally, register your application endpoints and assign traffic weights as needed. With AWS Global Accelerator, you can easily add or change endpoints across regions without updating DNS or static IP addresses, making it simple to scale and maintain high availability for your applications. Amazon Route 53 is a powerful global service from Amazon Web Services, or AWS, designed to help you register and manage domain names. It goes far beyond basic domain registration, offering robust tools for worldwide domain management. With Route 53, you can register domain names and manage the domain name system, or DNS, for your resources. The service routes internet traffic to your domain's resources and checks their availability using health checks. Route 53 leverages AWS's global infrastructure, using edge locations for high availability and redundancy. In fact, AWS offers a 100% available service level agreement for Route 53 thanks to its distributed DNS system. Route 53 lets you define how internet traffic is routed to your resources using various routing policies, such as failover and latency routing. The traffic flow feature enables you to create complex routing configurations by combining multiple policies for optimal performance. Route 53's application recovery controller manages failovers with integrated health checks. The Route 53 Resolver service connects DNS queries between your virtual private clouds and data centers, while the Resolver DNS firewall protects DNS queries within your VPC. Route 53 is ideal for architects, developers, system operators, and administrators seeking advanced domain management on AWS. It also supports certification exam objectives for AWS Solutions Architect and SysOps Administrator roles. Amazon Route 53 is the domain name management service from Amazon Web Services, or AWS. It acts like the Internet's phone book, translating easy-to-remember domain names into the numerical IP addresses that computers use to communicate. When you register a domain with Route 53, it becomes the authoritative domain name system, or DNS, server for your domain. Route 53 creates a public hosted zone for internet traffic, and you can also set up private hosted zones for internal networks called virtual private clouds, or VPCs. Each hosted zone includes essential records, 4 name server or NS records, and 1 start of authority or SOA record. NS records identify the DNS servers for your domain, while the SOA record defines the authoritative DNS server for your DNS zone. Route 53 supports standard DNS records, A records for IPv4 addresses, AAAA records for IPv6, MX records for email servers, TXT records for text information, and CNAME records to map one host name to another. Unique to Route 53, alias records let you map custom domain names directly to AWS resources, like CloudFront distributions, Amazon S3 buckets, or Elastic load balancers. When creating records, you set the name, type, value, time to live, and routing policy, which controls how DNS queries are answered. Amazon Route 53 health checks are powerful tools that help ensure your applications remain available and reliable. These independent resources work with most routing policies, allowing you to monitor the health of your endpoints and respond quickly to issues. When you set up a health check, Route 53 sends requests to your endpoint every 30 seconds. Based on the responses, Route 53 determines if the endpoint is healthy or unhealthy. This information guides how Route 53 answers DNS queries, always favoring healthy endpoints and ignoring those marked as unhealthy. You can configure health checks for different tiers of your application, verifying each layer before considering the entire application healthy. Route 53 adds up the number of healthy checks and compares it to a threshold you set. Health checks can target IP addresses or domain names using TCP, HTTP, or HTTPS protocols. For HTTP-based checks, you can even specify a string that must appear in the response body. Route 53 health checks can monitor the state of an Amazon CloudWatch alarm. The health status updates automatically based on the alarm's state, offering flexible options for handling insufficient data. Health checks are performed globally, and you can customize which regions are used. You can also choose to receive notifications whenever a health check fails, keeping you informed at all times. DMS routing policies determine how queries are answered. The simple routing policy links a domain name to one or more IP addresses, randomly selecting which to use. However, it does not support health checks. Weighted routing is similar, but lets you assign a numerical weight to each IP address, favoring some over others. A weight of 0 means a record is never returned. Weighted routing supports health checks, ensuring only healthy records are chosen. Geolocation routing tags records by location, such as country or continent, and returns the IP address best suited for the user's region. This helps serve customers in different languages or regions and can enforce licensing restrictions. Geoproximity routing, which requires Route 53's traffic flow feature, routes traffic based on distance and a bias value, allowing you to shift more or less traffic to specific endpoints by adjusting the bias. Failover routing directs traffic to a primary resource, but if a health check fails, it automatically redirects to a secondary resource. Latency routing chooses the record with the lowest latency for the user based on AWS's latency database, ensuring faster connections. Multi-value answer routing returns up to 8 healthy IP addresses for a single query, improving reliability. Each DNS routing policy offers unique ways to manage traffic, optimize performance, and ensure users reach healthy, responsive resources. Managing records in large, complex configurations can be challenging, especially when you have a group of resources like a fleet of web servers all serving the same domain. Traffic Flow is designed to simplify this process, making record creation and maintenance much easier. With the Traffic Flow visual editor, you can build complex sets of records and instantly see how they relate to each other. This tool allows you to combine multiple routing policies and health checks within a single configuration known as a traffic policy. Each traffic policy is automatically versioned, so you never have to start from scratch when making changes. Previous versions remain available until you choose to delete them, giving you flexibility and control over your configurations. A single traffic policy can define hundreds of records, and Traffic Flow generates all of them automatically when you create a policy record. You associate these policy records with domain or subdomain name records, and they appear in your hosted zone's record list. The same traffic policy can be reused across multiple public hosted zones, which is especially helpful when managing the same hosts for several domains. It is important to note that the geoproximity routing policy is only available if you use traffic flow, adding another layer of advanced routing options for your configurations. Amazon Route 53 Resolver is the Domain Name System, or DNS, service designed for your virtual private clouds, or VPCs, in AWS. It seamlessly integrates with your on-premises data center, making DNS management across environments straightforward and secure. To connect your data center's DNS with AWS, you need either a direct connect, often called DX, or a virtual private network, or VPN, connection. Once connected, you configure endpoints by assigning IP addresses in each subnet that requires Route 53 Resolver access. Route 53 Resolver manages both inbound and outbound DNS queries. Inbound queries let your data center resolve domains hosted in AWS. For outbound queries, you set up conditional forwarding rules. These rules specify which domains, hosted in your data center, should be forwarded from AWS. This setup ensures that DNS queries between your VPCs and your data center are handled efficiently and securely. The Route 53 Resolver DNS Firewall is a managed service that inspects and filters DNS queries originating from your VPCs. You define firewall rule groups listing domains to monitor and actions to take. You can allow, alert, or block queries and apply these rules to protect your VPC's outgoing DNS traffic. Amazon Route 53 Application Recovery Controller is designed to help you keep your applications resilient. It continuously monitors your application's ability to recover from failures and manages recovery across multiple availability zones, regions, and even your own data centers. With Route 53 Application Recovery Controller, you can define readiness checks to monitor AWS resource configurations, capacity, and network routing policies. These checks cover resources like auto-scaling groups, Amazon EC2 instances, Amazon Elastic Block Store volumes, Elastic Load Balancers, Amazon Relational Database Service instances, and DynamoDB tables. Readiness checks ensure your recovery environment is always prepared to take over when needed, verifying that capacity and scaling setups are consistent across regions before any failover. Readiness checks work alongside routing controls, which let you fail over an entire application based on custom conditions such as application metrics, partial failures, increased error rates, or latency. You can also initiate failover manually. Routing controls allow you to shift traffic for maintenance or during real failure scenarios, and safety rules help prevent failover to unprepared replicas. A control panel groups routing controls for your application, letting you turn traffic flow on or off to specific regions or availability zones. This enables custom traffic redirection during failover or maintenance. With fine-grained failover and verification, Amazon Route 53 Application Recovery Controller supports applications that demand very high availability. Amazon CloudFront is a content delivery network from Amazon Web Services, or AWS, designed to deliver your website's content to users worldwide with low latency and high speed. Its main role is caching content closer to your users. CloudFront uses a global network of edge locations to cache both static and dynamic content. For example, static files in Amazon Simple Storage Service, or S3, and dynamic content from Amazon Elastic Compute Cloud, or AC2, or Lambda functions, are distributed efficiently. To use CloudFront, you create a distribution and select your content's origin, such as an S3 bucket or an application load balancer. You can customize protocols, cache settings, price classes, and even use your own domain name with a digital certificate. CloudFront uses 3 caching layers: edge locations, regional edge caches, and AWS Origin Shield. This multi-layered approach improves cache hit ratios, reduces load on your origin servers, and enhances network performance by keeping content closer to users. CloudFront offers robust security, including encrypted solid-state drives, signed URLs, AWS Web Application Firewall or WAF, geo-restrictions, and integration with AWS Identity and Access Management. Monitoring is available through Amazon CloudWatch, AWS CloudTrail, and real-time logs. CloudFront is Amazon Web Services Content Delivery Network, or CDN, designed to cache and secure your content for faster, safer access worldwide. Let's look at 2 common patterns for using CloudFront to boost performance and security. First, you can set up CloudFront with an application load balancer as the origin. This means CloudFront sits in front of your website, caching content and protecting your backend. To secure access, configure CloudFront to add a custom HTTP header to each request. Then, set your load balancer to only forward requests containing this header, returning a 403 error for others. Rotate your custom header regularly to maintain security. Update your Route 53 DNS records so your website's friendly name points to CloudFront, not directly to the load balancer. Second, use CloudFront with an Amazon S3 bucket for static website hosting. CloudFront caches content globally, reducing latency. To secure access, create an Origin Access Identity, or OAI, and update your S3 bucket policy so only CloudFront can retrieve content. Use AWS Certificate Manager, or ACM, to enable HTTPS, ensuring secure delivery. With CloudFront, you can cache content closer to users and secure your backend, whether you use an application load balancer or S3. Databases. Amazon Relational Database Service, or RDS, is a managed service from Amazon Web Services that makes it easy to set up, operate, and scale a relational database in the cloud. AWS handles routine tasks like backups and patching for you. With Amazon RDS, you can choose from several popular database engines, including MySQL, MariaDB, PostgreSQL, Amazon Aurora, Oracle, and Microsoft SQL Server. You also select the compute instance type and size, tailoring performance to your workload's needs. For high availability, RDS offers multi-availability zone or multi-AZ deployments. This feature automatically creates a standby database in another availability zone, providing failover protection if your primary instance becomes unavailable. RDS supports storage autoscaling, so your database storage can grow automatically as needed. Most engines use Elastic Block Storage, or EBS, for storage, while Aurora uses a shared cluster storage architecture that scales seamlessly as your data grows. Automatic backups are enabled by default, storing data in Amazon's Simple Storage Service, or S3. You can set retention periods and use the Key Management Service, or KMS, for encryption. Manual snapshots and Aurora's backtrack feature offer additional recovery options. To create an Amazon Relational Database Service, or RDS, database on Amazon Web Services, start at the AWS Management Console. Head to the Database category and select RDS, which brings you to the Amazon RDS dashboard. Click Create Database to begin. Choose to create a new database, then select the standard Create method for more configuration options. Pick your database engine, such as MySQL, and select your preferred version. For a full feature set, select the production template. Enter a database instance identifier, set your master username, and choose or create a password. Next, pick your instance size from standard classes, selecting the smallest if you want to minimize resources. For storage, general purpose is a good default, and you can enable auto-scaling to allow storage to grow as needed. Select your virtual private cloud or VPC and decide if your database should be publicly accessible. For private databases, only resources inside the VPC can connect. Assign a security group to control access. Configure backup retention, enable encryption with the AWS Key Management Service, and set up monitoring. Choose a maintenance window and enable deletion protection to prevent accidental loss. Review your settings, then click Create Database. Your RDS instance will launch in just a few minutes. Amazon RDS Proxy is a managed service from Amazon Web Services that acts as a middle layer between your application and your database. It is especially useful for serverless applications, which often create and close many database connections rapidly. In serverless environments, like those using multiple Lambda functions for create, read, update, and delete operations, each function may open its own database connection. This can quickly overwhelm your database, consuming excessive CPU and memory and slowing down your application's response times. RDS Proxy helps by pooling and managing these connections, reducing the load on your database and improving performance. As a managed service, it handles installation, patching, scaling, and maintenance for you. It also boosts security by allowing you to enforce the use of identity and access management credentials and integrate with AWS Secrets Manager, so you do not need to hard-code credentials. Additionally, RDS Proxy increases application availability by automatically rerouting connections if your database fails or switches instances. RDS Proxy is ideal for unpredictable workloads, applications that frequently open and close connections, and those that keep idle connections open for quick responses. Overall, Amazon RDS Proxy streamlines connection management, enhances security, and keeps your applications running smoothly. Multi-AZ, an Amazon Relational Database Service, or RDS, stands for Multi-Availability Zone. This feature is all about resiliency and business continuity, ensuring your database remains available even if something goes wrong in one zone. When you enable Multi-AZ, Amazon RDS automatically creates a secondary database instance, called a replica, in a different availability zone within the same region. This replica is not for handling read-only traffic. Its sole purpose is to provide a failover option if the primary instance fails. If an outage or maintenance affects the primary instance, Amazon Web Services, or AWS, automatically switches to the replica. The domain name system, or DNS, record is updated, and this process usually takes between 60 and 120 seconds, depending on database size and activity. For SQL Server, Multi-AZ uses SQL Server mirroring, which also provides automatic failover, but requires specific configuration. Amazon Aurora, on the other hand, is fault-tolerant by default, but enabling Multi-AZ reduces failover time dramatically, promoting a replica instantly if the primary fails. When failover occurs, RDS triggers an event called RDS Event 025. You can set up notifications via short message service, or SMS, or simple notification service, or SNS, to stay informed and maintain high availability for your applications. Amazon Relational Database Service, or RDS, offers read replicas to help scale your database's read performance. Unlike Multi-Availability Zone, or MAZ deployments, read replicas are not designed for failover or resiliency. Instead, they serve read-only queries from a separate instance. When your primary RDS instance is overwhelmed by read-heavy traffic, you can create a read replica. A snapshot of your database is taken, and a secure asynchronous link is established between the primary and the replica. This allows applications and users to direct read-only queries to the replica, easing the load on the primary database. Read replicas are available for MySQL, MariaDB, and PostgreSQL engines. You can deploy up to 5 read replicas per source database and even place them in different regions for disaster recovery. With MySQL and MariaDB, you can nest replicas up to 4 layers deep, but this is not possible with PostgreSQL. MySQL requires version 5.6 or later and InnoDB storage. MariaDB supports any version. Monitor synchronization using the Amazon RDS replica lag metric in Amazon CloudWatch to ensure your replicas stay up to date. Restoring a database from an existing backup in Amazon Relational Database Service, or RDS, is a straightforward process, whether you are using automatic backups or manual snapshots. With automatic backups enabled, RDS saves transaction logs to Amazon Simple Storage Service, or S3, every 5 minutes. This means you can restore your database to a specific point in time, but only up to the latest restore time available. For example, if the latest restore time is 1500, you cannot restore to 1502 until the next backup cycle completes. Manual snapshots work differently. When you restore from a manual snapshot, you can only restore to the exact time the snapshot was taken. During the restore, you can change storage types, such as switching from general-purpose SSD to provisioned IOPS, but this may increase restore time. You can also adjust instance size, parameter groups, and security groups, though AWS recommends keeping these settings the same as the snapshot. To restore, select your snapshot in the RDS dashboard, choose Restore Snapshot, and configure your new instance. You can set a new identifier, select a virtual private cloud, adjust storage, and choose availability options. Click Restore Database Instance to begin. Once complete, your new database instance is available, making restoration from backups both quick and flexible. Managing backups for your Amazon Relational Database Service, or RDS, is crucial for protecting your data. But after creating a snapshot, what should you do next to ensure your data is safe and accessible? You can copy RDS snapshots within the same region or to a different Amazon Web Services, or AWS, region. This is useful for disaster recovery or running databases in new locations. Remember, copying an automated snapshot turns it into a manual snapshot. Also, when copying to another region, option and parameter group settings are not transferred, so you will need to recreate them. Amazon RDS Performance Insights is a feature designed to help users understand what is happening inside their databases, no matter their level of database management experience. Traditionally, Amazon CloudWatch was used for monitoring RDS databases. CloudWatch collects metrics from the hypervisor layer, offering between 15 and 18 metrics depending on the database engine. However, these metrics are limited and focus on the instance, not the database engine itself. Enhanced monitoring improved on this by using a lightweight agent to collect over 50 metrics directly from the operating system, even showing processes and threads like the Linux top command. Still, both tools focus on the instance, not the actual database workload. Enhanced monitoring can collect data as frequently as once per second, providing more granular insights than CloudWatch. Yet, it still leaves users piecing together clues from multiple graphs, trying to determine the root cause of performance issues. Performance Insights changes the game by collecting metrics directly from the database engine. Its dashboard in the RDS console visualizes database load, filtering by SQL, user, host, and wait. This condenses complex data into a single actionable metric. With Performance Insights, users no longer play detective. Instead, they get clear, focused insights, making it easier to identify and resolve database performance issues. Amazon RDS Performance Insights helps you understand your database's workload without adding significant overhead. It samples connection data from memory every second, tracking whether each connection is active or idle, and impacts performance by less than 1% of CPU load. Performance Insights collects details about each active connection, including the SQL query, its state, the originating host, and the user. This information is condensed into a single metric called Average Active Sessions, or AAS, which measures database load over time. The Performance Insights dashboard features a load chart displaying recent database load in AAS units, color-coded by weight type. Below, the top activity table highlights the SQL statements, weights, hosts, or users contributing most to the load, ordered by impact. Sampling every second means some fast queries are missed, but this actually reduces noise in the data. Like frames in a video, these samples create a seamless visualization of database activity, balancing clarity with minimal resource use. AAS is calculated by averaging active connections per minute. Regardless of query length or user count, the load chart visualizes overall activity, helping you pinpoint performance bottlenecks and optimize your Amazon RDS database. Active Average Session, or AAS, is a key metric used by Performance Insights to reveal the load on an Amazon Relational Database Service instance. AAS measures session activity, which usually means access to the Central Processing Unit, or CPU. Performance Insights uses color-coded graphs to show what is happening inside your database. Green means a query is using the CPU. Blue shows the query is waiting for disk input or output. Orange highlights when a query is waiting for a database resource, like a lock or buffer. The default graph displays an hour of activity, divided into 1-minute segments. Each segment shows the average active session state for that minute. This makes it easy to spot trends, like constant CPU load or frequent waits for disk or resources. If AAS is near zero, the database is idle. If it is less than the number of CPU cores, the instance is not blocked. But if AAS exceeds the number of CPU cores, sessions must wait, signaling a potential bottleneck. Monitoring AAS helps you understand database performance, spot issues like CPU saturation or disk waits, and make informed decisions about scaling or tuning your database for optimal efficiency. Amazon RDS Performance Insights is a powerful tool for monitoring your database performance. It helps you quickly determine if your database is under load, saving you from unnecessary troubleshooting of application software or network connections. When users report slow performance, Performance Insights shows if the database is the culprit. If the average active sessions, or AAS, is less than 1, the database is not blocked. If AAS exceeds the number of available CPU cores, the database is overloaded, confirming the issue is with the database itself. Performance Insights also helps right-size your RDS instance. If AAS is consistently lower than your CPU core count, your instance may be too large. If AAS is higher, your instance could be too small. Monitoring I/O-based weights can also highlight storage issues. You can access Performance Insights from the Amazon RDS Management Console, either through the menu or the Current Activity column, which visually indicates database load and capacity. Performance Insights data is published to Amazon CloudWatch, where you can set alarms and monitor metrics like DB load CPU, and DB load non-CPU for deeper insights. For advanced users, Performance Insights data is available via a public API and the AWS command line interface, enabling custom dashboards and automated monitoring solutions. Aurora Serverless version 2 is designed to make database management easier by automatically scaling your database instance capacity as your workload changes. This means you only pay for the resources you actually use, eliminating the need for complex capacity planning. Aurora Serverless v2 adjusts your database's capacity by increasing or decreasing Aurora capacity units, or ACUs. The number of ACUs determines how much memory, CPU, and networking your database has. Currently, Aurora Serverless v2 can scale between 0 and 256 ACUs, ensuring your database can handle anything from minimal to heavy workloads. You can set minimum and maximum capacity limits to control your costs. One ACU provides about 2 gigabytes of memory, along with matching CPU and networking resources. If you set your minimum capacity to 0 ACUs, your database can scale down during periods of inactivity, so you only pay for storage, not compute. When a new connection arrives after inactivity, Aurora Serverless v2 will start the database and scale up ACUs to meet demand. This process can take up to 15 seconds, making it ideal for applications that can tolerate a brief startup delay. Amazon DynamoDB is a fully managed NoSQL database from Amazon Web Services, or AWS. Unlike traditional databases that use structured query language, or SQL, DynamoDB is a key value store designed for ultra-high performance at any scale. DynamoDB is popular for gaming, web, mobile, and Internet of Things applications. It delivers single-digit millisecond latency, making it ideal for workloads that demand speed. As a fully managed service, AWS handles all the database administration, backups, and scaling, so you can focus on your application's logic. Setting up a DynamoDB table is simple. Just provide a table name and a primary key. Tables are schemaless, so each item can have different attributes. You can also add secondary indexes to query data by attributes other than the primary key. DynamoDB supports both global and local secondary indexes. You choose between provisioned and on-demand capacity modes. Provision mode lets you reserve specific read and write capacity units, while on-demand mode automatically scales with your workload. AWS charges based on your chosen throughput and storage. DynamoDB is highly available, automatically replicating data across 3 availability zones. However, it has limitations like a maximum record size of 400 kilobytes and eventual consistency for some queries. Monitoring throughput is essential to avoid performance issues. Amazon DynamoDB offers robust backup features to protect your data, similar to Amazon Relational Database Service, or RDS. Let us explore the key backup techniques DynamoDB provides to keep your tables safe and recoverable. DynamoDB supports automatic backups through point-in-time recovery. With a single click in the Amazon Web Services Management Console, you can enable or disable this feature. Once enabled, DynamoDB automatically retains continuous backups for 35 days. This means you can restore your table to any second within that period, providing a strong safety net against accidental or malicious data loss. Unlike RDS, there is no need to set backup retention periods or schedules. DynamoDB handles it all for you. For more control, DynamoDB offers on-demand manual backups. These backups are not limited by the 35-day retention period and remain until you delete them. This is especially useful for meeting compliance or governance requirements. Manual backups do not impact table performance, regardless of database size, and can be created in seconds. You can also schedule recurring backups using Amazon Web Services Backup. Enabling point-in-time recovery or creating a manual backup is simple. Just select your table, choose the backup option, and follow the prompts in the console. With DynamoDB, securing your data is straightforward and flexible, ensuring peace of mind for your database needs. Restoring your Amazon DynamoDB tables from a backup is simple, whether you are using an automatic point-in-time recovery or a manual on-demand backup. Let us walk through the process. To restore from a manual backup, start in the DynamoDB dashboard within the Amazon Web Services Management console. Select your table, then navigate to the Backup tab. Choose your manual backup, click Restore Backup, and give your new table a name, such as Manual Restore. You can decide to restore the entire table or exclude secondary indexes. You also have the option to restore within the same region or to a different region and to change the encryption type using a key management service key. Once your options are set, click Restore Table. In a few minutes, your new table will appear, fully restored. If you need to recover data lost at a specific moment, use Point-in-Time Recovery. In the Backups tab, select Restore to Point-in-Time. Enter a new table name and pick any restore time between the earliest and latest available dates. Confirm your settings and restore. Your table will be recreated as it was at that exact time. Amazon DynamoDB is a fully managed NoSQL database service from Amazon Web Services, or AWS. With DynamoDB, there is no need for database administration, server management, or backups. You simply set up your tables and configure the provision throughput, while AWS handles the rest, including replication across multiple availability zones for high availability. DynamoDB is designed for speed, delivering read and write operations in just milliseconds, regardless of table size. However, because data is replicated across zones, some queries may return older data due to eventual consistency. For most applications, this is seamless, but certain use cases may require even faster, more consistent reads. This is where DynamoDB Accelerator, or DAX, comes in. DAX is an in-memory cache that boosts DynamoDB's performance up to 10 times, reducing response times from milliseconds to microseconds. It is fully managed by AWS and integrates seamlessly with existing DynamoDB applications. DAX can handle millions of requests per second, supports clusters with up to 10 nodes, and reduces DynamoDB read capacity needs, lowering costs. It is fully compliant with DynamoDB API calls, requiring no changes to your application logic. DAX clusters reside within your virtual private cloud, or VPC, and support encryption at rest using the Advanced Encryption Standard and AWS Key Management Service. Application performance is more than just a technical concern. It directly affects your business's bottom line, influencing everything from revenue to customer loyalty and even your brand's reputation. Studies consistently show that delays in web and application performance can hurt key business metrics. For example, a 2017 study by Strangeloop found that just a 1-second delay in page load time leads to a 7% loss in conversions, 11% fewer page views, and a 16% decrease in customer satisfaction. When applications are unavailable, businesses not only lose revenue, but also risk damaging customer trust and their public image. On the other hand, improving performance pays off. Shopzilla, for instance, reduced their site load time from 6 seconds to 1.2 seconds, resulting in a 12% increase in revenue and 25% more page views. Ultimately, every second counts. Investing in application performance is investing in your business's success and customer satisfaction. Caching is a powerful technique that can dramatically improve application performance. By adding a high-speed data layer between your applications and their data stores, caching helps deliver information much faster than traditional methods like database queries or disk access. The core idea behind caching is simple: store frequently accessed datasets in memory. This allows applications to retrieve data at lightning speed, since in-memory access is at least 50 times faster than disk access. Latency drops from milliseconds to microseconds, making a noticeable difference. Implementing a caching solution brings several advantages. Not only does it boost performance, but it also enhances resiliency and scalability. Caching helps manage the size of databases and application instances, ensuring your systems can handle more users and data without slowing down. Many large-scale applications, such as social media platforms, gaming services, media sharing sites, and news outlets, rely heavily on caching. For example, Amazon Elasticache stores strategic datasets in memory, improving latency and throughput for read-heavy workloads. In high-performance computing, where massive datasets must be accessed quickly across multiple nodes, an in-memory data layer is essential. Disk-based access simply cannot keep up, making caching the only viable solution for these demanding scenarios. Amazon Elasticache is a web service designed to make deploying and operating an in-memory cache simple. It automates tasks like provisioning machines, installing software, patching, failure detection, and recovery, so you can focus on your application's performance. Elasticache creates an in-memory data layer between your applications and data stores, accelerating read operations. It integrates with services like Amazon EC2, Amazon RDS, CloudFormation, Elastic Beanstalk, and AWS OpsWorks. Monitoring metrics are sent to Amazon CloudWatch, helping you quickly evaluate and diagnose issues. Elasticache supports two key value in-memory engines, Memcached and Redis. Memcached is multi-threaded, leverages large multi-core instances, and is widely used as a caching solution without persistence. Redis, on the other hand, supports complex datasets, disk persistence, and can be deployed across multiple availability zones with automatic failover. You can scale your cache clusters by adding or removing nodes as your application needs change. Elasticache from Memcached includes auto discovery and automatic node replacement, making it easy to manage clusters even during workload spikes. Elasticache for Redis supports role-based access controls and encryption, meaning compliance standards like PCI DSS, HIPAA, and FedRAMP. This makes it suitable for applications with strict security requirements. Automation and optimization. Disaster recovery is about restoring operations quickly with minimal data loss after a catastrophic event. Disasters can range from natural events like earthquakes or floods, which may impact entire regions, to unauthorized access or accidental deletion of resources. Two key metrics in disaster recovery planning are Recovery Time Objective, or RTO, and Recovery Point Objective, or RPO. RTO is the maximum time a service can be unavailable before it causes unacceptable business damage. RPO is the maximum period in which data loss is tolerable, measuring the acceptable gap between your last backup and a service interruption. For example, if your RTO is 2 hours and an outage occurs at 9 in the morning, your service must be restored by 11. If your RPO is 8 hours and an outage happens at 3 in the afternoon, you must restore data from no earlier than 7 that morning. AWS offers several disaster recovery strategies: Backup and Restore, Pilot Light, Warm Standby, and Multi-Site Active-Active. Each method decreases RTO and RPO, but increases complexity and cost. Careful planning ensures your backup and recovery strategies meet your organization's RTO and RPO requirements, minimizing business impact during disasters. When planning for disaster recovery, two critical metrics come into play: Recovery Time Objective, or RTO, and Recovery Point Objective, or RPO. Understanding these helps ensure your business can survive unexpected disruptions. RTO is the maximum acceptable time your application can be down after a disaster. RPO is the maximum amount of data loss your business can tolerate, measured in time. Both are essential for business continuity planning and must be tailored to each application. To determine the right RTO and RPO, ask, what would happen if this application was lost? How much would downtime cost, both financially and reputationally? Are there service-level agreements or regulatory requirements? Does this application depend on others, or do others depend on it? These questions guide your disaster recovery strategy. Not all applications need the same RTO and RPO. Some require rapid recovery, which increases complexity and cost. Assess each application individually to balance resilience and budget. Consider how often your data changes. If it changes hourly, frequent backups are needed. If monthly, less frequent backups may suffice. Evaluate RTO and RPO before designing your disaster recovery strategy. Backup and restore is a recovery strategy designed for situations where quick recovery is not critical. It is best suited for deployments with low business risk if services are offline for a while. This approach typically results in the longest recovery time objective, or RTO, and recovery point objective, or RPO. Usually, RTO is under 24 hours, and RPO is measured in hours, making it less ideal for mission-critical systems. Amazon Web Services, or AWS, offers several tools to support this strategy. AWS Backup acts as a central hub, managing backups across services like Amazon Elastic Compute Cloud, or EC2, Amazon Relational Database Service, or RDS, Amazon DynamoDB, and Amazon. It provides scheduling, lifecycle rules, and centralized monitoring. If an availability zone fails, you can restore EC2 instances, EBS volumes, and RDS databases using snapshots and backups stored in Amazon Simple Storage Service, or S3. For regional outages, cross-region replication and AWS Data Lifecycle Manager automate backup copies, enabling recovery in a different region. Backup and restore is simple, but can be slow for large environments. Carefully plan backup schedules and cross-region replication to meet your organization's recovery needs and compliance requirements. The Pilot Light recovery method is a step up from basic backup and restore strategies. It introduces continuous data replication between your primary and disaster recovery regions, which helps reduce your recovery point objective, or RPO, and ensures critical infrastructure is always running in your disaster recovery region. With Pilot Light, your disaster recovery region has essential infrastructure like virtual private clouds and load balancers, always operational. Data is continuously replicated using services such as Amazon Simple Storage Service with cross-region replication, Amazon Relational Database Service cross-region read replicas, and Amazon Aurora Global Database. This means your data is nearly up to date in the disaster recovery region, minimizing data loss during a disaster. Imagine a three-tiered web application: front-end servers, application servers, and a database. In the primary region, everything is active, while the disaster recovery region keeps only the core infrastructure running. Data is replicated to an Aurora replica in the disaster recovery region. If disaster strikes, the disaster recovery region can quickly scale up, activate load balancers, and promote the Aurora replica to primary. Failover involves activating the secondary load balancer, provisioning application servers from pre-configured Amazon machine images, and promoting the database replica. This process can be automated or manual depending on your setup. The pilot light method balances cost and recovery speed, making it ideal for organizations seeking low data loss and efficient disaster recovery. When planning for disaster recovery, minimizing downtime is crucial. If you need a faster recovery time objective and recovery point objective than what backup and restore or pilot-like strategies offer, warm standby is your next best option. Warm standby builds on the pilot-light approach by keeping a scaled-down, operational version of your primary environment running in your disaster recovery region. This means essential resources are always active, ready to process requests immediately if a failure occurs. While this increases complexity and cost compared to Pilot Light, it significantly reduces recovery time, since resources do not need to be spun up from scratch. Imagine your primary region hosts a web application with traffic managed by Route 53, load balancers, and Amazon EC2 instances. Data is stored in an Aurora global database, replicated asynchronously to the disaster recovery region. In warm standby, your disaster recovery region already runs scaled-down web and application servers, plus an Aurora replica with write forwarding. If the primary region fails, Route 53 redirects traffic and your disaster recovery infrastructure is ready to serve requests almost instantly. Warm standby reduces downtime, but comes with higher costs due to always-on resources. Auto-scaling groups help manage increased demand, but brief connectivity issues may occur during scaling. Multi-site active-active is the most complex and costly disaster recovery strategy, but it delivers the lowest recovery time objective and recovery point objective. This makes it ideal for critical applications that cannot afford downtime or data loss. Unlike other recovery options that require provisioning extra resources after a disaster, multi-site active-active deploys your infrastructure at full scale across multiple regions. There is no designated disaster recovery region. Customers can access your applications from any region, and if one region fails, another seamlessly takes over. For example, Routes 53 routes traffic based on specific policies, while the Elastic Load Balancer distributes requests across availability zones. The application layer connects to DynamoDB, which uses global tables for automatic data replication and continuous backups in both regions. This setup ensures your services remain available without manual intervention. Despite its strengths, multi-site active-active is not without challenges. Regular disaster recovery testing is essential to confirm that remaining regions can handle increased traffic during a failure. Additionally, issues like data corruption or deletion may still require restoring databases from backups, which can impact recovery time. Multi-site active-active offers unmatched resilience for mission-critical workloads, but it demands careful planning, ongoing testing, and significant investment to ensure true business continuity. Decoupling in application development means letting each component work independently. This approach ensures that changes or failures in one part do not impact others, making applications more resilient and easier to maintain. In a tightly coupled system, layers depend on each other directly. For example, if a processing layer fails, it can disrupt the entire application. Decoupling solves this by introducing a messaging mechanism between layers, isolating failures and changes. Amazon's Simple Queue Service, or SQS, is a messaging service that enables decoupling. It acts like an email system for application layers. Messages are placed in queues by producers and picked up by consumers, even if no consumer is immediately available. When a message is sent to an SQS queue, consumers poll for new messages. Once picked up, the message is locked with a visibility timeout, preventing others from processing it. If not deleted after processing, it becomes visible again for another consumer. SQS supports delay queues, letting you postpone message delivery for up to 15 minutes. The default visibility timeout is 30 seconds, but it can be adjusted up to 12 hours to match your application's processing needs. Amazon Simple Queue Service, or SQS, offers two ways for consumers to receive messages: short polling and long polling. With short polling, SQS responds immediately to a request even if no messages are available. This happens when the wait time seconds parameter is set to 0. Long polling, on the other hand, waits up to 20 seconds for messages, reducing empty responses. By default, SQS messages can be between 1 byte and 256 kilobytes. If you need to process larger messages, the Amazon SQS Extended Client Library for Java lets you handle messages up to 2 gigabytes by storing them in Amazon Simple Storage Service, or S3. Standard queues in SQS offer at least once delivery and best effort ordering, supporting up to 120,000 in-flight messages. For guaranteed order and exactly once delivery, use FIFO queues, which support up to 20,000 in-flight messages but may perform slightly slower. If a message is not deleted after processing, it becomes visible again. To avoid endless retries with corrupted messages, use dead letter queues. Dead letter queues capture problematic messages for review. Combine SQS with Simple Notification Service, or SNS, to trigger alerts and automate remediation. The Simple Notification Service, or SNS, is Amazon Web Services' solution for distributing messages from one publisher to many subscribers. SNS uses a topic-based model, where a topic acts like a virtual mailbox for messages. When a publisher sends a message to a topic, SNS instantly pushes that message to all current subscribers. Unlike queues, topics do not store messages. Once a message is published, it cannot be recalled and there is no message preservation. Subscribers can be mobile devices, desktops, HTTPS endpoints, email addresses, AWS Lambda functions, or even phone numbers via Short Message Service, or SMS. SNS supports global SMS delivery, making it ideal for notifications, multi-factor authentication, and one-time passwords. SMS allows subscribers to set filter policies using JSON, so they only receive messages relevant to them. Delivery policies control retry patterns, and undeliverable messages can be sent to a dead letter queue for further analysis. SNS can fan out messages to multiple Amazon Simple Queue Service, or SQS, queues. This enables reliable, asynchronous workflows, such as triggering image processing when a file is uploaded to Amazon S3. When working with Amazon Web Services, or AWS, there are several ways to provision and operate resources programmatically. While the AWS console is great for simple, one-time tasks, developers and administrators often need more powerful, automated solutions. Application Programming Interfaces, or APIs, allow different software systems to communicate. Every action in the AWS console, like creating an S3 bucket, actually triggers an API call behind the scenes. Developers can write custom code to call these APIs directly, but must handle authentication and request signing themselves. To simplify this, AWS offers software development kits, or SDKs, for languages like Python, Java, PHP, and .NET. These SDKs handle the complexity of signing requests and make it easier to interact with AWS services using familiar programming languages. For those who prefer command line tools, the AWS Command Line Interface, or CLI, is a powerful option. Once configured, users can automate tasks and manage AWS resources directly from the terminal. Specialized CLIs exist for services like Elastic Beanstalk and the Elastic Container Service, or ECS. Infrastructure as Code, or IAC, lets you define your AWS infrastructure in templates. With AWS CloudFormation, you can create reusable templates to provision resources consistently across regions, making disaster recovery and scaling much simpler. By leveraging APIs, SDKs, the CLI, and infrastructure as code, AWS users can automate, scale, and manage resources efficiently and reliably. The AWS console is a user-friendly way to create and manage cloud resources, but as your infrastructure grows, you might notice that some tasks become repetitive and time-consuming when done manually. Imagine you have dozens of EC2 instances powering your website. If you need to generate a daily report of their public IP addresses, you could log into the console and copy each one by hand. However, this process is tedious and prone to mistakes, especially as IP addresses can change frequently. This is where the AWS Command Line Interface, or AWS CLI, comes in. Instead of clicking through the console, you can use simple commands in a terminal to interact directly with AWS services. Every action you take in the console actually makes an API call behind the scenes. With the AWS CLI, you make those same API calls, but through scripts or commands, using a Linux shell, the built-in Mac terminal, an EC2 instance, or even a program like Putty on Windows. Scripting with the AWS CLI is not only faster, but also safer and less error-prone. It allows you to automate repetitive tasks and manage resources more efficiently. In short, the AWS CLI is a powerful tool that gives you greater flexibility and control over your AWS resources. Ever spent hours clicking through endless screens in the Amazon Web Services console just to launch a single EC2 instance, only to make a mistake and start over? You are not alone. Manually creating resources in Amazon Web Services is time-consuming and error-prone. Even using the Command Line Interface, or CLI, still leaves you with manual updates and maintenance. There is a better way. Amazon Web Services CloudFormation lets you automate the creation, updating, and deletion of your infrastructure. Instead of writing shell scripts or custom logic, you define your resources declaratively in a CloudFormation template using either YAML or JSON. You write your infrastructure as code in a template, upload it to CloudFormation, and this service creates a stack, a collection of resources managed as a single unit. If any resource fails, CloudFormation rolls back everything, ensuring your environment is always consistent. With CloudFormation, you can version your templates, test changes, and deploy through continuous integration pipelines. This makes it easy to replicate environments like development, staging, and production. Stop wasting time with manual setup. Automate your Amazon Web Services infrastructure with CloudFormation and focus on building, not clicking. CloudFormation templates are the backbone of automating infrastructure in Amazon Web Services, or AWS. Whether you use JSON or YAML, every template follows the same structure, making it easy to standardize deployments. Each template includes several main sections: the format version, description, parameters, mappings, conditions, transform, resources, and outputs. The format version is always set to 2010-09-09. The description is optional, letting you document your infrastructure for collaborators. Resources is the only required section, where you declare at least one AWS resource, like an EC2 instance. Each resource has a logical ID, a resource type, such as AWS EC2 instance, and properties like instance type or image ID. To avoid hard-coding values, use the parameter section. Parameters let users customize things like instance type or key pair name at stack creation, making templates flexible. CloudFormation provides intrinsic functions like !ref, !get@, and !find and map for dynamic references. Mappings act as lookup tables, helping you select values like the correct Amazon machine image, or AMI, for different regions. Conditions control resource creation based on logic, while the transform section enables macros for advanced processing. The outputs section returns information, such as an instance's public IP, after stack creation. CloudFormation is Amazon Web Services' tool for managing infrastructure as code, but how does it actually work behind the scenes? Let's break down what happens internally when you create, update, or delete a stack using CloudFormation. A stack in CloudFormation acts as a state machine. When you create a stack, CloudFormation takes your template and parameters, then transforms them into a stack with actual resources. Updating a stack means CloudFormation compares your new template and parameters with the existing stack and then applies the necessary changes. Deleting a stack removes all the resources provisioned by that stack, turning it back into nothing. Each resource in your stack follows a similar life cycle: create, update, and delete. CloudFormation analyzes your template to determine dependencies, creating resources in the correct order. If resources are independent, CloudFormation can create them in parallel. During updates, it checks if changes are needed and only acts if necessary, minimizing disruptions. Understanding CloudFormation's internal process helps demystify the service. It is not magic, it is a logical function that takes your input and produces the desired infrastructure, efficiently managing dependencies and changes for you. Let us break down the life cycle of a stack in AWS CloudFormation, focusing on how information flows when you create, update, or delete a stack. Everything starts with a command, either from a person or a machine, sent to CloudFormation using the AWS command line interface, console, software development kit, or HTTP APIs. This command includes the template, parameters, and metadata needed for the stack. CloudFormation immediately checks for basic errors, like malformed JSON or circular references. If the request passes these checks, CloudFormation acknowledges the start of the process, returning a status and the Amazon resource name, or ARN, of the stack. Once acknowledged, CloudFormation issues commands to the stack, which delegates tasks to each resource defined in the template. Each resource interprets its properties and attempts to create, update, or delete itself, then reports back its result. CloudFormation collects these results and publishes events to the Simple Notification Service, or SNS. You can subscribe to these topics for updates or use custom listeners like AWS Lambda for automation. Understanding this flow helps you automate DevOps workflows and monitor stack changes efficiently. Mastering stack lifecycles is key to effective CloudFormation management. When learning to code, students quickly discover the value of reusing code. Instead of copying and pasting the same lines everywhere, they create functions and call them as needed. This makes code cleaner and easier to manage. The same principle applies to AWS CloudFormation. If you have a virtual private cloud, or VPC, configuration that you use in multiple templates, you do not need to copy it each time. Instead, you can create a separate CloudFormation template for the VPC and reference it wherever needed. This is called a nested stack. Imagine Stack A defines your test environment, while Stack B defines networking components like a VPC. Stack A can include Stack B as a resource. When you create Stack A, CloudFormation also creates Stack B. This can even extend to Stack B referencing Stack C, forming a hierarchy. To set up nested stacks, upload your child template to an Amazon Simple Storage Service or S3 bucket. In your parent template, add a resource of type AWS CloudFormation Stack and provide the S3 URL for the child template. Nested stacks modularize your templates, making them easier to read and maintain. Always update or delete change sets at the root stack level to ensure consistency across your entire CloudFormation hierarchy. CloudFormation is AWS's tool for defining infrastructure as code. But what if you need to manage third-party tools or unsupported AWS resources? That is where custom resources come in, extending CloudFormation's capabilities. Custom resources let you create new resource types in CloudFormation. This means you can automate provisioning for things like a MongoDB database or any tool not natively supported by AWS. You write the logic and CloudFormation handles the rest. Custom resources rely on AWS Lambda or Amazon Simple Notification Service or SNS. When CloudFormation needs to create, update, or delete your custom resource, it sends a request to your Lambda function or SNS topic, which runs your custom logic. First, write a Lambda function that handles create, update, and delete events. Next, declare your custom resource in your CloudFormation template, specifying the service token property. This property points to your Lambda's Amazon resource name, or ARN. Your Lambda must send a response to a signed Amazon Simple Storage Service, or S3, URL. CloudFormation checks this response to mark the resource as a success or failure. Custom resources give you flexibility, but require careful implementation. When managing third-party resources in AWS CloudFormation, you might wonder whether to use resource types or custom resources. Let's break down the key differences and help you choose the right approach. Resource types are the latest method for managing third-party resources in CloudFormation. The biggest advantage is that AWS handles the underlying infrastructure for you. You no longer need to manage S3 buckets, Lambda functions, or SNS topics to perform operations. Sharing resource types is also easier, since once registered in the CloudFormation registry, they are available for all templates in your account and region. Plus, resource types require a schema, allowing CloudFormation to treat them like native resources. This enables features like drift detection, change sets, and AWS config integration. However, developing resource types can be more challenging. You must create a schema that follows strict rules and learn the CloudFormation command line interface, or CLI. This can feel daunting compared to custom resources. Custom resources are quicker to set up and don't require registration. If you need something fast and simple, they might be the better choice. Overall, consider resource types first for consistency and integration, but in some cases, custom resources may still be the right fit. When building serverless applications on Amazon Web Services or AWS, Lambda is often the first tool that comes to mind. But what happens when your workflows get more complex? Lambda is great for short, simple tasks, but it has limitations. For example, it can only run for up to 15 minutes, and it does not natively support retries, waiting, or parallel execution. This is where AWS step functions come in. AWS Step Functions is a state machine service that lets you orchestrate complex workflows, guiding your application through a series of steps, decisions, and actions. You define your workflow using Amazon State Language, a JSON-based format. Step Functions provides a real-time visual graph in the AWS console, making it easy to design, debug, and monitor your workflows as they run. Step functions support states like task, choice, wait, parallel, and map. These allow you to run tasks, make decisions, pause, process items in parallel, and iterate over lists, all without managing servers. For example, you can automate video processing, validating files, extracting metadata, updating databases, and sending notifications, all orchestrated seamlessly with AWS step functions. Simple Email Service, or SES, is Amazon Web Services' managed platform for sending and receiving emails at scale. SES is designed for marketers and developers who need reliable, cost-effective email communication with customers, such as sending order confirmations or account notifications. SES integrates easily with existing systems using the Simple Mail Transfer Protocol, or SMTP, and AWS Software Development Kits, or SDKs. It supports both outgoing and incoming email, making it versatile for automated workflows. SES also scans incoming emails for spam and viruses, ensuring your communications remain secure. When you first use SES, you start in a sandbox environment, allowing you to test by verifying a single email address. After verification, you can send test emails. To move to production and send to more recipients, request to leave the sandbox through AWS support. SES can automatically process incoming emails, such as handling unsubscribe requests or creating support tickets. You can configure SES to deliver emails to Amazon S3, notify via simple notification service, or trigger AWS Lambda functions for custom processing. SES uses recipient-based and IP address-based controls to manage email flow. Actions include storing emails, sending notifications, or rejecting unwanted messages, giving you full control over your email system. The AWS Cloud Development Kit, or CDK, is now an important topic for both the AWS Certified Developer Associate and AWS Certified DevOps Engineer Professional exams. Let's take a quick look at what makes the CDK so useful for developers. The AWS Cloud Development Kit is an open-source software development framework that lets you define AWS infrastructure and resources using code. Instead of writing complex YAML templates, the CDK automatically generates AWS CloudFormation templates at compile time, making infrastructure management more accessible and efficient. With the CDK, you can use familiar programming languages like Python, C#, Java, JavaScript, and TypeScript. This means you can leverage your existing skills and use common programming constructs such as functions, loops, and conditionals. The CDK also includes libraries called constructs, which help you define AWS resources like S3 buckets, DynamoDB tables, Lambda functions, and API gateway APIs. You can even create your own custom constructs. Developers interact with the CDK using its command line interface to create, build, and deploy applications to specific environments, streamlining the entire process. Explore the CDK further to gain hands-on experience and start building your own cloud applications. Good luck on your certification journey. Monitoring and reporting. Amazon CloudWatch is a global monitoring service designed to give you deep visibility into the health and performance of your applications and infrastructure. It collects and presents operational data, helping you minimize incidents and optimize your environment. CloudWatch offers a suite of powerful features. With CloudWatch dashboards, you can build custom visualizations of metrics and alarms from resources across multiple regions. CloudWatch metrics track key data points like disk reads or number of objects, and support anomaly detection using machine learning to spot unusual activity. CloudWatch alarms let you automate actions or send notifications when thresholds are crossed, integrating seamlessly with dashboards for real-time awareness. Dashboards are fully customizable, allowing you to display exactly the data you need for specific projects, customers, or regions. Metrics can be standard or custom, and detailed monitoring is available for deeper insights, with data collected as frequently as every minute. Alarms can trigger automated responses, such as scaling resources or sending alerts. CloudWatch Event Bridge connects your applications to AWS services, enabling real-time, event-driven architectures by routing events to targets like Lambda or SQS. CloudWatch logs centralize log data from AWS services and your applications. With Log Insights, Container Insights, and Lambda Insights, you can analyze and visualize logs, gaining actionable information to troubleshoot and optimize your systems. CloudWatch dashboards in Amazon Web Services or AWS make it easy to visualize your data without digging into each service. With dashboards, you can quickly see key information and make decisions about your workloads and processes, all from a single customizable view. Dashboards are built from widgets, which include line charts, stacked area charts, number widgets, bar charts, pie charts, text widgets, log tables, and alarm statuses. You can even run queries within widgets for detailed insights. CloudWatch also offers automatic dashboards for services like EC2, giving you instant visibility into important metrics. A standout feature is the ability to perform math on metrics and aggregate data across sources, such as monitoring CPU load across an entire auto-scaling group. You can create dashboards visually using the drag-and-drop editor or programmatically with JSON code, even integrating them into CloudFormation templates. The editor lets you arrange and resize widgets for a tailored experience, while code-based dashboards offer flexibility for automation. Dashboards can be shared across accounts and regions, with options for public or restricted access. Best practices include using large graphs for key metrics, annotating graphs, and providing clear descriptions so everyone understands the data at a glance. Amazon CloudWatch Anomaly Detection, introduced by Amazon Web Services in 2019, uses machine learning to automate the creation and maintenance of CloudWatch alarms. This reduces manual intervention and makes monitoring more effective and efficient. Machine learning models in CloudWatch Anomaly Detection learn what is normal and abnormal for your chosen metrics by analyzing historical data. Unlike traditional static thresholds, these models adapt over time, refining their understanding as more data is collected. When enabled, CloudWatch Anomaly Detection creates a confidence band of expected values for each metric. If the metric's value falls outside this band, an alarm is triggered. The model adjusts for hourly, daily, or weekly trends and updates every 5 minutes. You can fine-tune the anomaly detection threshold and use any standard or custom metric with a repeatable pattern. The service supports configuration through the AWS Management Console, AWS Command Line Interface, and AWS Software Development Kits. The model's accuracy depends on the quality and quantity of historical data. Exclude abnormal periods from training data for best results. Quote, "For the best result, at least 3 days of data is recommended," said Stephen Cole. CloudWatch Anomaly Detection is a powerful, adaptive tool for monitoring, but it is not a silver bullet. Use it alongside other alarms for comprehensive coverage. When building systems on Amazon Web Services, or AWS, you might start with monolithic architectures. These are tightly connected and hard to scale. Microservices improve things, but still require services to know about each other. Enter event-based architecture. Here, services react to events, not direct calls. Amazon Event Bridge is AWS's event coordinator. It collects information from AWS services, external software as a service providers, and your own applications, then routes events to where they are needed. Events in EventBridge are structured as JSON strings. Each event includes details like version, unique ID, source, AWS account, timestamp, region, resources involved, and a details section with the event's content. Over 90 AWS services can generate these events. Events land on an event bus. Every AWS account has a default one, but you can create custom ones. Rules filter events and decide where they go. You can even schedule rules or send events across accounts. Targets are where the action happens. They include Lambda functions, EC2 instances, and more. EvenBridge also integrates with over 30 software as a service providers, making it a powerful tool for building flexible, scalable systems. Amazon EventBridge offers a powerful feature, event archiving. With EventBridge Archives, you can store events for as long as you set the retention period, or even indefinitely. Since events are text-based, storage is efficient and cost-effective. Archiving events is essential for disaster recovery. If your database is ever corrupted or deleted, archived events let you reconstruct its exact state. Replaying events archived is also useful when updating your app or adding new features, helping you extract new insights from old data. EventBridge includes a schema registry, which describes the structure of events. Every AWS service integrated with EventBridge has pre-built schemas, making development easier. You can also discover schemas from software as a service events or create your own custom schemas from JSON. Developers can generate code bindings for Java, Python, and TypeScript. These bindings help Visual Studio validate variables and expose attributes, speeding up development for both AWS and custom schemas. While Amazon's Simple Notification Service is simple and highly scalable, EventBridge offers advanced routing and SaaS integration. Compared to Kinesis, EventBridge provides greater flexibility, especially for SaaS provider events. EventBridge also integrates with over 30 software as a service providers, making it a powerful tool for building flexible, scalable systems. AWS CloudTrail is a service designed to record and track events in your AWS account. It captures both application programming interface, or API requests, and non-API actions, whether they come from users, the AWS Management Console, or other AWS services. CloudTrail organizes events into 3 categories: management events, which track control plane operations, like creating users or databases; data events, which log resource-level actions, such as Amazon S3 Object Access; and insight events, which highlight unusual activity to help identify potential issues. To store and analyze events beyond the default 90-day event history, you can set up CloudTrail trails. There are 3 types: all region trails, which cover every region in your account; single region trails, which focus on one region; and AWS organization trails, which capture events across all accounts in your AWS organization. CloudTrail Lake lets you store, review, and query events for up to 7 years. You can filter which events to keep and use structured query language, or SQL, to analyze data, making it easier to troubleshoot incidents and security threats. CloudTrail Lake also collects logs from AWS config and external sources, including your own data center. Integration with partners like CrowdStrike and GitHub allows seamless data capture through CloudTrail channels, enhancing your visibility and security. AWS CloudTrail is a powerful service that records activity across your Amazon Web Services environment. Whether you set up trails for a single region, all regions, or your entire AWS organization, CloudTrail captures a comprehensive log of events, giving your business a clear view of what is happening in your cloud infrastructure. One of the main benefits of CloudTrail is enhanced security. By tracking every API call, your security teams can quickly identify suspicious events, such as unsuccessful sign-in attempts or unauthorized actions. This visibility allows you to investigate incidents, determine who initiated them, and implement preventative measures. With CloudTrail, you gain a deeper understanding of your environment, helping you spot weaknesses and reinforce your security boundaries. CloudTrail makes it easy to consolidate activity records from multiple regions into a single Amazon Simple Storage Service bucket. This single pane of glass approach simplifies analysis and auditing. CloudTrail Insights, a feature you can enable, automatically detects unusual behavior in write API actions, alerting you to potential threats and providing additional metadata for investigation. CloudTrail's detailed logs support governance and regulatory compliance. By maintaining a recorded audit of actions and configuration changes across accounts and regions, your organization can meet audit requirements and ensure operational best practices are followed. To set up and manage AWS CloudTrail, you need the right permissions. Without them, you will not be able to create or configure trails. If you lack access, contact your AWS administrator or security team. AWS offers 3 managed policies for CloudTrail. The CloudTrail's service role policy is for the service-linked role and cannot be attached to users or groups. The AWS CloudTrail Full Access policy lets you configure CloudTrail and includes permissions for related services like Amazon Simple Notification Service, Amazon S3, Amazon CloudWatch Logs, and AWS Key Management Service. This is because CloudTrail often integrates with these services for log storage, encryption, and notifications. If you let CloudTrail create resources like S3 buckets or SNS topics, it automatically applies the necessary permissions. For example, CloudTrail can write logs to the S3 bucket it creates. However, if you use existing resources, you must manually add the required permissions to ensure CloudTrail works correctly. The AWS CloudTrail read-only access policy only allows you to view trail settings, list trails, and look up events from the last 90 days. It does not permit creating or modifying trails. AWS CloudTrail trails are essential for capturing, tracking, and retaining events across your AWS accounts. Without trails, you can only view events in the CloudTrail dashboard for up to 90 days. Trails send captured events to log files, typically stored in Amazon Simple Storage Service or Amazon S3, or to CloudTrail Lake for longer retention and advanced querying. CloudTrail log files are written in JavaScript Object Notation, or JSON, and can contain multiple events. Each event records details like the action requested, who made the request, when it happened, and which AWS service was involved. For example, the user identity field shows who performed the action, while event time records the timestamp. The event source reveals the AWS service, such as signin.amazonaws.com for console logins. Other important fields include source IP address, which captures the user's IP address, and user agent, which identifies the browser or tool used. The response elements field shows if the request succeeded. Additional event data can reveal if multi-factor authentication, or MFA, was used. Each event also has a unique event ID and indicates if it was read-only. CloudTrail delivers logs to S3 using a structured folder hierarchy: bucket name, prefix, AWS logs, account ID, CloudTrail, region, year, month, and day. This makes navigation and management straightforward. CloudTrail can aggregate logs from multiple AWS accounts into a single S3 bucket, simplifying centralized log management for organizations. AWS CloudTrail and Amazon CloudWatch work together to enhance your security monitoring by providing deep visibility into your infrastructure. By integrating CloudTrail logs with CloudWatch, you can quickly identify risks and anomalies across your AWS environment. To send CloudTrail event logs to CloudWatch, you must enable this option during trail creation or by editing an existing trail. You can choose an existing or new log group and assign a role for CloudTrail to publish logs. CloudWatch enables robust security monitoring of CloudTrail logs. For example, you can receive alerts when API calls modify security groups or network access control lists in your virtual private cloud, or when changes occur in identity and access management policies. Custom metric filters let you search for specific terms in your logs, such as unsuccessful console login attempts. By setting thresholds, you can trigger automatic notifications for suspicious activity, helping you respond quickly to potential threats. Contributor insights visualize top contributors to specific events, like changes in your virtual private cloud. By creating rules, you can pinpoint users or IP addresses responsible for key activities, making it easier to spot security issues. CloudWatch Log Insights uses a query language to analyze CloudShell logs. With sample queries, you can quickly extract valuable information, visualize trends, and export results for further analysis, helping you proactively detect and resolve issues. Managing a handful of machines is simple, but as your fleet grows into the hundreds or thousands, maintaining consistency becomes a real challenge. That is where automation in AWS Config come in. AWS Config is a service designed to automatically discover your Amazon Web Services resources, providing a complete inventory and tracking configuration changes over time. This visibility is crucial for operational excellence and quick remediation when things drift from your desired state. By default, AWS Config is disabled when you create a new account. To get started, you need to enable the AWS Config Recorder. This module tracks changes in your resource configurations and records them as configuration items. The AWS Config Recorder operates within a specific region and can monitor all current and future resources or just selected types. It even supports global resources like AWS Identity and Access Management users and roles. Remember, you must define a role to allow AWS Config to interact with your resources. AWS Config typically delivers its records to an Amazon Simple Storage Service bucket. You can also send detailed change notifications to Amazon Simple Notification Service or Amazon Event Bridge. Data is retained for 7 years by default. Once enabled, AWS Config examines each resource, creating configuration items, including one for the recorder itself. AWS Config brings automation, visibility, and consistency to your cloud environment. When you set up AWS Config, the first thing delivered to your Amazon Simple Storage Service, or S3, bucket is a configuration item for each resource. Each configuration item includes metadata, attributes, relationships, and the current configuration. Metadata covers details like version ID and capture time. Attributes include the resource ID, creation time, Amazon Resource Name or ARN, and tags. Relationships show how resources connect, such as an Elastic Block Store or EBS volume attached to an Elastic Compute Cloud or EC2 instance. The current configuration details the resource's present state. AWS Config delivers 2 main types of files to your S3 bucket: configuration history and configuration snapshots. Configuration history is a timeline of configuration items for a specific resource, showing how it changed over time. These files are delivered every 6 hours. Configuration snapshots, on the other hand, capture the state of all resources at a single point in time. Snapshots can be generated manually or on a schedule, such as every hour or every day. Both histories and snapshots are in JSON format and stored in separate folders within your S3 bucket. Aggregators in AWS Config consolidate configuration and compliance data from multiple AWS accounts and regions. This means you can view all your configuration items and compliance results in one place, making it easier to manage resources across your organization. Aggregators provide a unified view for better visibility and control. AWS config rules help you define the desired configuration state for your AWS resources. AWS config continuously evaluates your resources and marks them as compliant or non-compliant based on the rules you set. AWS offers over 320 managed rules covering more than 55 AWS services. These rules are ready to use or customize. For example, the EIP attached rule checks if elastic IP addresses are attached to EC2 instances, while EC2 volume in use check ensures EBS volumes are in use. The restricted SSH rule helps enforce security by limiting SSH access. Custom roles. If you need more flexibility, you can create custom roles using AWS Lambda. Associate your role with a Lambda function to define your own compliance logic. The AWS Config Rule Development Kit, or RDK, simplifies this process for those comfortable with the AWS command line interface. CloudFormation Guard is an open-source policy-as-code tool. It uses a domain-specific language to define rules that validate CloudFormation templates, Terraform files, and Kubernetes configurations, ensuring compliance before deployment. You can choose proactive or detective evaluation modes and set triggers based on configuration changes or specific time intervals. Some rules require parameters like max access key age. Tags help organize and group resources as your AWS environment grows. AWS Config gives you visibility into your cloud resources by tracking their configurations and evaluating them against defined rules. Compliance in AWS Config means a resource follows all applicable rules. If it fails even one, it is marked non-compliant. Sometimes, AWS Config cannot determine compliance, resulting in an insufficient data status, which can happen if a rule has never been evaluated or if evaluation results are missing. When resources are non-compliant, AWS Config does not block their creation, but highlights the issue for remediation. Remediation can be manual or automatic. Automatic remediation uses AWS Systems Manager automation documents to trigger corrective actions as soon as non-compliance is detected. If the issue persists, you can set up retries and specify wait times between attempts. Hundreds of predefined remediation actions are available, and you can also use Systems Manager Change Manager to schedule changes or require approvals. A conformance pack is a collection of AWS config rules and remediation actions bundled together. You can deploy these packs across accounts, regions, or organizations using YAML documents. AWS provides templates, or you can create custom packs tailored to your needs. Conformance packs offer a flexible compliance framework, but are not designed to guarantee adherence to specific governance standards. They serve as a strong starting point for implementing best practices. Logging is often overlooked until a problem strikes, but its value to infrastructure cannot be overstated. Many organizations only realize its importance after a security breach or incident has already occurred. Logs are generated by services and applications, capturing extensive information and storing it for future analysis. Some logs can even be monitored in real time, enabling automatic responses based on their contents. From an auditing perspective, logs are invaluable. They often include metadata like date stamps, source IP addresses, and usernames. For example, CloudTrail logs help organizations meet compliance certifications by providing evidence of traceable and auditable actions. When incidents happen, resolving them quickly is crucial. Logs provide insight into what occurred before, during, and after an event, helping teams pinpoint the source and reduce resolution time. This leads to a better customer experience and can even prevent issues from escalating in the first place. By consistently logging activity across applications, networks, and cloud infrastructure, organizations can establish performance baselines. Monitoring logs with thresholds and alerts allows for early detection of threats and anomalies, giving operational teams the information they need when it matters most. Amazon CloudWatch is a monitoring service for your AWS resources, but it is also a powerful tool for collecting and analyzing logs from your applications and AWS services. With CloudWatch logs, you can monitor log streams in real time and set up metric filters to alert you to specific events. The unified CloudWatch agent is essential for collecting logs and additional metrics from Amazon Elastic Compute Cloud, or EC2, instances, as well as on-premises servers running Linux or Windows. To set up the agent, you need to create roles with the right permissions, allowing CloudWatch to collect data and interact with the AWS Systems Manager, or SSM. One role manages configuration storage in SSM's parameter store, while another sends data to CloudWatch. Install the agent using the EC2 Systems Manager's run command. Select your EC2 instance, choose the Amazon CloudWatch agent package, and run the install action. If you enter the wrong package name, installation will fail, so accuracy is key. Configure the agent using the built-in wizard, specifying which metrics and logs to collect. Store the configuration in SSM's parameter store, then start the agent using Systems Manager. Now, your logs and metrics flow directly to CloudWatch. CloudWatch Logs centralizes data, making it easy to monitor, search, and respond to events across your AWS environment. Amazon CloudFront is Amazon Web Services' content delivery network designed to speed up the distribution of your content using a global network of edge locations. When you enable access logs, every user request to your CloudFront distribution is recorded for analysis. CloudFront access logs are generated at each edge location and are specific to each distribution. Logs for different distributions are kept separate, but all edge locations for a single distribution write to the same log file. These logs are delivered to Amazon Simple Storage Service, or Amazon S3. To enable logging, simply edit your CloudFront distribution settings, turn logging on, and select your S3 bucket for log storage. You can also add a log prefix or enable cookie logging, which records cookie data if your origin is not S3. You need full control permissions on the S3 bucket to enable logging. CloudFront uses your credentials to grant the AWS Data Feeds account access, allowing it to write logs. Log delivery to S3 can take from 1 to 24 hours. Web distributions log 26 fields per entry, including timestamp, edge location, requester IP, HTTP method, status code, and protocol. Real-time messaging protocol, or RTMP distributions log 13 fields, such as event type and source IP. Virtual Private Cloud Flow Logs, or VPC flow logs, capture IP traffic information flowing between network interfaces in your virtual private cloud. This is essential for monitoring, troubleshooting, and securing your cloud environment, especially when managing hundreds of resources across multiple subnets and VPCs. Unlike Amazon Simple Storage Service access logs, VPC flow logs send data to Amazon CloudWatch logs, not to Amazon Simple Storage Service. However, there are limitations. You cannot monitor traffic from EC2 classic environments, and logs for peered VPCs are only available within the same account. Some traffic, like DHCP, Amazon DNS, and metadata service traffic, is not captured. You can create flow logs for a network interface, a subnet, or the entire VPC. During setup, select a filter for accepted, rejected, or all traffic. Choose an identity and access management role with the right permissions, and specify a CloudWatch log group. Remember, once created, flow logs cannot be modified. Delete and recreate if changes are needed. Each log entry includes details like version, account ID, interface ID, source and destination addresses, ports, protocol, packet and byte counts, timestamps, action, and log status. The action field is crucial for identifying accepted or rejected traffic. AWS Service Catalog is a powerful tool designed to simplify how organizations manage and provision IT resources. It lets IT admins pre-approve services like EC2 instances, databases, and software, making it easy for end users to deploy secure, compliant stacks without constant admin intervention. Within AWS Service Catalog, a product is any IT service you want to make available, from a single EC2 instance to a complex multi-tiered application. Products are created using AWS CloudFormation templates and can include detailed descriptions, versioning, and tags for tracking usage and costs. These products are grouped into portfolios, collections tailored for specific teams or roles, each with its own permissions and owner for accountability. Admins can apply constraints to products and portfolios, controlling who can launch resources, what configurations are allowed, and where deployments happen. For example, launch constraints use AWS Identity and Access Management or IAM roles to ensure only approved permissions are used. Template constraints help enforce compliance by limiting user options during provisioning. Service actions empower users to perform specific operational tasks, like database backups, without needing full access. AWS Service Catalog offers a free tier for up to 1,000 API calls per month, with minimal charges beyond that, making it cost-effective for most organizations. Managing software licenses in the cloud can be complex, especially when dealing with multiple vendors like Microsoft, SAP, Oracle, and IBM. Asset managers and auditors often struggle to keep track of licenses across both cloud and on-premises environments. AWS License Manager is designed to simplify this process. It supports tracking for any software where licensing is based on virtual cores or vCPUs, physical cores, sockets, or the number of machines. With AWS License Manager, you can create license configurations that include customizable rules tailored to your specific licensing agreements. These rules define how licenses are counted, set minimum and maximum thresholds for resources, and specify the total number of licenses available. You can set hard limits to block the launch of instances that would breach your license agreements, or soft limits that allow launches but send notifications. Rules can also specify which Amazon Elastic Compute Cloud, or EC2, tenancy types can consume a license, such as shared tenancy, dedicated instances, or dedicated hosts. AWS License Manager integrates with AWS Systems Manager and AWS organizations, enabling centralized monitoring across multiple AWS accounts and on-premises environments. It also supports Bring Your Own License from AWS Marketplace. AWS License Manager streamlines license management, helping you stay compliant and organized across all your environments. The AWS Health Dashboard is your central hub for monitoring the health of Amazon Web Services. It is divided into two main sections: events affecting everyone and events specific to your account's resources. Let's break down how each section helps you stay informed. First, you'll find Open and Recent Issues, which displays current problems across the AWS platform. If there are no major incidents, this section may be disabled. Below that, Service History provides a timeline of past issues, making it easy to investigate outages that happened over weekends or holidays. Switching to your account health, the dashboard correlates global AWS issues with your own resources. For example, if you run an EC2 instance, you might see scheduled events indicating upcoming maintenance. Simply stopping and restarting your instance moves it to new hardware, minimizing disruption. To avoid manually checking the dashboard, use EventBridge. EventBridge can monitor AWS health events, notify your operations team, and even trigger custom actions like creating support tickets, ensuring a fast response to any incident. With the AWS Health Dashboard and EventBridge, you can quickly identify, understand, and respond to issues, keeping your AWS environment running smoothly. Let's take a quick look at the AWS Management Console. The first step is always to get a broad overview of your environment. This means understanding which services you use, your current and past usage, and your overall expenses. To start analyzing costs, head to the billing dashboard. You can find it by typing bill in the search bar or navigating through the menu. The billing dashboard is your main platform for tracking expenses and usage. The first thing to check is your bill from the previous month. Select the last month from the drop-down menu to see your total spending, tax details, and payment summaries. You can also download your bill as a CSV file or PDF. Focus on the most expensive services. For example, if Elastic Compute Cloud is your biggest cost driver, prioritize it in your analysis. Smaller expenses, like those for API Gateway or CloudFront, may not need deep investigation if their impact is minimal. Check which regions are being used. Some, like those in Asia, are more expensive than others such as Northern Virginia. Ask why multiple regions are necessary and use this insight to guide further optimization. AWS Cost Explorer is a powerful built-in tool for managing your cloud finances on Amazon Web Services. It helps you analyze costs, spot trends, and identify major cost drivers in your environment, all at no extra charge for basic use. To access Cost Explorer, head to your AWS billing dashboard and launch the tool. You'll see a menu that lets you explore costs grouped by service, with a default 6-month overview displayed as a bar chart for easy comparison. You can adjust the time frame to view costs daily, monthly, or even forecast future spending. Use filters to focus on specific regions, services like EC2, or even drill down to instance types. The data table below the chart provides detailed breakdowns, which you can export for deeper analysis. Enable hourly and resource-level data for more granular insights, noting that this incurs a small fee. Choose between unblended and amortized cost views to match your accounting needs, especially if you use reserved instances or savings plans. Leverage filters to isolate untagged resources or analyze API operations for services like S3. With these features, AWS Cost Explorer empowers you to optimize spending and make informed financial decisions in the cloud. The AWS Cost and Usage Report, or CUR, is the most essential tool for capturing your AWS billing data. This detailed CSV file records every aspect of your cost and usage data across all AWS resources, providing historical, by-the-hour insights that help you spot trends and make informed decisions. To start using the CUR, head to the AWS Management Console. On the billing dashboard, find the Cost and Usage Report option in the left menu. By default, it is disabled, so you will need to enable it and create a new report. Give your report a name and be sure to include resource IDs for unique tracking. Next, choose an Amazon S3 bucket to store your CUR files. You can select an existing bucket or create a new one, set a path, and pick your preferred time granularity. Remember, more granular data means larger files. You can also decide whether to create new report versions or overwrite existing ones. CUR files can be exported for use with Amazon Athena, Redshift, or QuickSight. Athena uses Parquet files for serverless SQL analysis, while Redshift and QuickSight use CSV files for big data queries and visual dashboards. Expect minimal S3 storage costs for your Kerr data. Before cloud computing, companies had predictable costs thanks to fixed procurement processes. Contracts were signed up front, and expenses were easy to track. But with the shift to the cloud, costs have become variable. While this brings speed and flexibility, it also makes it harder to understand and control spending. Now, application and finance teams must collaborate more closely to manage budgets effectively. To tackle these challenges, teams need to track usage, set budgets, and receive alerts when spending exceeds limits. AWS Budgets is designed for exactly this. It lets you monitor your Amazon Web Services, or AWS, usage and costs, set custom budgets, and get notified if you approach or exceed your budget. This helps both business leaders and engineering managers make informed decisions. With AWS Budgets, you start by defining what you want to track, such as cost, service usage, or coverage for savings plans and reserved instances. Next, you set your budget amount and decide which projects or services it applies to. For example, you might set a $100 monthly budget for all services. You can configure alerts at thresholds like 80% of your budget and choose notifications via email, simple notification service, or AWS chatbot. AWS Budgets can even automate actions such as changing permissions or stopping instances and generate reports for leadership to review. Understanding where your cloud budget goes is crucial. In Amazon Web Services, or AWS, cost allocation strategies help you track spending by resource and service. The key to this visibility? Tagging every resource in your cloud environment. Tags in AWS are simple key and value pairs attached to resources. For example, you might tag resources with environment, production, or service backend. These tags let you instantly see which resources belong to which business unit, project, or application. AWS offers the Cost and Usage Report, also known as Kerr. This report tracks your monthly costs and usage, breaking down data by product, usage type, and operation. Kerr files are stored in Amazon Simple Storage Service, or S3, and can be updated up to 3 times daily. Start tagging resources from the very beginning. Use clear, consistent tags that match your business needs. Avoid retroactively tagging resources, as it can be frustrating and confusing. Consider policies that require tags before deploying new resources. A well-planned tagging strategy makes cost allocation simple and insightful. Use AWS tools like Cost Explorer and Kerr for detailed analysis. Remember, effective tagging leads to better decisions and greater control over your AWS spending. Tagging your resources is essential for any organization looking to manage costs and streamline operations. By applying the right tags, you can easily track, allocate, and optimize your resources across different departments and projects. Some of the most widely used tags include cost center or business unit tags, which help allocate resource costs accurately. Service or workload name tags identify which service a resource belongs to, while resource owner tags clarify responsibility. Simple resource name tags make resources easier to recognize, and environment tags distinguish between development, testing, and production environments. Check your cloud provider for pre-generated tags like those offered by Amazon Web Services to save time. Start by aligning your tags with your overall cost allocation strategy. Tag every resource to avoid gaps in your data and ensure each tag serves a clear purpose. Limit the number of tags to avoid redundancy and keep things manageable. Consistency is crucial, so use clear, descriptive naming conventions for all tags. Automate tag management with tools like the Amazon Web Services Tag Editor to save time and enforce policies that prevent untagged resources. Regularly audit and maintain your tags, involving your entire team to ensure ongoing accuracy and improvement. AWS cost allocation tags are essential tools for tracking and managing your cloud spending. These special tags help you organize costs by project, department, or any custom category, making it easier to visualize and allocate expenses across your organization. To make the most of cost allocation tags, you need to activate them in the AWS billing section. Once activated, AWS detects all tag keys used in your account and suggests them for activation. Only active tags will appear in Cost Explorer charts and reports. For example, tags like Cost Center and Name can be enabled, while inactive tags are linked to resources no longer in use. Without activating these tags, you will not be able to filter or analyze costs by tag in Cost Explorer or other AWS services. There are two main types of cost allocation tags: user-defined and AWS-generated. User-defined tags are custom tags you create, while AWS-generated tags, such as created by, are automatically applied to resources for cost tracking. Both types are visible only in the AWS Billing and Cost Management console. To enable AWS-generated cost allocation tags, log into your master account as an IAM user with the right permissions. In the Billing console, select Cost Allocation Tags from the menu, then click Activate to enable the tags. AWS Systems Manager is a suite of fully managed services designed to automate configuration and ongoing management of your systems at scale. Whether your instances run on Amazon EC2, in your own data center, or on other cloud platforms, Systems Manager delivers secure, reliable operations. With Systems Manager, you can select which instances to manage and define the tasks you want to perform. Schedule modifications using maintenance windows, create and update system images, collect software inventory, apply patches, and configure both Linux and Windows operating systems. All of this can be done from a single console or through the command line interface, streamlining your workflow and reducing complexity. Forget about juggling multiple tools for different platforms. Systems Manager eliminates the need for secure shell keys, remote desktop ports, or Bastion host to connect to your instances. Its cloud-native design supports agility and elasticity, letting you manage one or thousands of instances, regardless of workload duration. Systems Manager integrates seamlessly with other AWS management tools, including Identity and Access Management for access control, CloudTrail for auditing, and CloudWatch events for automation, all without complex licensing. AWS Systems Manager empowers you to automate, maintain, and manage your entire infrastructure with complete visibility and control wherever your systems reside. AWS Systems Manager is designed to fit seamlessly into your existing Amazon Web Services configuration and management toolset. It offers a comprehensive solution for managing your cloud resources, making it easier to oversee operations across your entire environment. One of the standout features is the Systems Manager Explorer, a customizable operations dashboard. Explorer delivers a unified view of your operational data and work items, spanning all your accounts and regions. You can tailor the dashboard to your needs using drag-and-drop functionality and drill down into specific detail to prioritize tasks. This flexibility helps you stay organized and focused on what matters most. Explorer also enables you to take action quickly by using automated runbooks when necessary. Systems Manager integrates smoothly with your Amazon CloudWatch dashboards and your personal health dashboard, ensuring you have all the information you need in one place. With these capabilities, AWS Systems Manager empowers you to provision and operate your resources efficiently at scale, streamlining cloud management for your organization. AWS Systems Manager offers over 20 features and integrations, providing a unified dashboard to manage the lifecycle of your cloud instances. It helps you organize, monitor, and act on your AWS resources efficiently and securely. Some of the standout features include Fleet Manager, Session Manager, Run Command, Parameter Store, Patch Manager, and State Manager. These tools let you manage inventory, patch assets, run commands, and securely connect to Amazon Elastic Compute Cloud, or EC2, instances in private subnets. Most features use Systems Manager documents to define operations and maintenance windows to schedule them. You can select which instances to manage in 3 ways: manually, by choosing each instance, by using instance tags, where you specify tag key value pairs, or by leveraging resource groups, which let you operate on logical collections of resources. Resource groups are built using common tags and can represent development tiers, departments, or projects. They can also be based on CloudFormation stacks, mirroring the stack's logical structure for streamlined management. Tagging your resources is essential. With the Tag Editor and Tag Policy Editor, you can organize, enforce, and bulk edit tags, making resource management and visibility much easier across your AWS environments. AWS Systems Manager is a powerful service that helps you manage your cloud and on-premises infrastructure. To use its features, every server or virtual machine must become a managed instance, which means it can communicate with Systems Manager. The key to this communication is the Systems Manager Agent, or SSM agent. This software must be installed and configured on each instance. It comes pre-installed on Amazon Linux and AWS Windows images, and is available for other platforms like Ubuntu, Red Hat Enterprise Linux, SUSE, and CentOS. The SSM agent is open source and can even be installed on physical servers or virtual machines outside AWS. Each managed instance needs an Identity and Access Management, or IAM, role. AWS provides predefined policies such as the Amazon EC2 role for SSM to simplify setup. For non-EC2 servers, you can use hybrid activations to register and centrally manage them alongside your EC2 instances. Once configured, all managed instances appear in the Fleet Manager console. Here you can view details like instance ID, operating system, IP address, and SSM agent version. Session Manager lets you securely connect to instances without opening inbound ports or managing keys. It uses Transport Layer Security version 1.2, supports full session logging, and integrates with AWS security tools for auditing and access control. Once you have configured your managed instance with the Systems Manager agent and assigned the appropriate access role, you can access the Systems Manager console. Under the Node Management section, you will find the Fleet Manager feature, designed to simplify instance management. Fleet Manager displays all your managed instances in one place, providing visibility into key details such as instance ID, platform type, instance type, operating system name, IP address, and the version of the Systems Manager agent. This centralized view makes it much easier to monitor and manage your entire fleet. Within the same Node Management section, you will also see the Session Manager feature. Session Manager is a fully managed capability that allows you to connect to any managed instance using an interactive browser-based shell. It supports Linux, Windows, and macOS instances, making it a versatile tool for administrators. Session Manager does not require open inbound ports, bastion hosts, or the management of SSH keys. You also do not need SSH or remote desktop clients. All communication is secure, and every command and output can be tracked and dispatched to CloudTrail, CloudWatch, or Amazon S3 for auditing. AWS Systems Manager Run Command is a powerful tool that lets you execute commands across one or more of your managed instances. Whether you need to automate routine tasks or perform complex administrative actions, Run Command streamlines the process, making management at scale much simpler. To use Run Command, you start by selecting a Systems Manager document. These documents, written in JSON or YAML, define the actions to be performed on your instances. You can use pre-built documents like the popular AWS Run Shell script or create your own. Documents are reusable and can accept parameters, allowing you to tailor commands for different scenarios. When executing a command, you specify both the document and the target instances. For large environments, Run Command offers rate control. This feature lets you set concurrency, determining how many instances receive the command simultaneously, and an error threshold, which stops execution if failures exceed your set limit. Run Command provides flexible output options. You can direct command results to an Amazon S3 bucket or Amazon CloudWatch logs. Additionally, you can configure notifications through Amazon's Simple Notification Service, or SNS, to stay updated on command status and results. AWS Systems Manager Parameter Store is a centralized solution for managing your application configuration and secrets. Whether you need to store plain text data like database connections or sensitive information such as passwords, Parameter Store provides a secure and organized way to handle it all. One of the standout features is its integration with the AWS Key Management Service, or KMS, which allows you to automatically encrypt sensitive values. This means your secrets are protected without extra effort. Parameter Store also enhances security by separating configuration data from your code, and it offers integrated audit capabilities through AWS CloudTrail. This lets you track who accessed or changed your parameters, adding an extra layer of accountability. Parameters can be tagged and organized into hierarchies, making it easy to manage different environments like development, quality assurance, and production. You can track changes using parameter versions, set up notifications for updates, and even create custom validation routines using AWS Lambda functions. Parameter Store is not limited to AWS Systems Manager. You can reference parameters in services like Amazon Elastic Container Service, AWS Lambda, CloudFormation, Code Deploy, Code Pipeline, and your own applications. Simply create a parameter, specify its type and value, and reference it wherever needed. In Amazon Web Services, or AWS, maintenance windows are a powerful way to schedule potentially disruptive administration tasks. Instead of running updates or patches manually, you can automate these actions to occur during a specific, predefined period, minimizing impact on your workloads. A maintenance window is an independent resource in AWS. To set one up, you define a schedule that specifies exactly when tasks can run. You can choose a start and end time, or use cron or rate expressions for recurring schedules. You also set the duration in hours, ensuring tasks only run within your chosen window. Once the window is created, you register targets by name, using instance tags, resource groups, or by selecting instances manually. With your maintenance window in place, you can register tasks to run. These might include run command documents, automation document tasks, Lambda function tasks, or step functions tasks. You can also set limits for how many tasks run simultaneously and the allowable error rate. AWS keeps a history of all executed tasks for easy review. Maintenance windows help you avoid operational downtime by grouping disruptive tasks into controlled periods. This flexibility ensures your systems stay updated and secure without unexpected interruptions. Systems Manager is a suite of services designed to help you manage your computing instances securely and efficiently, no matter how many you have. It brings together all your operational data, giving you a unified view for performance and compliance. To take full advantage of Systems Manager, your machines need to become managed instances. A managed instance is any machine that can communicate with Systems Manager and meets a few essential requirements. This setup allows you to securely connect, collect inventory, and automate tasks. First, you must install and configure the Systems Manager agent on each machine. This agent processes tasks you specify, such as running commands or collecting data. Second, each instance needs a role with the right permissions. You can use the Amazon EC2 role for Systems Manager or the Amazon SSM Managed Instance Core policy to define these permissions. Third, your instance must have network access to the public Systems Manager endpoint. This is achieved through an internet gateway for public subnets or a virtual private cloud endpoint for private subnets. With these 3 steps, your instances are ready for Systems Manager, enabling secure, centralized management across your entire fleet. Systems Manager documents are a key part of how AWS Systems Manager operates. These documents define the steps and parameters for actions you want to perform, and they are written in either JSON or YAML. They act as independent resources within the Systems Manager ecosystem. Systems Manager supports over half a dozen document types, but the most common is the command document. Command documents are essential for the Run command feature, which lets you specify exactly what actions to execute on your managed instances. They are also used by the State Manager to apply configurations and by maintenance windows to schedule tasks. With a command document, you can run shell scripts, configure CloudWatch, set up Docker, or perform other administrative tasks on your instances. These documents are versatile and can be tailored to fit a wide range of operational needs, making them a powerful tool for automation. There are more than 100 pre-configured Systems Manager documents available. You can use them as they are or modify them to suit your requirements. Common examples include AWS Run Shell scripts for Linux and AWS Run PowerShell script for Windows. AWS Systems Manager is a powerful tool for managing your cloud infrastructure. Let us explore some of its key features that help you control, automate, and secure your instances. With Fleet Manager, you get a centralized view of all your managed instances. This feature provides detailed visibility into each instance, making it easy to monitor and manage your entire fleet from one console. Session Manager allows you to connect securely to any managed instance using an interactive browser shell. There is no need for open inbound ports, bastion hosts, or SSH keys. All sessions are tracked for auditing and compliance, ensuring secure and accountable access. Run command lets you execute commands on one or multiple instances at once. You define the actions using command documents, control how many instances are updated simultaneously, and set error thresholds to pause execution if issues arise. Parameter Store separates configuration data from code. It securely stores plain text data and secrets, integrates with the AWS Key Management Service, and supports versioning, notifications, and validation routines using AWS Lambda functions. Maintenance windows let you schedule tasks like patching or software updates during predefined periods, minimizing downtime and ensuring your applications remain available while critical maintenance is performed. Managing patches across your servers can be complex, but Patch Manager, a feature of AWS Systems Manager, streamlines the process. It automates patching for both security and reliability, keeping your managed instances up to date and secure. Patch Manager supports a range of operating systems, including Amazon Linux, Ubuntu Server, and Windows Server. You can scan your managed instances to identify missing patches or let Patch Manager automatically install them. It also generates patch compliance reports, so you always know where your systems stand. Patches are defined using patch baselines. AWS provides predefined baselines for each supported operating system, but you can create custom baselines for more control. Organize your patching strategy with patch groups using a case-sensitive tag key, patch group. Assign values like web servers or app servers to target specific environments or application tiers. Patch Manager integrates with AWS CloudTrail, Amazon EventBridge, Amazon S3, AWS Config, and AWS Identity and Access Management. This allows you to gather patch data and send it to other AWS services, supporting compliance and audit requirements. Schedule patches during maintenance windows to minimize disruption. Use Systems Manager documents like AWS Run Patch Baseline and AWS Configure Windows Update for flexible, automated patching across your fleet. State Manager is a secure and scalable configuration management feature within Systems Manager. It gives you control over how configurations are applied across your managed instances, whether you are adjusting firewall settings, shutting down unused ports, or disabling unnecessary services. With State Manager, you define policies using automation documents, including several predefined options for common scenarios. These policies are assigned through an association, which specifies what needs to be done, the target instances, and a schedule for when changes occur. For example, you can configure network settings or automatically install software modules at startup, ensuring your desired state is always maintained. State Manager supports configuration scripts in Shell, Ruby, and Python, and works seamlessly with existing tools like Ansible, Salt, or PowerShell. It can identify and repair compliant and non-compliant machines across multiple accounts. Integration with Amazon EventBridge enables event-driven automation, while outputs can be sent to CloudWatch logs or Amazon S3 for monitoring. All API interactions are logged in CloudTrail, providing a complete audit trail. Native integration with identity and access management lets you control who can access State Manager and run configuration tasks, ensuring enterprise-wide compliance and security. AWS X-Ray is a service that helps developers analyze and debug distributed applications, especially those built with microservices. With X-Ray, you can see how your application and its underlying services are performing, making it easier to identify and troubleshoot performance issues and errors. X-Ray provides an end-to-end view of requests as they travel through your application, mapping out all the underlying components. You can use it to review request behavior, discover application issues, and improve performance. X-Ray works seamlessly with other AWS services like Amazon EC2, AWS Lambda, and AWS Elastic Beanstalk, and supports popular programming languages such as Java, Node.js, and .NET. X-Ray traces user requests, aggregates data from different services, and lets you visualize relationships and latency between components. You can even tag and filter trace data to diagnose issues faster. To get started, simply launch a sample application from the X-Ray console using a provided CloudFormation template. Within minutes, you'll see real-time request data and performance insights. Amazon Athena is now included in the AWS Certified Developer Associate exam. So let's take a quick look at what this powerful service offers and how it can help you analyze your data. Amazon Athena is a fully managed serverless service that lets you interactively query data stored in Amazon S3 data lakes, as well as other sources like data warehouses and big data repositories. You use standard structured query language, or SQL, so there's no need to learn a new language. Athena is designed to handle datasets up to petabytes in size, and you only pay for the queries you run. Athena uses data definition language, or DDL, to define tables and supports a variety of file formats, including CSV, JSON, and Parquet. You can specify partition keys to efficiently query large datasets by any column. Athena integrates with services like Elastic MapReduce, or EMR, AWS Glue, QuickSight, and Redshift Spectrum, making it easy to build analytics pipelines. It also supports querying data in S3 compressed, helping reduce storage costs. You can interact with Athena using AWS software development kits, the AWS API, or ODBC and JDBC drivers, making it accessible for developers. That's a quick introduction to Amazon Athena. Good luck on your certification journey. Amazon Kinesis Data Firehose is a fully managed service designed to simplify the process of delivering streaming data to various destinations. It handles all the infrastructure, storage, and networking, so you do not need to worry about provisioning or maintaining hardware or software. Kinesis Data Firehose can collect, transform, and load large datasets to destinations like Amazon S3, DynamoDB, Amazon Redshift, OpenSearch, Splunk, and more. It automatically scales to handle your data volume and replicates data across 3 facilities within a region for durability. You can send data to Firehose from Kinesis data streams or directly from any application, making it flexible for different use cases. Firehose buffers incoming data based on size or time before delivering it. For example, buffer sizes range from 1 megabyte to 128 megabytes for Amazon S3, and buffer intervals can be set from 60 to 900 seconds. Firehose does not use shards and is fully automated for scalability, ensuring seamless data delivery. Firehose can compress and encrypt data and optionally back up transformed data to another Amazon S3 bucket. The Kinesis agent, a Java application, can be installed on Linux or Windows systems to collect and send data, making integration straightforward for web, log, or database servers. Amazon OpenSearch Service is a fully managed search service from Amazon Web Services, or AWS. It is the successor to Amazon Elasticsearch Service and lets you deploy OpenSearch clusters with ease. OpenSearch itself is an open-source search, analytics, and visualization suite created by Amazon, based on Elasticsearch and Kibana. If you are familiar with the ELK stack, which stands for Elasticsearch, Logstash, and Kibana, you will find OpenSearch very approachable. With OpenSearch, you can index and search large collections of data, making it ideal for website search, real-time application monitoring, and interactive log analytics. OpenSearch supports both Elasticsearch and OpenSearch application programming interfaces, or APIs, so adding custom search features to your applications is straightforward. It also integrates with visualization tools like Kibana and OpenSearch dashboards. For high availability, you can deploy OpenSearch clusters across 2 or 3 availability zones. OpenSearch can ingest streaming data from Amazon CloudWatch logs, Kinesis Data Firehose, and other AWS services such as S3 and DynamoDB. OpenSearch offers tiered storage, including hot, ultra-warm, and cold storage tiers, providing cost-effective options for both frequently updated and archived data. There is also Amazon OpenSearch Serverless, which lets you run OpenSearch without managing clusters. You pay only for the resources you use, with data durability similar to Amazon S3. Amazon OpenSearch Service is now included in the AWS Certified Developer Associate and AWS Certified DevOps Engineer Professional exams. Good luck on your certification journey. Amazon Managed Grafana is a fully managed service from Amazon Web Services, or AWS, built on the open-source Grafana analytics and visualization platform. With this service, you can harness Grafana's powerful data visualization and operational dashboarding capabilities without the hassle of provisioning infrastructure or installing software. With Amazon Managed Grafana, you can create workspaces, which are logically isolated Grafana servers. Each workspace can connect to a variety of data sources, including Amazon Cloud Watch, AWS X-Ray, the Amazon Managed Service for Prometheus, and Amazon TimeStream. You can create multiple workspaces per account within the same AWS region, making it easy to organize and manage your monitoring environments. The service also integrates with AWS organizations, giving you a comprehensive view across your AWS accounts and resources within your organizational units. Access management is streamlined through AWS Single Sign-On, or SAML. You can assign users administrator, editor, or viewer privileges. Administrators manage data sources, users, teams, folders, and dashboards. Editors can work with dashboards and alerts, while viewers have read-only access to assigned dashboards. If you need more advanced features, you can upgrade your workspace to Grafana Enterprise. This unlocks additional third-party plugins, as well as support and training from Grafana Labs. Amazon Managed Service for Prometheus is a powerful, serverless solution designed to monitor container metrics at scale. It is now included in the AWS Certified DevOps Engineer Professional exam, making it essential knowledge for candidates. This service is fully compatible with Prometheus, the popular open-source systems monitoring and alerting toolkit. With Amazon Managed Service for Prometheus, you do not need to provision or manage any infrastructure. It automatically scales as your containerized workloads grow or shrink, ensuring seamless performance. The service also provides multi-availability zone deployments for high availability. Any data ingested into a Prometheus workspace is automatically replicated across 3 availability zones within an AWS region, offering robust data durability and resilience. Amazon Managed Service for Prometheus can monitor applications running on Amazon Elastic Container Service, Amazon Elastic Kubernetes Service, AWS Fargate, and even self-managed Kubernetes clusters on premises or in other clouds. It supports the Prometheus query language, or PromQL, so you can filter and aggregate metrics without writing code. Integration with Amazon Managed Grafana enables advanced monitoring, alerting, and dashboards. This overview highlights the key benefits of Amazon Managed Service for Prometheus. Good luck as you prepare for your AWS certification journey. Security and compliance. Identity and Access Management, or IAM, is a crucial service that helps you manage who can access your AWS resources and what they can do. Let's break down what IAM really means and how it works. Identity management is the first part of IAM. It's all about defining and managing identities, such as AWS usernames. When you log in, you present your unique identity, like your AWS username. IAM ensures that each username is unique within your AWS account, so you cannot have 2 users with the same name. After presenting your identity, you verify it by providing a password. Access management focuses on authorization. Once your identity is authenticated, IAM determines what you are allowed to do. For example, you might have full access to Amazon EC2, or read-only access to Amazon RDS. These permissions control which AWS resources you can use and how. Access control is about how you access secured resources. This can include using a username and password, enabling multi-factor authentication, or using federated access, which lets external users access AWS resources securely through identity providers. Understanding IAM's authentication and authorization controls is essential for designing secure AWS infrastructure and protecting your resources effectively. AWS Identity and Access Management, or IAM, is the backbone of security and access control in your Amazon Web Services account. Without IAM, you cannot manage who or what can access your resources, making it essential for any cloud environment. IAM lets you create user objects for individuals or applications, each with a unique Amazon resource name, or ARN. You can group users into user groups, assign permissions with policies, and set up roles for temporary access. Multi-factor authentication, or MFA, adds an extra layer of security, especially for privileged users. Federated access allows external identities, like those from Active Directory or Google, to authenticate without creating separate IAM users. Policies written in JSON define what users, groups, or roles can access. Use AWS managed policies for common needs, or create customer-managed and inline policies for custom requirements. Always enforce a strong password policy and adopt AWS's recommended security best practices to protect your environment. Access Analyzer highlights risky external access, while Credential Reports help you audit user credentials. Service Control Policies, or SCPs, set permission boundaries across AWS accounts in AWS organizations. AIM security is only as strong as your configuration. Take ownership and architect your access controls carefully. When you create a new Amazon Web Services account, it automatically generates an AWS account root user. This root user is the original account and has complete, unrestricted access to every resource and feature in your AWS environment. Think of it as the ultimate administrator. The root user's power comes with significant responsibility. Any resource you create is accessible by this user, making it essential to use the root account with extreme caution. Security restrictions and careful management are critical to protect your AWS environment from accidental or malicious changes. While an Identity and Access Management, or IAM, user can handle most administrative tasks, some actions are exclusive to the root user. These include changing account settings, enabling the AWS IAM Identity Center, registering as a seller in the reserved instance marketplace, activating IAM access for billing, closing your account, joining AWS GovCloud, restoring lost permissions, and activating multi-factor authentication delete on S3 buckets. To protect your AWS account, only use the root user for these specific tasks. Always secure it with a strong password and enable multi-factor authentication. For all other administrative actions, use an IAM user with administrator privileges to minimize risk. Creating a new user in AWS Identity and Access Management, or IAM, is a straightforward process using the AWS Management Console. Let's walk through the essential steps to get your user up and running. First, navigate to the IAM dashboard under Security, Identity, and Compliance. Click on Users, then select Add Users. Enter a username, which can be up to 64 characters. Next, choose the access type: programmatic access for tools like the AWS command line interface, or AWS Management Console access for web login. You can select one or both. For console access, set a password, either auto-generated or custom. You can require the user to change their password at first login for added security. Assign permissions by adding the user to groups, copying permissions from another user, or attaching policies directly. For example, you might add the user to groups like Cloud Academy or RDS Full Access. Optionally, add tags for organization. Review all settings, then create the user. Download the CSV file containing the username, access key ID, secret access key, and console login link. Remember, you only get one chance to save these credentials. That's it. Your new IAM user is ready with the right access and permissions securely set up in just a few minutes. Managing IAM users in the Identity and Access Management dashboard lets you fine-tune security and access for each user. Let's walk through the key features you can adjust after creating a user. Start by selecting a user to view their summary. Here, you'll see details like their Amazon resource name and creation time. Under the Permissions tab, you can review which policies are attached, such as Amazon S3 Full Access or Amazon Relational Database Service Full Access. You can also set a permissions boundary to limit the user's maximum permissions or generate a custom policy based on their activity using CloudTrail events. In the Security Credentials section, you can manage passwords, enable or disable console access, and set up multi-factor authentication or MFA. Options include a virtual MFA device, a universal second factor security key, or a hardware device. For example, you can use the Google Authenticator app to quickly assign a virtual MFA device for added security. You can view, deactivate, or create new access keys for programmatic access. Tags can also be added, like specifying a location to help organize users. Finally, the Access Advisor shows which services the user can access and when they last used them, helping you keep permissions up to date. IAM user groups in Amazon Web Services, or AWS, are a powerful way to manage permissions from multiple users at once. Rather than assigning policies to each user individually, you can group users by job role or requirement and attach policies directly to the group. To create a user group, simply log in to your AWS Management Console and navigate to the IAM dashboard. Click on User Groups, then select Create Group. Give your group a meaningful name like Developers or My S3 and EC2 Group. Next, add existing IAM users to the group. And finally, attach the necessary permissions using AWS Managed, Customer Managed, or Inline policies. Once your group is created, you can easily add or remove users at any time. To update permissions, just attach or remove policies from the group. For example, if your developers need access to Amazon S3 and EC2, attach the Amazon S3 and EC2 full access policy. If they later need RDS access, simply add the RDS full access policy. Remember, each AWS account supports up to 300 groups, and each user can belong to up to 10 groups. For efficient management and security, always assign permissions to groups rather than individual users. In Amazon Web Services, or AWS, an IAM role is a special identity that lets trusted users, services, or applications temporarily access your AWS resources. Unlike a user, which is tied to a single person, a role can be assumed by different entities as needed. When a role is assumed, AWS generates a unique set of temporary credentials for that session. This means there are no long-term passwords or access keys associated with the role. Each time a user, service, or application needs access, they receive new credentials that expire after the session ends, making roles ideal for secure, short-term access. Every IAM role has policies attached that define what resources can or cannot be accessed. Additionally, each role has a trust relationship, which specifies who or what is allowed to assume the role. This could be a user, another AWS account, or an AWS service. IAM roles are commonly used to grant temporary access to users, allow cross-account access, let AWS services act on your behalf, or enable applications to access resources without embedding credentials. Roles can be assumed by users in the same or different AWS accounts, AWS services like EC2, or external federated users. AWS service roles are a powerful way to let AWS services access other resources in your account, securely and efficiently. Instead of managing credentials manually, you can assign roles to services like Amazon EC2 for seamless access. Imagine you have an EC2 instance running an application that needs to interact with Amazon's Simple Storage Service, or S3. Rather than embedding credentials in your code, you assign an Identity and Access Management, or IAM role to the instance. This role contains permissions for the actions your application needs, like putting or getting objects from S3. Assigning roles means you do not have to rotate or manage credentials on every instance, reducing administrative overhead and security risks. If you need to change permissions, simply update the role, and all associated instances are updated instantly. Some AWS services require very specific permissions. For these, AWS provides service-linked roles, which are created automatically and come pre-configured with the exact permissions needed. For example, AWS Systems Manager uses the AWS service role for Amazon SSM role to manage resources on your behalf. Service roles let you customize permissions, while service-linked roles are tightly controlled and specific to each service. Both approaches help you manage access securely and efficiently within AWS. Sometimes you need to grant someone temporary access to Amazon Web Services resources. The best way to do this is by letting them assume a role with the necessary permissions instead of attaching policies directly to users. Attaching policies to individual users is not a security best practice. Adding permissions to a user group can also be risky, since everyone in that group would get the same access. Roles provide a safer, more targeted solution. Start by creating a new role in the AWS Identity and Access Management dashboard. Choose your own account as the trusted entity and attach the required permissions, like full access to Amazon's Simple Storage Service. Update the trust relationship so only the specific user, such as Stuart, can assume this role. Next, add an inline policy to the user, Stuart, allowing him to use the Secure Token Service Assume Role action for the new role. This gives him permission to temporarily take on the role's access. When Stuart needs access, he simply switches roles in the console. Once finished, he can switch back, restoring his original permissions. This keeps access secure and temporary. Federation in Amazon Web Services, or AWS, lets users from outside your AWS account securely access resources without creating separate AWS users. This is done by establishing trust between an identity provider and AWS as the service provider. With Web Identity Federation, users authenticate through external providers, like Google or Facebook. For example, a mobile app storing photos in Amazon S3 can let users sign in with their social accounts. Instead of embedding long-term credentials, the app exchanges the user's authentication token for temporary AWS credentials using the Assume Role with Web Identity Application Programming Interface, or API. This is secure and scalable. SAML 2.0, or Security Assertion Markup Language, is often used by organizations to let employees access AWS using existing directory services, like Microsoft Active Directory. Employees authenticate internally, and SAML assertions are sent to AWS Security Token Service, or STS, to assume roles with specific permissions. This approach reduces administrative overhead and enables single sign-on. Both methods use temporary credentials mapped to AWS Identity and Access Management, or IAM, roles. These credentials grant only the permissions needed and expire automatically, enhancing security. Federation in AWS streamlines access, improves security, and simplifies management, whether for app users worldwide or employees in your organization. When working with AWS Identity and Access Management, or IAM, understanding the 4 main policy types is essential for managing permissions securely and effectively. Identity-based policies are attached to users, groups, or roles. These policies control what actions those identities can perform. There are 2 types: managed policies, which can be reused across multiple entities, and inline policies, which are unique to a single user, group, or role. Managed policies come in 2 forms: AWS managed policies, pre-configured by AWS, and custom managed policies, which you create for custom needs. Resource-based policies are attached directly to resources, like Amazon S3 buckets or IAM roles. These policies specify which principals can access the resource and what actions they can perform. For example, an S3 bucket policy defines who can access the bucket and under what conditions. Permission boundaries set the maximum permissions a user or role can have. They do not grant permissions themselves, but act as a limit. For instance, even if a user has full S3 access, a permission boundary can restrict them to read-only access. Service control policies, or SCPs, are used with AWS organizations. They define the maximum permissions for accounts or organizational units, overriding individual identity permissions. Understanding these policy types helps you manage AWS IAM permissions with clarity and control. IAM policies are the backbone of access control in AWS, defining exactly what identities can or cannot do. But what is their structure, and how do you read them? IAM policies are written in JSON, or JavaScript Object Notation. Each policy contains at least one statement, enclosed in curly braces. If there are multiple statements, they are grouped in square brackets. The policy always includes a version, which specifies the language syntax, with the current version being 2012-1017. Each statement can include several elements: SID, an optional statement ID; effect, which is either allow or deny; action, specifying the API calls permitted or denied; resource, identifying the AWS resource using an Amazon resource name, or ARN; and condition, which sets criteria for when permissions apply. For resource-based policies, you'll also see principal, defining who the policy applies to. Alternatives like not action or not resource can help simplify or restrict permissions further. For instance, a policy might allow full CloudTrail access only from a specific IP range, or grant a user named Stewart permission to manage an S3 bucket, but only if authenticated with multi-factor authentication. Creating IAM policies in Amazon Web Services, or AWS, is essential for managing permissions securely. Let us quickly explore 3 straightforward ways to create your own custom-managed IAM policies using the AWS Management Console. First, you can copy an existing AWS managed policy. In the IAM dashboard, select Create Policy, then Import Managed Policy. For example, import Amazon S3 Full Access. Switch to the JSON tab and update the resource to your specific Amazon resource name, or ARN. After reviewing, name your policy and create it. This method is efficient for tweaking existing policies to fit your needs. Second, try the AWS Policy Generator. Visit the Policy Generator website, select IAM Policy, and use drop-downs to choose services, actions, and resources. Add statements as needed, then generate the policy in JSON format. Copy this into the IAM Console's JSON tab, review, name, and create your policy. This tool simplifies policy creation without needing to write JSON manually. Finally, you can build a policy from scratch. Use the visual editor or write JSON directly in the IAM console. Select services, actions, resources, and conditions, then review and create your custom policy. Recap. These three methods make creating IAM policies in AWS flexible, efficient, and accessible for all skill levels. Every time someone tries to access a resource in Amazon Web Services or AWS, the process begins with authentication. AWS first checks that the person or application making the request is a valid, authenticated user. Next, AWS determines the context of the request, such as which service or action is being requested. This step ensures that only relevant policies are considered for the specific request. Now comes the heart of the process: policy evaluation. By default, all access to AWS resources is denied. Access is only granted if a policy explicitly allows it. However, if any policy explicitly denies access to a resource, that deny will always override any allow for the same resource and action. AWS evaluates policies in a specific order. First, organizational service control policies, then resource-based policies, followed by IAM permission boundaries, and finally, identity-based policies. Each step checks for explicit deny or allow statements that affect the request. For example, if a user named Steward requests to upload an object to an S3 bucket, AWS checks each policy type in order. If no deny is found and an allow exists, Steward's request is permitted. Remember, explicit deny always wins over allow, and the evaluation order matters. Understanding this process helps ensure secure and effective access control in AWS. Cross-account access in Amazon Web Services, or AWS, lets identity and access management users from one account access resources in another account using roles. This approach is essential for organizations that separate environments, like development and production, into different AWS accounts for better management and security. The process relies on two terms: the trusted account, which requests access, and the trusting account, which grants it. Instead of creating extra user accounts in sensitive environments, you grant temporary permissions through roles, following the principle of least privilege. To set up cross-account access, first, create a role in the trusting account, such as production. Define the trusted account as an entity allowed to assume this role and assign the necessary permissions like EC2 full access. Then, in the trusted account, grant users permission to assume the role. Finally, test by switching roles to confirm access. For example, a developer in the development account can assume a role in the production account to launch an EC2 instance, but only with permissions specified by the role. This keeps environments isolated and secure. Adding multi-factor authentication strengthens security. Cross-account access streamlines management while protecting critical resources. AWS IAM Identity Center is a service designed to simplify how organizations manage user access across multiple Amazon Web Services accounts and cloud applications. It acts as a central hub, making it easier to control authentication and permissions for your workforce. With IAM Identity Center, you can manage workforce identities, which are your employees or users, from a single location. These identities can be created directly in the service or synchronized from existing sources like Microsoft Active Directory or Okta. This centralization streamlines security, especially for organizations using several Amazon Web Services accounts. Application assignments allow you to grant single sign-on access to cloud-based applications such as Microsoft Office 365 and Salesforce, as well as custom SAML 2.0 enabled apps. Multi-account permissions let you centrally control access across all your Amazon Web Services accounts, eliminating the need to duplicate permissions in each account. To use IAM Identity Center, you must connect it to your Amazon Web Services Organization Management account. This integration enables centralized management of users, groups, and permissions, providing a customizable access portal for your workforce. In short, IAM Identity Center offers a seamless, secure, and efficient way to manage access for your workforce across multiple Amazon Web Services accounts and cloud applications, all from one place. To implement IAM Identity Center across your AWS infrastructure, start by reviewing your current identity sources, like Active Directory or other external providers. Syncing existing users saves time and avoids duplicating identity management. Also, ensure AWS Organizations is enabled, as IAM Identity Center requires it. If AWS Organizations is not already set up, enable it during the initial configuration. For environments using web filtering or secure gateways, add required AWS Identity Center URLs and DNS domains to your allow lists to ensure seamless operation. Next, log in to your AWS management account as the root user. Open IAM Identity Center and enable the service. Define your identity store. Choose between the default Identity Center, Active Directory, or supported external providers like Azure Active Directory, CyberArk, or Okta. Configure permission sets for your AWS accounts. Start with the predefined Administrator Access Permission set, which grants full access to AWS services. Permission sets act as templates, simplifying role-based access control across multiple accounts. Assign permission sets to users or groups from your chosen identity store. If using the default store, create users directly in IAM Identity Center. Associate permissions to grant appropriate access. Users sign in through the AWS Access Portal for single sign-on. Always enable multi-factor authentication for enhanced security, especially for administrative roles. Permission sets in IAM Identity Center are essential for managing access levels for your workforce users. They define what resources users can access, ensuring everyone has the right permissions for their job roles. When creating a permission set, you can choose from predefined templates like Database Administrator, Network Administrator, or Read-Only Access. These templates are tailored to common job roles. Alternatively, you can create a custom permission set for more flexibility, allowing you to specify exactly what permissions are needed. Predefined permission sets require only a name, optional description, session duration, relay state, and tags. Custom permission sets let you add up to 10 managed policies and 1 inline policy, with the option to set a permissions boundary for even finer control. Once created, permission sets appear in the console showing their name, description, unique Amazon resource name, and provisioned status. Provisioned means the set is in use, while not provisioned means it is not yet assigned. Assign permission sets to groups rather than individual users. This streamlines access management, making it easier to update permissions from multiple users at once and maintain security best practices.
Application assignments in AWS IAM Identity Center make accessing cloud-enabled applications seamless. By using the Access portal, users can enjoy single sign-on, meaning they only need to sign in once to access all assigned applications securely and efficiently. To get started, add your cloud applications to AWS IAM Identity Center. You can choose from a library of pre-integrated cloud applications or add a custom Security Assertion Markup Language 2.0 or SAML 2.0 application. Each option provides specific instructions to help you establish a secure trust between your application and IAM Identity Center. For example, if you select a pre-integrated application like Slack, you'll follow step-by-step instructions to configure it. You can customize the application's name and description, download the IAM Identity Center SAML metadata file and certificate, and adjust optional properties like the application's start URL or session duration. Once configuration is complete, assigning permissions is straightforward. Simply select the application, choose Assign Users, pick the groups or users who need access, and confirm. The application will now be available to those users in the Access portal. With everything set up, users can access their assigned applications directly from the IAM Identity Center Access portal, streamlining authentication and improving productivity.
IAM Identity Center offers a range of service-specific settings to help you manage access and security within your AWS organization. Let's break down the key options you'll find under the Settings section of the IAM Identity Center console. On the Settings page, you'll see details like the Amazon Resource Name, or ARN, of your IAM Identity Center instance, the region it's deployed in, and whether Identity Center applications are enabled in member accounts. These details help you understand where your Identity Center is running and how it's configured. You can also check if a delegated administrator account has been set, which is important for managing permissions. A delegated administrator account allows users in member accounts to manage IAM Identity Center, reducing the number of people who need access to your AWS management account. This helps minimize security risks by limiting high-level access. You can choose your identity source, such as the built-in Identity Center directory, Active Directory, or an external provider. Authentication settings let you enable one-time passwords and multi-factor authentication, adding extra layers of security for your users. Finally, the Management section lets you assign a delegated administrator or delete your IAM Identity Center instance. Be cautious. Deleting removes all users, groups, and permissions if you use the built-in identity store.
User authentication is one of the most frustrating parts of building any application, whether it is for mobile or web. Deciding who can access certain features is crucial, but setting up a secure system for this can be tedious and time-consuming. Traditionally, user information was stored in a standard user database. This could be hosted on-site or in the cloud, often as a relational database with tables for usernames and permissions. In the Amazon Web Services or AWS ecosystem, this meant using the Relational Database Service, known as RDS, or running your own database on EC2 instances. Managing these databases requires significant effort to set up and maintain. In corporate environments, employees' details are usually stored in directory services, like Microsoft Active Directory. No one wants to create yet another username and password just to use a new application. Amazon Cognito solves these pain points. It is a lightweight service that handles user authentication, allowing users to sign in with their existing corporate credentials. This means less hassle for users and less work for developers, making authentication much simpler and more secure.
Amazon Cognito is an authentication and user management service designed to simplify secure access for your applications. It integrates seamlessly with third-party identity providers like Apple, Facebook, Google, and Amazon, and even supports federation with your own Active Directory services. Amazon Cognito user pools are used to manage and authenticate users directly. They provide sign-up and sign-in functionality for your web and mobile apps, handling everything from user registration to password recovery, making it easy to manage users securely and efficiently. Amazon Cognito identity pools enable you to grant users access to AWS resources by federating identities from various providers, including your own Active Directory. Identity pools allow users to access external web and mobile applications securely and conveniently.
Amazon Cognito user pools make user management for your web or mobile app simple. They handle sign up and sign in, storing all user information securely in a dedicated directory, so you can focus on building your application. You can customize what information users provide at sign up, from emails to addresses or even custom attributes. Password policies are flexible, letting you require minimum lengths, numbers, or special characters. For added protection, Cognito supports multi-factor authentication, or MFA, which is highly recommended for apps handling sensitive data like financial or medical information. Cognito user pools allow users to sign in with social accounts, like Google or Facebook, after you set up developer accounts with those providers. You can also enable sign-in with SAML, or Security Assertion Markup Language, which is useful for single sign-on with enterprise identity providers. Cognito offers a customizable web interface for sign-in and sign-up, supporting OAuth 2.0 for secure authorization. You can also integrate AWS Lambda functions to trigger custom actions during user flows, such as sending welcome emails or preparing user environments. Cognito user pools remove authentication headaches, letting you focus on your app's core features. Simplify user management and security all in one place.
Let's break down how user authentication works with user pools and Amazon Cognito. Understanding this flow is key to building secure applications that protect user data and provide a smooth login experience. When a user wants to log in, your application presents a login screen or terminal. The user enters their credentials, either from an account they created or through a third-party provider. The application then calls the Initiate Auth operation, which signals to Amazon Cognito that authentication should begin. If the credentials are correct, Cognito may respond with either a token or a challenge. Challenges can include CAPTCHAs or dynamic questions designed to screen for bots and enhance security. You can even customize these challenges to fit your needs. The client must solve the challenge and respond using the Respond to Auth challenge operation. If the user fails, Cognito can issue new challenges, repeating the process until authentication succeeds or fails. Once the user successfully completes any required challenges, Cognito returns authentication tokens to the client. These tokens allow the user to access protected resources within your application, marking the end of a secure and efficient authentication flow.
Amazon Cognito identity pools, also called federated identities, are a powerful way to provide temporary access to Amazon Web Services credentials for your users or guests who need to interact with AWS services. Identity pools can be used alongside Amazon Cognito user pools, letting users access specific AWS features as needed. They also support federation with public identity providers like Amazon, Facebook, and Google, making it easy to integrate with popular platforms. Identity pools define two types of identities: authenticated and unauthenticated. Authenticated identities are users who have signed in using a public login provider, such as Amazon Cognito user pools, Apple, Facebook, Google, SAML, or OpenID Connect. Unauthenticated identities, on the other hand, are useful for scenarios like letting users preview AWS resources before logging in, or providing a guest pass to basic services, encouraging them to sign up later. Each identity type is assigned a role with specific policies that control what the user can see or modify within AWS. This ensures clear boundaries and secure access for both authenticated and unauthenticated users. Remember, identity pools manage authentication and access to AWS services, while user pools focus on sign-up and sign-in operations.
Let's break down how authentication works when using identity pools in your application. Understanding this process is key to securely connecting your users to the resources they need, whether they sign in directly or through a federated provider. First, your app has users sign in using Amazon Cognito user pools. This can be through the user pool itself, a social sign-in, or a SAML-backed authentication service. The identity provider, or IDP, sends an identity token to Cognito. Cognito then standardizes this into a Cognito user pool token, or CUP token, regardless of how the user authenticated. While CUP tokens work for many backend services like API Gateway or Lambda, some AWS services, such as Amazon S3 or DynamoDB, require a different approach. In these cases, your app needs to use an identity pool to authenticate and authorize access on behalf of the user. Your app sends the CUP token to the identity pool. The identity pool exchanges it for a security token service, or STS token. This STS token provides temporary AWS credentials linked to a specific AWS role. With these credentials, your application can securely access AWS services like S3 or DynamoDB, ensuring users have the right permissions every time they interact with your app.
AWS Identity Federation lets users access resources across different systems using a single set of credentials. This means you do not need separate logins for every service, making access simpler and more secure. Identity federation involves two parties: the identity provider, or IDP, which authenticates the user, and the service provider, or SP, which grants access based on that authentication. This trust relationship allows seamless access between systems. Think of logging into Medium using your Google or Facebook account. Here, Google acts as the identity provider, and Medium is the service provider. This process is called single sign-on, or SSO. AWS supports several identity standards, including OAuth 2.0, OpenID Connect, and Security Assertion Markup Language 2.0, or SAML 2.0. These standards enable secure, federated access for users and applications. Three main AWS services support identity federation: AWS Single Sign-On for managing access across multiple AWS accounts, AWS Identity and Access Management for configuring federated access per account, and Amazon Cognito for secure authentication in web and mobile apps. AWS Identity Federation streamlines access, reduces administrative overhead, and enhances security by leveraging trusted identity providers across your cloud environment.
Encryption is essential for protecting sensitive data. Unencrypted data, also called plain text or clear text, can be read by anyone with access. To keep information like customer records secure, encryption transforms this readable data into something unreadable. Symmetric encryption uses a single key for both encrypting and decrypting data. For example, if you encrypt a file with a key, you need that same key to decrypt it. This method is fast and efficient, but sharing the key securely can be risky. If someone intercepts the key, they can access your data. Common symmetric algorithms include Advanced Encryption Standard, or AES, Digital Encryption Standard, Triple DES, or Blowfish. Asymmetric encryption uses two keys, a public key for encryption and a private key for decryption. The public key can be shared openly, while the private key remains secret. If someone wants to send you an encrypted message, they use your public key. Only you can decrypt it with your private key. Algorithms like RSA, Diffie-Hellman, and digital signature algorithm are widely used. The AWS Key Management Service, or KMS, supports both symmetric and asymmetric encryption. It securely stores and manages keys, ensuring only authorized users can access decryption keys. Understanding these encryption methods is crucial for using AWS KMS to protect your sensitive data in the cloud. The Amazon Web Services Key Management Service, or AWS KMS, is a managed service designed to help you generate and store encryption keys. These keys are essential for protecting your data across many AWS services, like Amazon Simple Storage Service and Amazon Relational Database Service. AWS KMS offers several types of keys. Customer-managed keys are created and controlled by you, giving you full authority over their permissions. AWS managed keys are created by AWS services for specific integrations, while AWS owned keys are managed by AWS and used across multiple accounts. Data keys are generated by KMS for use outside the service, and HMAC keys allow you to create and verify hash-based message authentication codes. Importantly, AWS employees cannot access your keys, and if you delete them, they cannot be recovered. KMS is designed for encryption at rest, not for data in transit. For data in motion, you will need solutions like Secure Sockets Layer. KMS integrates with AWS CloudTrail, which logs key usage and helps you meet compliance and governance requirements. In short, AWS KMS provides a secure, centralized way to manage encryption keys, ensuring your data at rest remains protected across AWS services. Amazon Web Services Key Management Service, or AWS KMS, is a secure and fully managed service that helps you create and control cryptographic keys used to protect your data. Let's break down its key components and how they work together. KMS supports both symmetric and asymmetric keys. Symmetric keys use the same key for encryption and decryption and never leave KMS unencrypted. Asymmetric keys, on the other hand, use a public and private key pair. The public key can be shared, while the private key remains protected within KMS. There are three types of KMS keys: customer managed, AWS managed, and AWS owned. Customer-managed keys give you full control, including permissions, rotation, and deletion. AWS-managed keys are created and maintained by AWS for specific services, while AWS-owned keys are used internally by AWS. KMS can generate data keys for encrypting data outside of KMS. These keys can be symmetric and asymmetric, and their key material can originate from KMS, external sources, or be imported by you for greater flexibility. Key policies and grants define who can use or manage each key. Automatic key rotation is recommended for security, and KMS ensures previous key material is retained for decryption. This layered approach keeps your data secure and accessible. Securing your AWS Key Management Service, or KMS, keys is crucial for protecting sensitive data. Let us break down the essential methods to control access and keep your keys safe. KMS key policies are resource-based policies created within the KMS service. Each key has one policy written in JSON specifying who can administer, use, or grant temporary access to the key. Importantly, to use Identity and Access Management, or IAM, policies for access control, you must first allow this in the key policy itself. Without this, IAM permissions to allow access are ignored unless they explicitly deny access. Key administrators are users or roles defined in IAM who can manage the key but cannot use it for encryption or decryption. However, administrators can update the key policy, potentially granting themselves usage rights. Key users are specified in the policy and can perform cryptographic operations like encrypting, decrypting, or generating data keys. The same principle can be both an administrator and a user if needed. Grants allow temporary delegation of key permissions to other principals like users or roles without updating the key policy. Grants are created using KMS APIs and are often used by AWS services like Elastic Block Store or EBS. Always review your key policies, define administrators and users carefully, and use grants for temporary access to keep your KMS keys secure. Let's walk through creating a new customer-managed key management service key, or KMS key, using the AWS Management Console. This process helps you control encryption and access in your AWS environment. Start at the AWS Management Console dashboard. Head to the Key Management Service section. Here, you'll see both AWS-managed and customer-managed KMS keys. Click the orange Create Key button to begin. Choose your key type, symmetric or asymmetric. For most encryption and decryption needs, select symmetric. You can also decide if the key will be single region or multi-region, and set the key material origin. For this example, we'll use the default KMS origin and single region. Next, set an alias for your key, like new key. Define key administrators, such as specific IAM users or roles. Administrators can manage the key, but not use it for cryptographic operations. Then, assign key users who can perform cryptographic actions. By default, key users can also create grants. Review your settings, including the key policy, before finishing. Once created, you can view details, manage tags, enable key rotation, and edit the policy for customer-managed keys. Remember, disabling or deleting a key can make encrypted data unrecoverable, so proceed with caution. Understanding who can access an AWS Key Management Service key, or KMS key, can be tricky. Access is controlled through three main methods: key policies, identity and access management policies, or IAM policies, and grants. Let's break it down with a simple example. Imagine three KMS keys: Key A, Key B, and Key C. For users, Alana, Danny, Carlos, and Jorge each have different permissions set by key policies and IAM policies. Each key's policy and each user's permissions interact in unique ways. Alana can use Key A because her IAM policy allows all KMS actions, and Key A's policy permits IAM-based access. She cannot access Key B since its policy does not allow IAM permissions. But she can use Key C due to the key policy's explicit allowance. Danny can only use Key B as its policy grants him access directly. Carlos can encrypt with Key A via his IAM policy, use Key B through the key policy, but is denied Key C due to an explicit deny. Jorge is only allowed access to Key C, where he can perform cryptographic operations and create grants. Remember, explicit denies always override allows, and key policies determine whether IAM permissions are considered. Always review both policies for accurate access control. AWS Cloud HSM is a cloud-based hardware security module, or HSM service. An HSM is a physical, tamper-resistant device designed to protect cryptographic material and encryption keys, ensuring your sensitive data stays secure. Cloud HSM devices are validated to Federal Information Processing Standards, or FIPS, 140-2 Level 3. This level of security is often required for document signing or operating a public certificate authority for SSL certificates. Importantly, each Cloud HSM is a dedicated single-tenant appliance, meaning it is not shared with any other AWS customer. With Cloud HSM, you can create, store, and manage both symmetric and asymmetric cryptographic keys. It supports cryptographic hash functions, message authentication codes, data signing, signature verification, and secure random data generation. These features make Cloud HSM an enterprise-class solution for secure encryption key management and storage. Symmetric encryption uses one key for both encryption and decryption, while asymmetric encryption uses a public key to encrypt and a private key to decrypt. Common asymmetric algorithms include RSA and Diffie-Hellman. Symmetric algorithms include Advanced Encryption Standard, or AES. AWS also offers Key Management Service, or KMS, which uses managed HSMs but provides less direct control than Cloud HSM. Cloud HSM is Amazon's managed hardware security module service designed for secure key storage and cryptographic operations. At its core, Cloud HSM clusters group multiple hardware security modules, or HSMs, to act as a single, highly available unit across different availability zones within your virtual private cloud, or VPC. To deploy Cloud HSM, you start by creating a cluster and selecting subnets in various availability zones. Each HSM is linked to your VPC through an Elastic Network Interface, or ENI, which serves as a bridge between your network and the HSM residing in an AWS-owned VPC. This setup ensures both redundancy and seamless connectivity. When you create a cluster, Cloud HSM automatically generates a security group, Cloud HSM-cluster-cluster ID-SG, to control communication between HSMs and your resources. It also creates a service-linked role, AWS service role for Cloud HSM, enabling Cloud HSM to send logs to CloudWatch logs on your behalf. To interact with your HSMs, provision an EC2 instance in your VPC, add it to the security group, and install the Cloud HSM client software. Configure connectivity by copying your issuing certificate and specifying your HSM's IP address. Once everything is configured, activate your HSM cluster. Your infrastructure is now ready for secure cryptographic operations using Cloud HSM. Accessing AWS Cloud HSM is a bit different from other AWS services. While most resources use Identity and Access Management, or IAM, Cloud HSM relies on its own internal users and role-based access control. However, you still need IAM permissions to use the Cloud HSM service itself. Cloud HSM features several user types, each with specific responsibilities. When you first connect to your HSM cluster, you start with the Pre-Crypto Office, or Preco user. This temporary user has read-only access and must activate the cluster. Once you change the Preco password, it becomes the Crypto Office, or CO user. The CO user manages other users and can perform administrative tasks. Crypto users, or CUs, handle cryptographic operations like creating and managing keys, as well as encryption and decryption. Finally, the appliance user, or AU, is responsible for cloning and synchronizing HSMs within the cluster. Cloud HSM's hardware security modules include physical tamper detection. If tampering is detected, the device will delete all keys. The system also protects against brute force login attempts by locking out users after repeated failed logins. To sum up, AWS Cloud HSM uses its own user management system, with each user type playing a unique role in security and operations. Understanding these roles is essential for secure and effective Cloud HSM access. Let us explore how AWS KMS, or KMS, interacts with AWS Cloud HSM to provide flexible and secure encryption key management for your data in the cloud. By default, AWS KMS manages key stores using hardware security modules, or HSMs that are fully controlled by AWS. As a user, you do not have direct access to these HSMs, but you benefit from seamless integration with many AWS services. If your organization needs stricter compliance or more control, you can create a custom key store in KMS, backed by your own Cloud HSM cluster. This lets you manage your own HSMs, giving you full control over your cryptographic keys while still using KMS integrations. KMS creates Customer Master Keys, or CMKs. These can be managed by AWS or by you. When you manage them, you control key rotation, access, and policies, increasing flexibility and security. To set up a custom key store, your Cloud HSM cluster and KMS must be in the same region with at least 2 HSMs in different availability zones. You also upload a Trust Anchor certificate and create a dedicated crypto user for KMS operations. With AWS KMS and Cloud HSM, you can balance convenience, integration, and compliance for your encryption key management needs. AWS Cloud HSM provides robust monitoring and logging to help you manage your cryptographic hardware securely and efficiently. Let's explore how Cloud HSM integrates with Amazon CloudWatch, AWS CloudTrail, and CloudWatch logs for comprehensive visibility. Cloud HSM pushes key metrics to Amazon CloudWatch, a global service designed to monitor the health and performance of your AWS resources. Metrics include HSM unhealthy, HSM temperature, HSM session count, and network traffic indicators like interface ETH2 octets input and output. With CloudWatch, you can set alerts and notifications when thresholds are reached, enabling proactive responses to operational issues. AWS CloudTrail records all API calls related to Cloud HSM, whether they originate from the AWS Management Console, command line interface, or other AWS services. Each API request, such as Create HSM, is logged as an event in Amazon Simple Storage Service, or S3, along with metadata like the caller's identity and timestamp. Cloud HSM audit logs, generated by the Cloud HSM client daemon, capture every command executed on the HSM. These logs are automatically sent to CloudWatch logs, where you can monitor log streams in real time and set metric filters for specific events. Each log entry includes details such as event time, sequence number, reboot counter, command type, opcode, session handle, response, and log type, providing a complete audit trail for your Cloud HSM operations. AWS Secrets Manager is a service designed to help you protect sensitive information like database credentials, API keys, and plain text secrets. It streamlines security best practices by securely storing and managing these secrets within your Amazon Web Services environment. Traditionally, developers embedded credentials directly into applications, which made password rotation difficult and risky. With AWS Secrets Manager, applications can securely request credentials via an API, eliminating the need to hard code secrets. This also enables automatic credential rotation without updating application code. Secrets Manager encrypts secrets using the AWS Key Management Service, or KMS, which leverages hardware security modules validated under FIPS 140-2. You can choose between default, managed, or customer-managed encryption keys. Access is tightly controlled using both identity-based and resource-based IAM policies. Creating a secret is simple. Select your database, set credentials, choose an encryption key, and enable automatic rotation if needed. Secrets can be retrieved through the AWS Management Console, the AWS Command Line interface, or programmatically using AWS software development kits. AWS Secrets Manager centralizes secret management, supports cross-account sharing, and enhances your security posture with features like automatic rotation and region replication. It is a powerful tool for protecting sensitive data in the cloud. AWS offers two key services for managing sensitive information: the AWS Systems Manager Parameter Store and AWS Secrets Manager. Both help you avoid hard-coding credentials, boosting security and simplifying management. Parameter Store, part of AWS Systems Manager, or SSM, lets you centrally store parameters like environment variables, database strings, and passwords. Secrets Manager is designed specifically for sensitive secrets, such as database credentials and API keys, making them easy for applications to retrieve securely. Parameter Store allows encryption using the secure string option, but it is not enabled by default. Secrets Manager, on the other hand, always encrypts secrets by default using AWS Key Management Service, or KMS, and you cannot disable this protection. Parameter Store does not support automated password rotation. If credentials change, you must update them manually. Secrets Manager, however, can automatically rotate credentials for supported databases like Amazon RDS and Amazon Redshift using built-in Lambda functions. Parameter Store is versatile, storing both secret and non-secret values. Secrets Manager focuses on sensitive data and allows secure sharing of secrets between AWS accounts, which Parameter Store does not support. As your business grows on Amazon Web Services, or AWS, managing your cloud environment becomes more complex. That is where AWS organizations and service control policies come in, offering centralized control and security. Expanding businesses often need multiple AWS accounts. This multi-account strategy helps with cost optimization, billing, security, governance, and organizing workloads or business units as your organization scales. AWS Organizations lets you centrally manage and categorize all your AWS accounts under a single structure. Think of it as a family tree, bringing together your accounts for easier management, security, and compliance. The hierarchy starts with the root container at the top. Below that, organizational units, or OUs, group related accounts. Each AWS account has a unique 12-digit number. Service control policies, or SCPs, can be attached at any level to manage permissions. Setting up AWS organizations is straightforward and helps you manage multiple AWS accounts efficiently. Let us walk through the essential steps to get your organization up and running smoothly. Start by choosing a master AWS account. This account should be dedicated solely to managing your organization, not for provisioning resources. Limiting access to the master account enhances security as it holds administrative capabilities. Once you have your master account, navigate to AWS Organizations in the AWS Management Console. Click Create Organization. You can enable all features for advanced controls or select Consolidated Billing for centralized cost management. To add accounts, select Add Account. You can invite an existing AWS account by entering its email or account ID. The invited account owner will receive an email invitation to join your organization. After acceptance, the account becomes a member. Organize your accounts by creating organizational units, or OUs. For example, create production and test OUs, then move accounts into them for better structure and policy management. AWS Organizations simplifies account management. Remember, keep your master account secure and use OUs to streamline administration and apply policies efficiently. Service Control Policies, or SCPs, are a powerful tool in AWS organizations for setting permission boundaries across your accounts. Unlike identity-based or resource-based policies, SCPs do not grant permissions themselves. Instead, they define what actions are allowed or denied. Think of SCPs as guardrails. Even if a user has full access to a service through an identity-based policy, an SCP can restrict that access. For example, if an SCP denies Amazon S3, users cannot access S3 regardless of their other permissions. To use SCPs, you must enable them from your organization's root account in the AWS Organizations console. Once enabled, you can create policies and attach them to accounts or organizational units, setting boundaries for what services can be used. In a demonstration, a user named Alice had full S3 access via an IAM policy. After attaching an SCP that denied S3 to her account, Alice was blocked from S3, receiving an access denied error, despite her previous permissions. SCPs are inherited down the organizational hierarchy, combining restrictions from parent to child. They affect all users and roles, including the root user, but do not impact resource-based policies or service-linked roles. Disabling SCPs removes all restrictions. Managing multiple Amazon Web Services or AWS accounts is a best practice for separating workloads and allocating costs by business unit or team. However, as your organization grows, manually provisioning accounts and managing permissions can quickly become overwhelming. Ensuring security rules are followed and tracking logs across accounts adds even more complexity. AWS Control Tower is designed to simplify this process. It orchestrates over 14 AWS services, including AWS Identity and Access Management, or IAM, AWS Organizations, AWS Config, and AWS Trail Cloud, all from a single console. With Control Tower, you can automate the creation of new accounts, apply consistent security and compliance controls, and manage everything centrally. This means you no longer need to set up each service individually or worry about whether teams are following best practices. Control Tower also allows you to extend governance to existing accounts, making it easier to maintain oversight as your environment evolves. Control Tower provides centralized identity, access, account management, logging, and security. While there is no extra charge for using Control Tower itself, you will pay for the underlying AWS services it provisions, such as AWS Config for compliance. In short, AWS Control Tower streamlines multi-account management, automates provisioning, and ensures consistent governance across your AWS environment, making life much easier for administrators and security specialists. Let's break down the core concepts of AWS Control Tower, the service that helps you set up and govern a secure, multi-account AWS environment based on best practices. When you first access AWS Control Tower, you are prompted to create a landing zone. This is the foundation of your AWS environment, designed for security and compliance. The landing zone organizes all your accounts, users, and resources under a unified structure. AWS Control Tower uses AWS Organizations to set up your account structure. It automatically creates 3 organizational units: the root organizational unit, which is the parent, the security organizational unit, which contains shared accounts, and the sandbox organizational unit, where your team's accounts live. Within the security organizational unit, you get 2 key accounts: the log archive account, which stores all logs from every account, and the audit account, which gives security teams programmatic access for automated security operations and audits. Control Tower provisions a directory and IAM identity center, managing users and permissions. You can connect external identity providers like Azure Active Directory or Okta for seamless user access. Avoid deleting or modifying pre-configured resources, especially IAM roles, to prevent Control Tower from entering an unknown or broken state. When you set up your AWS Control Tower landing zone, it provisions not just accounts and identities, but also controls, sometimes called guardrails. These are high-level security rules that help you oversee and manage what users and resources can do in your environment. There are 3 main types of controls: detective, preventative, and proactive. Detective controls, like AWS config rules and AWS Security Hub checks, help you spot policy violations, such as public S3 access. Preventative controls, enforced through service control policies, block actions that could break your rules, like stopping changes to S3 bucket policies. Proactive controls use CloudFormation guard policies to scan resources before they are created, ensuring only compliant resources are provisioned. AWS offers over 400 controls, categorized as mandatory, strongly recommended, or elective. Mandatory controls, like enforcing logging, are always enabled. Strongly recommended controls enforce best practices, while elective controls let you further customize your security. You can find controls in the Control Tower console by control objective, AWS service, or compliance framework. This flexibility helps you tailor security to your organization's needs, ensuring continual oversight and compliance across your AWS environment. Once your AWS Control Tower landing zone is set up, you are ready to add accounts and manage your multi-account environment with greater control and efficiency. There are two main ways to add accounts manually using the AWS Control Tower console. You can create new accounts or enroll existing ones into your organization. Creating a new account is straightforward. Go to the Account Factory page, fill in details like the account email and organizational unit, then click Create. To enroll an existing account, select it from your organization list and click Enroll. Remember, your landing zone must not be in a state of drift, and you need the right permissions to enroll accounts. For automation, you have three options. First, use AWS Control Tower Account Factory for Terraform, or AFT, which provisions accounts through a pipeline triggered by a Git push. Second, Account Factory customization lets you use blueprints to predefine resources and controls, streamlining future account creation. Third, AWS Lambda functions can automate provisioning, though this method is more complex and may require adjustments for your needs. If you need to remove an account from Control Tower, simply unmanage it from the Account Factory page. This does not delete the account or user access. It just removes Control Tower oversight. With AWS Control Tower, you can efficiently manage, automate, and even unmanage accounts, giving you flexibility and control over your cloud environment. If you deliver web content through services like Amazon CloudFront, Amazon API Gateway, Application Load Balancers, or AWS App Sync, securing your applications is crucial. The AWS WAF, or AWS Web Application Firewall, adds an essential layer of protection against common web attacks. AWS WAF helps prevent threats like SQL injection and cross-site scripting, many of which are highlighted by the Open Web Application Security Project. The main building block of AWS WAF is the Web Access Control List, or WebACL, which determines which web requests are safe. Web ACLs contain rules and rule groups. Rules inspect requests based on specific criteria, allowing, blocking, or counting them. Rule groups are collections of rules, including AWS-managed groups and third-party options from the AWS Marketplace. When a user requests web content, AWS WAF filters the traffic using Web ACLs before it reaches your application. Harmful requests are blocked, and only safe traffic is allowed through, protecting your resources at the network edge. Implementing AWS WAF is faster and easier than traditional solutions, reducing risks and giving peace of mind to your security team. AWS Web Application Firewall, or AWS WAF, uses rules and rule groups within Web Access Control Lists, or Web ACLs, to inspect and control web traffic. These rules are essential for keeping your web applications secure and effective. You can add managed rule groups, which are sets of predefined rules created by AWS and third-party vendors like Fortinet and GeoGuard. For example, Fortinet's group protects against the Open Web Application Security Project Top 10 vulnerabilities, while GeoGuard helps detect IP fraud using geolocation. Each rule group has a capacity rating, measured in Web ACL capacity units, or WCUs, to manage resource usage. If you need more control, you can create your own rules. Options include IP sets, which filter traffic by IP address, and the rule builder, which lets you define logic using a visual editor or JSON. You can also create custom rule groups outside the Web ACL, set their maximum WCU capacity, and monitor them with CloudWatch metrics. Rules can allow, block, or count requests. Rule priority matters. Whitelisted IPs are allowed first, then blacklisted IPs are blocked, followed by rules for attack patterns like SQL injection. Rules execute in order, so plan carefully. AWS Firewall Manager is a security management service designed to simplify protection across multiple Amazon Web Services accounts. If you manage security for more than one account, this tool can help centralize and automate your efforts. With AWS Firewall Manager, you can create security policies that automatically apply protections to existing and newly created resources across your organization. It integrates with services like AWS Web Application Firewall, AWS Shield Advanced, AWS Network Firewall, Virtual Private Cloud Security Groups, and Amazon Route 53 Resolver Domain Name System Firewall. To use Firewall Manager, you must have AWS Organizations set up with all features enabled. AWS Organizations lets you centrally manage and categorize multiple accounts. You also need to enable AWS Config in every account and region where you want to manage resources. For certain protections, enabling sharing with AWS Organizations in AWS Resource Access Manager is required. First, designate a Firewall Manager administrator account within your AWS organization. Then, enable AWS Config, and if needed, sharing in Resource Access Manager. Finally, ensure all necessary regions are enabled in both your management and administrator accounts. Once configured, AWS Firewall Manager streamlines security management, making it easier to protect your entire AWS environment. AWS Firewall Manager is a security management service that lets you centrally configure and manage firewall rules across multiple AWS accounts. It uses policies to protect different resource types, each with its own configuration. You can create several policy types. AWS Web Application Firewall, or WAF policies, protect web applications from common attacks using Web Access Control Lists. Shield Advanced policies defend against distributed denial of service, or DDoS attacks. Network firewall policies secure virtual private clouds, or VPCs, with fine-grained rules. Security group policies manage instance-level traffic, and Route 53 Resolver DNS firewall policies block malicious domain queries. Creating a policy generally involves 5 steps. First, choose the policy type and region. Second, describe the policy by naming it and defining rules. Third, set the policy scope to specify which accounts and resources are covered. Fourth, optionally add policy tags. Finally, review and create the policy. For a WAF policy, you configure rule groups at the start and end of your Web Access Control List. Administrators can add custom rules in between, tailoring protection for each account. Denial of service, or DOS, and distributed denial of service, or DDoS, attacks are major threats to computer systems and networks. But what exactly are they, and how do they work? A DOS attack tries to overwhelm a system by flooding it with fake requests, making it unavailable to real users. DDoS attacks take this further, using many sources to send massive amounts of bogus traffic, making them even harder to stop. DDoS attacks often rely on botnets, which are networks of compromised computers controlled by a bot master. Tools like the high-orbit ion cannon and low-orbit ion cannon make launching attacks easy, even for those with little technical knowledge. Attackers use methods like ICMP, or ping floods, to overload networks, and SYN floods to exploit the TCP, handshake process. These attacks can target individual computers, routers, or entire networks, causing widespread disruption. Defending against DOS and DDoS attacks requires careful network design, proper configuration of protection devices, and a solid business continuity plan to keep services running even during an attack. AWS Shields is a managed security service designed to protect your Amazon Web Services applications from distributed denial of service, or DDoS, attacks. It automatically detects and mitigates threats that could impact your cloud environment, keeping your resources safe and available. DDoS attacks can target different layers of the Open System Interconnection, or OSI model. AWS Shield detects and defends against attacks at Layer 3, the network layer, Layer 4, the transport layer, and Layer 7, the application layer. This means it can stop bandwidth floods, protocol exploits, and HTTP request floods before they disrupt your services. AWS Shield comes in two versions. Shield Standard is free for all AWS customers and protects against common network and transport layer attacks. It integrates with services like CloudFront and Route 53. Shield Advanced, which costs extra, adds protection for more resource types, including EC2 and elastic load balancers, and covers application layer attacks as well. Shield Advanced offers enhanced monitoring, 24/7 access to the Shield response team, integration with AWS Web Application Firewall, and cost protection if your resources scale during an attack. Both versions provide dashboards to track attacks, but Shield Advanced delivers deeper insights, real-time metrics, and centralized monitoring across multiple accounts. AWS Network Firewall is a fully managed service designed to simplify network-level protection for your Amazon Virtual Private Clouds, or VPCs. With no infrastructure to manage, you can deploy and configure robust security in just a few clicks directly from the AWS console. One of the standout features of AWS Network Firewall is its flexibility in defining firewall rules. This allows you to exercise fine-grained control over your network traffic, making it easier to block or stop unwanted connections. You can also import existing rules written for common open-source platforms and even integrate third-party intelligence feeds provided by AWS partners. This adaptability ensures your firewall policies can evolve with your security needs. AWS Network Firewall works seamlessly with AWS Firewall Manager, especially within an AWS organization, making it easier to centrally manage all your network firewalls. There are multiple deployment models available, each designed to fit different network architectures and security requirements, providing you with options that best suit your environment. Typical use cases include inspecting traffic between VPCs, filtering outbound traffic, securing AWS Direct Connect and VPN connections, and filtering internet-bound traffic. AWS Network Firewall delivers comprehensive protection, helping you maintain a secure and compliant cloud environment. Every business faces security threats, from Bitcoin mining to rogue user behavior. As technology evolves, so do the risks. That is why Amazon Web Services, or AWS, introduced Amazon Guard Duty, a powerful threat detection service designed to protect your AWS environment. Amazon Guard Duty is a regional-based intelligent threat detection service. It monitors your AWS accounts for unusual activity by analyzing data from sources like virtual private cloud flow logs, domain name system logs, CloudTrail events, Elastic Kubernetes Service Control Plane events, Lambda network logs, and Amazon Relational Database Service login events. Guard Duty evaluates threats in two ways, using threat intelligence and machine learning. It checks your logs against known malicious sources, such as suspicious Internet Protocol addresses and URLs, using feeds from AWS, CrowdStrike, and Proofpoint. Machine learning helps Guard Duty spot unknown threats by learning your account's normal behavior and flagging anomalies. Guard Duty generates findings with severity levels, helping you investigate issues quickly. It integrates with AWS Security Hub, Amazon Detective, and Amazon CloudWatch Event Bridge, making it easy to aggregate, investigate, and respond to threats across your AWS accounts. Amazon Guard Duty delivers automatic, continuous security analysis, helping you safeguard your AWS environment against evolving cyber threats. Amazon Guard Duty is a threat detection service that analyzes activity across your AWS environment. Let's break down its key data sources and the optional protection plans that help keep your cloud secure. When you enable Guard Duty, it automatically analyzes logs from three core sources: VPC flow logs, AWS CloudTrail logs, and DNS query logs. VPC flow logs capture network traffic in and out of your virtual private cloud. CloudTrail logs track API calls and management events, while DNS query logs record domain requests made through Amazon Route 53. These sources provide foundational visibility into your AWS environment. Guard Duty also offers optional protection plans. S3 protection analyzes object-level activity in Amazon S3 buckets. Lambda protection monitors network activity for Lambda functions. EKS protection covers Kubernetes clusters with audit logs enabled by default and runtime logs requiring manual setup. RDS protection tracks login activity to Amazon Aurora databases. Malware protection identifies compromised EC2 instances, EBS volumes, or containers. All plans except EKS runtime logs are enabled by default. You can disable any protection plan if needed. Remember, Guard Duty does not retain your logs. Manage retention through each AWS service directly. Guard Duty's flexible data sources and protection plans help you detect threats and secure your AWS environment. Amazon Guard Duty is a security service that detects potential threats in your AWS environment. When Guard Duty finds something suspicious, it creates a finding in its dashboard, giving you the details you need to investigate and respond. Each finding is broken into 5 main parts: the summary, the affected resource, the action, the actor, and additional information. The summary includes key data like the finding type, severity, region, account ID, resource ID, and timestamps. If you use malware protection, you might also see a malware scan ID. These details help you quickly understand what happened and where. The finding type follows a specific syntax: threat purpose, resource type affected / threat family name dot detection mechanism. For example, cryptocurrency / EC2 / Bitcoin tool dot B dot DNS means an EC2 instance is running Bitcoin software and communicating with a Bitcoin-related domain. Not every finding includes all elements, but this structure helps clarify the threat. Findings are scored as high, medium, or low severity. High means immediate action is needed. Medium suggests suspicious activity, and low indicates a blocked threat. Prioritize high-severity findings to protect your environment. You can upload trusted IP lists to whitelist addresses and threat lists to flag known malicious IPs. This customizes GuardDuty's detection for your needs. Amazon Detective is a powerful service designed to help security teams investigate and analyze security issues across your Amazon Web Services, or AWS, accounts. It streamlines the process of uncovering the root cause of threats and suspicious activities, making investigations more efficient. Detective automatically ingests log data from multiple sources, including CloudTrail management events, virtual private cloud network flow information, Amazon GuardDuty, Security Hub findings, and Elastic Kubernetes Service audit logs. There is no need to manually enable or configure these logs. Once Detective is enabled, it uses machine learning and statistical analysis to build a behavior graph, which visually maps interactions between users and resources over time. The behavior graph highlights entities such as accounts, users, roles, IP addresses, and EC2 instances, as well as the relationships between them. For example, it can show when an IP address connects to an EC2 instance. You can view this graph in force-directed, circular, or grid-based formats within the Detective console. Amazon Detective integrates with Amazon GuardDuty and AWS Security Hub, allowing you to drill down into specific findings. It stores data for 1 year, enabling you to define custom date ranges and gain valuable historical context during investigations. To get started with Amazon Detective, first make sure Amazon GuardDuty is enabled in your Amazon Web Services account. This is required before you can use Detective. After GuardDuty is active, wait 48 hours, then enable Detective. Remember, Detective is a regional service, so you must enable both GuardDuty and Detective in every region where your workloads run. Begin by enabling Detective in a designated administrator account. Attach the Amazon Detective full access policy to this account's principal. For smooth integration, use the same account as your GuardDuty and Security Hub administrator. If you use Amazon Web Services organizations, avoid using the organization administrator account for Detective. You can invite up to 1,200 member accounts per behavior graph. Detective helps you investigate security findings, such as unusual login attempts or DNS data exfiltration, flagged by GuardDuty. Each GuardDuty finding includes an Investigate with Detective link, letting you drill into details and visualize affected resources. Detective maintains up to a year of aggregated data, supporting thorough root cause investigations. Detective's visualizations include maps of user logins, timelines, and charts, making it easier to correlate threat indicators and understand security events across your environment. Let's break down how pricing works for Amazon Detective, Amazon Web Services security investigation tool. Every account gets a 30-day free trial in each AWS region where Detective is enabled, giving you a risk-free way to explore its features and benefits. After the trial, Amazon Detective charges are based on the total volume of data ingested per account, per region, and per month. Pricing can vary slightly between AWS regions, so it is important to check your specific region's rates. As your data volume increases, you benefit from discounts on the per gigabyte price, making it more cost-effective for larger workloads. To estimate your monthly costs, you can use the AWS pricing calculator or Detective's own projected cost estimator. These tools help you understand how much you might pay based on your volume of VPC flow logs, CloudTrail management events, Amazon Elastic Kubernetes Service audit logs, and GuardDuty findings across all your accounts. For example, ingesting 500 gigabytes of data in the US East/1 region costs about $1,000 per month. At 10,000 gigabytes, the cost is around $8,500. And for 20,000 gigabytes, it's about $11,000 per month. Amazon Detective, a security service from Amazon Web Services, or AWS, has recently introduced several new features designed to make threat investigations even more effective. AWS is always working to enhance its services, and Detective is no exception. One of the standout additions is called Finding Groups. This feature uses machine learning and graph theory to group thousands of separate security findings into a single, connected security event. By doing this, it becomes much easier to identify and investigate related incidents that might otherwise be hidden among millions of discrete events. Finding groups help security teams see the bigger picture when it comes to potential compromises. With graph analysis, Detective can correlate findings and highlight the severity of a group, as well as the tactics used by threat actors. These tactics include initial access, privilege escalation, defense evasion, lateral movement, and exfiltration. The Detective console displays a summary of observed tactics, a visualization of the behavior graph, and a full list of involved entities and findings. You can now enable AWS security findings as a new data source within Detective. Best of all, these new features are automatically enabled and come at no additional cost. AWS Security Hub is designed to help you consolidate security findings and alerts for multiple accounts and provider products into a single, easy-to-use dashboard. With Security Hub, you can centrally view and manage security alerts, automate security checks, and respond quickly to security issues as they arise. Security Hub integrates seamlessly with several AWS services, including Amazon GuardDuty, Amazon Inspector, and Amazon Macie. It also works with AWS Firewall Manager, Identity and Access Management Access Analyzer, AWS Systems Manager Patch Manager, AWS Systems Manager Explorer and Ops Center, and Amazon Detective. The integration with Amazon Detective allows you to investigate findings in depth by switching between Security Hub and Detective. Additionally, Security Hub supports third-party integrations with over 60 vendors, such as Symantec, Sumo Logic, Splunk, Atlassian, Slack, ServiceNow, Rackspace, Palo Alto Networks, PagerDuty, and CloudStrike. Security Hub continuously runs account-level configuration and security checks based on AWS best practices and industry standards. It provides a readiness score, highlighting specific accounts and resources that need attention, making it easier to prioritize and address security issues efficiently. By consolidating findings and automating checks, Security Hub reduces the effort needed to collect, prioritize, and remediate security issues. Its broad integration with both AWS and partner solutions ensures comprehensive coverage and support for your organization's security needs. AWS Security Hub is designed to help organizations keep their cloud environments secure by automatically implementing 3 essential standards. These standards are defined by the Center for Internet Security, or CIS, an organization dedicated to making the connected world safer by publishing guidelines that protect against cyber threats. Once AWS Security Hub is enabled, it begins monitoring your environment against CIS benchmarks, providing clear visibility into your security posture. The first standard is the AWS Foundational Security Best Practices version 1.0, curated by AWS security experts. This includes basics like enabling multi-factor authentication, setting strong password policies, using groups for permissions, and ensuring Amazon S3 buckets are not publicly accessible. The second standard is the CIS AWS Foundations Benchmark, version 1.2, which focuses on best practices for AWS configuration, especially monitoring and logging. The third is the Payment Card Industry Data Security Standards, or PCI DSS, version 3.2.1, which is crucial for anyone storing or processing credit card information in AWS. Security in AWS is critical. AWS Security Hub simplifies the complex task of monitoring, collecting, and remediating security issues, helping organizations avoid costly mistakes and stay ahead in an ever-evolving threat landscape. Managing security in the cloud can be overwhelming, especially with the sheer volume of information generated by security services. AWS Security Hub simplifies this by providing a single point of access to your security findings and automatically checking your environment against AWS best practices. No matter your experience level with Amazon Web Services or AWS, you will need to use AWS Identity and Access Management, or IAM. IAM lets you create users, define access controls, and manage passwords and access keys, forming the backbone of your security setup. The root user is the owner of your AWS account and has unrestricted access, including billing information. Always enable multi-factor authentication, or MFA, for the root user. Afterward, create an administrator group, assign permissions, and add users with MFA to this group. Groups make it easier to manage permissions efficiently. Assign permissions to groups, not individual users, whenever possible. Provision access keys only if necessary and allow users to assume roles when required for specific tasks. Roles grant temporary permissions, often used for service-to-service interactions. Always follow the principle of least privilege, giving only the permissions needed. Never store access keys in your code or on Amazon EC2 instances or Amazon S3 buckets. AWS Security Hub is designed to be your central location for managing security across your Amazon Web Services environment. With Security Hub enabled, findings from services like Amazon Guard Duty, Amazon Inspector, and Amazon Macy are automatically sent to Security Hub, making it a single point of access for identifying and remediating security issues. Security Hub leverages AWS config rules to perform most of its security checks, ensuring your resources comply with AWS best practices and industry standards. It continuously runs account-level configuration and security checks, so you always have up-to-date insights into your security posture. Security Hub also integrates with Amazon Event Bridge, allowing you to automatically send notifications and remediation details for security findings. You can even use custom actions to route results to ticketing systems or automated remediation services, streamlining your response process. AWS Security Hub aggregates findings from over a dozen AWS services, including Guard Duty, Inspector, Macy, AWS Firewall, Systems Manager, Patch Manager, and Identity and Access Management Access Analyzer. This integration provides a unified view of your security landscape, making it easier to monitor and address potential threats as your environment evolves. Amazon Inspector has undergone a major transformation, introducing a new version with an updated architecture, enhanced features, and deeper integrations. This new Amazon Inspector replaces the previous version, now known as Inspector Classic, and brings automated security scanning to the forefront. Amazon Inspector automates security assessments for your applications, focusing on unintended network exposure, vulnerabilities, and deviations from best practices. You can enable Inspector at the organization level, making it easy to manage security across multiple accounts. With automated discovery and continuous scanning, Inspector delivers near real-time results, presenting findings that consider multiple factors to generate a meaningful inspector risk score. Inspectors' results are backed by a vulnerability database maintained by AWS security experts, and each finding includes recommended remediation steps. Once activated, Inspector scans Amazon EC2 instances, Elastic Container Registries, and Lambda functions for security issues and vulnerabilities. Inspector integrates seamlessly with AWS Security Hub, Amazon Event Bridge, and solutions from Amazon Partner Network partners. Inspector findings can be viewed in the Inspector console, sent to Security Hub, or dispatched to partner security tools. These integrations help you quickly implement workflows for remediation and issue resolution, keeping your applications secure and compliant. One of the biggest changes to Amazon Inspector is its reliance on the AWS Systems Manager agent, replacing the dedicated Inspector Classic agent. This consolidation means easier provisioning and improved performance. The AWS Systems Manager agent is open source, available on GitHub, and even comes pre-installed on select Amazon machine images. Amazon Inspector now supports a wide range of operating systems, including Amazon Linux, Amazon Linux 2, Amazon Linux 2 ECS optimized base AMIs, Mac OS versions 10.14 and 10.15, Ubuntu Server 16, 18, and 20, as well as Windows Server 2008 through 2019. With the latest improvements, Amazon Inspector automatically discovers and continuously scans your resources. There is no longer a need to manually schedule or configure assessment scans, nor do you need to select resources for evaluation. Inspector keeps monitoring your environment, even as changes occur. Inspector uses a knowledge base with hundreds of security rules and provides severity scores using the Common Vulnerability Scoring System, or CVSS, from the National Vulnerability Database. If you fix a vulnerability, Inspector detects and closes the finding automatically. Amazon Inspector integrates with AWS organizations for centralized management and connects with Amazon Event Bridge and Security Hub for near real-time automation. With just one click, you can enable Inspector across your organization and streamline security workflows. The Amazon Inspector dashboard gives you a comprehensive view of security findings across your entire environment. By selecting any finding, you can access detailed information. The dashboard streamlines key data, highlighting scan coverage, your most critical findings, and which resources have the highest number of issues.